All right, people. I believe all of you are doing great, having a good time. So, welcome to this beautiful channel that is Unacademy NEET English. And in the today's session, we're going to be talking about the magnetism. Okay. When it comes to the magnetism, it has got two chapters in it. The first one is magnetic effects of current, and then we have magnetism and matter. And we say over here, we will be talking about, we will be completing, that is two chapters, both of these two chapters in this particular marathon. So every single thing will be from the scratch. Every single thing will be from the basics. I would want you guys to watch it from the starting till the end. Okay, I have not basically missed any of the concepts out there. Every problem pattern is discussed. Even on every single topic, I have discussed more than 10 questions. Okay, so if you follow this, definitely you are going to score maximum, I would say, when it comes to the magnetism. And this is the extremely high weightage chapter. You can expect 4 questions from this portion, that is magnetism. So let's get started and let's dive into this. So the first topic that we have exactly over here is Biot-Savart's law. I say we have a wire over here. I'm taking a wire over here. Okay. And in this wire, I'm saying current is flowing. So I call this as a current carrying wire. I call this as a current carrying wire. So I have a wire over here in which current is flowing. So I call this as a current carrying wire. Now, guys, sure, near to the wire, I'm placing a magnetic compass. I'm placing a magnetic compass. Sir, why do we place the magnetic compass near to the wire? We are basically performing an experiment. I would want you guys to perform an experiment. You take a wire in which current I is flowing, and near to the wire, you place a magnetic compass. Okay, you place a magnetic compass. Now, guys, you start observing that the needle of this magnetic compass starts deflecting. Sir, what is the work of this magnetic compass? We say magnetic compass is used to detect the magnetic field. If I say the magnetic field is present over here, so you can find it, you can detect it with the help of the magnetic compass. So if I'm placing the magnetic compass over here, means I'm detecting the magnetic field, whether the magnetic field is present here or not. What I did is, I'll take a current carrying wire. I'll place a magnetic compass near it. Now, I start observing that the needle starts deflecting. The needle starts deflecting. So the needle of this magnetic compass start deflecting. What does that mean? That means magnetic field is present. Magnetic, let's suppose this is the point P. Magnetic field is present at point P. That means magnetic field is present at point P. Okay. So what I did, guys, as of now, please right now focus over here. See, previously, when it comes to the electrostatics, I told you if you have got a charge over here, we say this charge creates the electric field around it. Let's suppose if I am taking a magnet over here, this is a magnet. We say this magnet will create the magnetic field around it. Okay. Now, if I say we'll place a piece of iron over here or a coin over here in this magnetic field, what will happen? It will be attracted towards this magnet. So a magnet creates the magnetic field around it. A charge creates the electric field around it. This is the basic simple definition of the magnetic field. Now see, when it comes to the wire, I am taking the current carrying wire and I place the magnetic compass near it. I observed that this needle of the magnetic compass start deflecting. What does that mean? That means magnetic field is present at this point P. So can I say a current carrying wire produces the magnetic field. A current carrying wire produces the magnetic field around it. So basically, what I wanted to make you understand is that if you have got a wire over here in which current is flowing, and you place a magnetic compass near it, here also, here also, here also, here also, you observe that the needle of the magnetic compass start deflecting. What does that mean? That means a current carrying wire is creating the magnetic field around it. Like a bar magnet creates the magnetic field, similarly, a wire in which current is flowing creates the magnetic field around it. Please tell me in the chats if everything is crystalline clear till over here. I would want you guys to tell me in the chats if everything is crystalline clear till over here. Let me know in the chats. Let me know in the chats. Great. Okay, great. Now guys, now the question is, if you say a current carrying wire creates the magnetic field around it, if I ask you the simple question, how can we find how much is the magnetic field because of that current carrying wire? Guys. I say, let's suppose I'll take that wire over here, okay? And in this wire, let's suppose current I is flowing. I'm saying that, sir, at this point P, magnetic field is being created because of the wire. Now, if I ask you how much is this magnetic field at this point, for that, we use the Biot-Savart's law. So this is the first topic that we need to talk about over here. We say Biot-Savart's law. So Biot-Savart's law will help us to find how much is the magnetic field at the point P. Okay, now guys, so we say this is magnetic effects of current. That's why we say magnetic effects of current means a current carrying wire creates the magnetic effects around it. Now guys, so we say when it comes to the Biot-Savart's law, what does it say? It says that magnetic field due to a current carrying element. Okay, listen to me very carefully. We have to find how much is the magnetic field at point P. So what I want you guys to do is, I want you guys to take a small element of this wire, and I can say the element has got the length of dl. Current in this is I, and the length of the element is, let's suppose, dl. I'm taking a small element over here, that is dl. Okay, so the first thing I'll mention over here, let's take a small element, we say dl. Okay, and if I ask you how much is the current flowing in this small element, you say, sir, I. Why? Because in the entire wire, current flowing is I. So in this element also, current flowing will be same I. Same I will be the current flowing in this element. Now guys, I would want you to focus over here. If we say and we call it a current carrying element. Why do we call it a current carrying element? Why? Because this is a small element, and in this small element current is flowing. So that's why we are calling it the current carrying element. Because current is flowing over here. So we have to find the magnetic field because of this current carrying element at this point. Okay. Now guys, can I say magnetic field, and when it comes to the magnetic field, we represent magnetic field with B. So we say magnetic field
magnetic field due to this small element, due to this small element will be small, and that is what we call dB. Guys, sir, we were supposed to find the magnetic field because of the entire wire. No. Biot-Savart's law first tells us to find the magnetic field because of the small current carrying element. Later on, we'll find the magnetic field because of the whole wire, because of the entire wire. As of now, we need to find the magnetic field because of the small current carrying element, that is ideal. And that will be how much? That is dB. Now, guys, experimentally, we saw that. Let's suppose you have to find the magnetic field at r distance from the wire, and between this ideal and between this r, I am saying this is the angle theta over here. This is the angle theta over here. Now, guys, we say experimentally we observed that magnetic field because of this small current carrying element at this point P, it is directly proportional to, we say, this magnetic field dB. We saw that it is directly proportional to, we say, sir, ideal. More bigger, if you have the big current carrying element, we say it will create the big, we say, large magnetic field at this point. Bigger is the element, bigger will be the magnetic field. Smaller is the element, smaller will be the magnetic field. That's why we say directly proportional. One more thing, if you go far from the wire, this is the wire, if you go far from the wire, we say magnetic field will decrease. If you come close to the wire, we say magnetic field will increase. So I can say over here, this magnetic field is inversely proportional to r square. It is inversely proportional to r square. One more thing, we observed that experimentally. This magnetic field, because of this current carrying element, this dB, it came out to be directly proportional to, we say, sine of theta also, sine of this angle theta also. More is the value of theta, more will be the magnetic field. More is the value of theta, more will be the magnetic field. Okay. Now, if I say combine all the three equations, I'll write over here. Combine all the three equations. So can I write? We say this magnetic field dB, it is proportional to, I can say this is IDL, and we say sine of theta, ideal sine theta. This magnetic field is proportional to ideal. This magnetic field is proportional to sine theta, and it is inversely proportional to, we say, r square. dB is proportional to IDL sine theta divided by, we say, r square. Now, I would want you guys to replace this proportionality. Replace the proportionality with a constant. So if we replace this proportionality with a constant, so I can say that will be mu naught divided by 4 pi. Sir, what is this mu naught by 4 pi? Like in Coulomb's law, you have 1 by 4 pi epsilon naught. That is the constant. Here you have got the constant mu naught by 4 pi. Over there, it was permittivity of free space. Over here, it is permeability of free space. Whatever the work permittivity does in the electrostatics, same work this mu naught will perform over here. And then I can write over here this IDL, and then I say sine of theta divided by, we say, r square over here. This is what we call the Biot-Savart's law, or this is what we call the magnetic field because of the small current carrying element. This is what we call the magnetic field because of the small current carrying element. And guys, let me just tell you, this Biot-Savart's law helps us to find the magnetic field because of the current carrying element, not because of the entire wire. So we say this is the magnetic field, that is B, due to a small current carrying element. This is the magnetic field because of a small current carrying element, that is dB is equal to mu naught by 4 pi I dl sine theta by r square. And when it comes to the value of this mu naught by 4 pi, you also remember, we say the value of this mu naught divided by 4 pi. The value of this mu naught divided by 4 pi, we say it is 10 raised power minus 7. It is 10 raised power minus 7. Keep this thing in your mind. Keep this thing in your mind. Now guys, listen to me very carefully. Since we say magnetic field is a vector quantity, okay, it has got magnitude and it has got direction. I would want you guys to find the vector form of this. This is the scalar form. I would want you guys to find the vector form of the Biot-Savart's law. See guys. I say vector form of Biot-Savart's law. Vector form, this is BIOT. Vector form of the Biot-Savart's law. Now guys, understand one thing very carefully. As we recently got this magnetic field because of a small current carrying element, that is mu naught divided by 4 pi, and then we say I dl, and we write over here sine theta divided by r square. Guys, what if I ask you one single thing over here? What if I ask you one single thing over here? What is that? Do you guys know a unit vector? Do you guys know a unit vector? Unit vector. Sir, let's suppose I say I have got a vector over here A. A is any vector. And I want to write its unit vector. We say we'll place a cap on top of it. It becomes the unit vector. So means if you want to write the unit vector of Y, you'll have to place this cap. And when it comes to the magnitude of this unit vector, it is always 1. The magnitude of the unit vector is always 1. Cool. Now guys, since this is a unit vector, we say, let's talk about any vector. Let's suppose if we talk about this vector, let's talk about this, we have got a vector quantity A. We know this vector will have the magnitude, it will have the magnitude, that is magnitude of A, and it will have the direction. And direction we write in terms of unit vector. So unit vector is used to find the direction. It helps us to find the direction. So vector A multiplied by mod of A multiplied by vector A. This is the magnitude, this is direction. From here, I can write this unit vector will be equal to that vector A divided by mod of A, divided by mod of A. Similarly, if I say, you have got a vector Y over here, you have got a vector Y, or you have got a unit vector R. How can we write this unit vector R? You say, sir, I'll write this vector R divided by, we say, mod of R. This is how we can write this unit vector over here. Cool? Yes. Now, guys, and what is the value of this unit vector? It is always 1. If I say, multiply here with a unit vector, multiply with a unit vector. So I can say this dB will come out to be, that is mu naught divided by 4 pi. And then I can write over here I dl, and then we say sine of theta divided by r square. And I'll write the unit vector of this r. So I can say over here, sir, r. Can we do it? Yes, we can do it. Why? Because the magnitude of a unit vector is 1, so it will not create any difference. Okay, 1 multiplied by something will be something only. Now, guys, I say, can I write it? Guys. We say, here it is. Ideal, you can consider this as one vector. R is another vector. And then you have sine of theta. We say as. If I say A vector cross B vector, it is always equal to AB sine of theta. You might have heard A cross B is AB sine theta. This is the cross product of two vectors, multiplication of two vectors by using cross product. Similarly, here it is IDL sine theta into R. So IDL is one vector, R is another vector. So A vector, B vector. You can consider this as A, you can consider this as B, AB sine theta. So we can write over here, this dB will come out to be, that is mu naught divided by 4 pi. And here, this will be simply, that is IDL vector and then we say cross, I can write over here this R vector in this particular case. Okay, okay. And divided by, we say over here R square, because A cross B is AB sine theta. Then further, we can write in the next step, that is this dB will come out to be, that is mu naught divided by 4 pi. dB is equal to mu naught by 4 pi. Guys, how do we write this unit vector? That is vector R divided by mod of R. So I can write over here, this will be IDL vector cross. Instead of this, I would want you guys to write this R vector divided by this R, and this R square will become over here, that is R cube. Now I would want you guys to place this in a box. Place this in a box over here. So we say this is the vector form. We say this is the vector form of Biot-Savart's law. Biot-Savart's law. And this was asked in NEET 2020. This was asked in NEET 2020. What is the vector form of Biot-Savart's law? 4 options were given. So this is so dB is equal to mu naught, and you need to put the vector on top of this. So dB vector is equal to mu naught by 4 pi IDL cross R divided by R cube. So this is what we call the vector form of Biot-Savart's law. I would want you guys to let me know in the chats if everything is crystal and clear. Everyone means everyone. Everyone means everyone. Tell me, guys. And smash the like button, guys, if you have not liked the session yet. I would want you guys to mark the attendance. Marking the attendance is mandatory. Great. So we say this is what we call the vector form, and this is what we call the scalar form. Scalar form and vector. Now, guys, let's talk about the magnetic field due to a finite current carrying wire. Magnetic field due to a finite current carrying wire. See, guys, till now, because of the Biot-Savart's law, it helps us to find, guys, understand, it helps us to find the magnetic field because of a small current carrying element. What if I tell you to tell me the magnetic field because of the entire wire over here? So now let's find the magnetic field, that is B, due to the whole wire. I would want you guys to tell me what is the magnetic field because of the entire wire. That's what we need to discuss right now. Now, guys, see, in this particular case, let's suppose we have got this wire over here in which current I is flowing. This is the current I flowing. We are supposed to find the magnetic field at point P. Okay. I'll first write the statement over here. Since the current is flowing in the wire. Since the current is flowing in the wire, so it produces the magnetic field. Then where are we supposed to find the magnetic field? I say to find the magnetic field at, we say, R distance. At R distance. We are supposed to find the magnetic field at what distance? We say at R distance. Now, guys, what is the method that we actually use? We use the Biot-Savart law only. We'll take a small current carrying element. We'll find the magnetic field because of that over here. That will be very small. Then we'll take one more element. We'll find the magnetic field because of that element. Then we'll take one more element. We'll find the magnetic field because of that element by using Biot-Savart's law. Now, once we get the magnetic field because of all the elements over here, Once we get the magnetic field because of all the elements over here, we'll add those small magnetic fields with the help of the integration. Okay? And finally, the result we are going to get, guys, I'll not do the derivation now. I'll directly write over here. So we say that magnetic field will be simply, that is mu naught I divided by, we say 4 pi r. Mu naught by 4 pi is the constant. I is the current flowing in the wire. R is the distance where you are supposed to find the magnetic field. And guys, if I say you join this point, you join this point with one end of the rod, okay? And it is creating the angle over here, it is making the angle over here. Let's suppose this is theta 1. If I say you join this point with another end of the rod, it is making the angle theta 2 with r. So I can write over here further, then we say sine of theta 1 plus we say sine of theta 2. So this will be the magnetic field because of the entire wire. This is the magnetic field because of the entire wire. Keep this thing in your mind. Guys, previously the Biot-Savart's law tells us the magnetic field because of the element. By using the Biot-Savart's law only, we calculated the magnetic field because of the entire wire at this point, that is mu naught I by 4 pi r, sine of theta 1 plus sine of theta 2. As simple as that, Okay? So I didn't do the derivation over here, but I'm telling you this directly because we are not supposed to waste the time. Now guys, since this magnetic field is a vector, let's talk about the direction. We say direction of magnetic field. Guys, listen to me very, very, very carefully. I would want you guys to listen to me very, very, very carefully. Let's talk about the direction. Let's talk about the direction of the magnetic field. See, guys, when it comes to the direction of the magnetic field, see, the simple thing is, I would want you to place your thumb along the direction of current, okay? This is the thumb you have got. Place the thumb along the direction of current. Then curl your fingers at the point where you have to find the magnetic field, like this. So I'm curling over here, it is pointing inwards. So the direction of current is upwards. So I'm saying, what is the magnetic field at point P? Curl your fingers at point P. It is going inwards. So here, magnetic field will be inwards. So I'll write the same statement over here. Place your thumb along current. Place your thumb along current. Then curl your fingers. At that point. Then curl your fingers at that point where we have to find the magnetic field. And then I say that will give the direction of magnetic field. What I'm saying in this particular case is, place your thumb along the direction of current, curl your fingers at this point where you have to find the magnetic field. So we say it is pointing inwards, so it will be, magnetic field will be over here in. So what does this cross actually mean? Cross means the direction is inwards. Okay? Now guys, I would want you guys to tell me the answer of this question. Let's suppose I give you a wire over here. This is a wire. Okay? And in this wire, current is flowing in the upward direction. You guys are supposed to tell me what is the magnetic field at this point P, at this point P. What is the direction of the magnetic field? What is the thing you guys are supposed to do? Place your thumb along the direction of current, curl your fingers at this point. So we say shear magnetic field is inward. Now, if I ask you to tell me the direction of the current at point Q, we say place your thumb along that, this is the right hand. Place your thumb along the direction of current, curl your fingers at this point. Thumb is pointing outwards. So we say shear magnetic field will be outwards. This dot means outwards and this cross means inwards. So I can say magnetic field is outward. And shear magnetic field is inward. Okay, let's suppose I give you one more example over here which will make you understand. Let's suppose I have got a wire over here. In this wire, current is flowing, that is I. What is the magnetic field at this point? What is the magnetic field at this point? See guys, place your thumb along the direction of current, curl your fingers. So we say shear magnetic field is outward. Now when it comes to from the lower side of this wire, place your thumb along the direction of current, thumb is curl your fingers, it is pointing inwards. So here magnetic field will be inwards. As simple as. Guys, please tell me in the chats if everything is crystalline clear. I would want you guys to give me the signal. ASAP, ASAP. Everyone means everyone. Everyone means everyone. Let me know if everything is crystalline clear. If everything is crystalline clear. Now guys, listen to me very carefully. Listen to me very carefully. Find the magnetic field at point P. Find the magnetic field at point P. Okay? Find the magnetic field at point P. We'll have to find the direction in so many questions. So chill, you don't have to worry about anything. Now see. Now see. Guys, see. In this particular case, we have got a wire over here in which current 2 ampere is flowing. And you guys are supposed to find out the magnetic field at our distance, which is at 4 meters. We know when it comes to the magnetic field, we say magnetic field because of the wire is mu naught by 4 pi. Mu naught by 4 pi. And I say over here, I divided by R. And then I'll write over here sine of theta 1 plus I say sine of theta 2. So this is the general equation that we need to use over here to find the magnetic field. Now, I can say over here B will be, what is the value of mu naught by 4 pi? I told you it is 10 raised power minus 7. How much is the current flowing over here? That is 2 ampere divided by. At what distance you guys are supposed to find the magnetic field? 4 meters. And then I'll write sine of. What is this angle given over here? That is theta 1. That is sine of 30. Then we say plus sine of 30 over here. So I can say magnetic field is equal to. So 2 1s are 2 2s are 4. So it will be 1 by 2. So that will be 0.5. 0.5 multiplied by this 10 raised power minus 7. And sine 30 is 1 by 2 plus 1 by 2. Half plus half is 1. So I can say in this particular case, magnetic field will be 0.5 into 10 raised power minus 7. Okay. And you can write over here Tesla, T. We measure the magnetic field in Tesla. So you can write the Tesla. Is that clear? Is that clear? Tell me, guys, is that clear? Now, how do we find the magnetic field direction? Guys. Place your thumb along the direction of current. Thumb is upward, current is upward, so place your thumb along the direction of current. curl your fingers at this point. It is curling inwards. So this is giving you the direction inwards, this curling. So means magnetic field is inwards. So I'll write over here cross. Cross means inwards. Great. Great. Now guys, magnetic field because of the infinite wire. See. Since the current is flowing in the wire, it will create the magnetic field. We are supposed to find the magnetic field at this point P, which is at R distance. And it is going till infinity from the upper side. It is going till infinity from the lower side. So that's what we call the infinite wire over here. Now guys, let's suppose when it comes to the infinite wire, guys, how do we find the magnetic field? The general formula is mu naught I by 4 pi r sine theta 1 plus sine theta 2. In this particular case, I want you guys to define the theta 1 first. Guys, see, if I say when it comes to the theta 1, you join this point with one end of the rod. Sir, is this one end of the rod over here? We say no. Is this end of the rod over here? No. Then where is the end of the rod? We say end of the rod is at infinity. So I cannot join it something like this. I'll have to make it something like this. We say then only they will meet at infinity. Then only they will meet at infinity. Similarly, if you want to join this point with another end of the rod, that's not over here, but that's at infinity. You'll have to make it something like this. We say this line will join this end at infinity. This line will join this end at infinity. Now, clearly I can see over here, this is the value of theta 1. So theta 1 and this is the value of theta 2. And I can say here, theta 1 is equal to 90 degrees. And I can say theta 2 is also 90 degrees over here. So in case of an infinite wire, theta 1 and theta 2 both are, we say, 90. Now use the general formula. The general formula is, as we say, magnetic field is mu naught by 4 pi. Then we say I by R. Then I can write over here sine of theta 1 plus we say sine of theta 2. Okay. Now the current flowing is I and we are supposed to find at R distance. So I can say this magnetic field will be, that is mu naught by 4 pi. And then I can say I divided by R. And then I'll write over here sine of 90 plus we say sine of 90. Now we know that sine 90 is 1, sine 90 is 1. 1 plus 1 will come out to be 2. So I can say this magnetic field will be mu naught by 4 pi and I'll write I divided by R and over here it is 2. And over here it is 2. So here I can say, so this 2 1s are, 2 2s are 4. So this magnetic field will come out to be, that is mu naught I divided by, we say 2 pi R. So this will be the magnetic field because of the infinite wire. This will be the magnetic field because of the infinite wire. At what distance? At R distance. And what is the direction over here? Place your thumb along the direction of current and curl your fingers at this point. So it is curling, it is giving us the direction inward. So because of the infinite wire, this is the magnetic field at R distance. Guys, is this clear? Please tell me in the chats. Please tell me in the chats. Next, magnetic field because of a semi-infinite wire. Let's now talk about the magnetic field because of the semi-infinite wire. Guys. When it comes to the semi-infinite wire, I would want you to focus exactly over here. See. In this particular case, semi-infinite wire means which is going till infinity from one end only. Okay? And another end is finite. That's why we call it the semi-infinite. One end is going till infinity and another end is finite. And in this particular case, if I want you guys to join this, we have to find the magnetic field at this point at R distance. Current flowing in this is I. I would want you guys to join this with one end of the rod. Sir, can I join it something like this? No. Why? Because its end is not over here, but that's at infinity. So I can say you will have to make this line something like this. So we say this line will meet its end at infinity. So here this will be the value of theta 1 in this particular case. So I can say this will be the value of theta 1 in this particular. Now, guys, if I say you have to join this with another end of the rod, so how you are going to do that? We say you'll do it something like this. So I can simply say, when you join it something like this over here, sir, between this line which you are joining and between this R, they are parallel to each other. Okay? Okay? So if this is the line and this is R, if they are parallel to each other, so I can say theta 2 will be 0 degrees. So in this particular case, I can simply say, we say here theta 1 is 90 degrees and we say theta 2 will be 0 degrees. So you'll remember from now onwards, when it comes to the semi-infinite wire, theta 1 we take 90 degrees and theta 2 we take 0 degrees. Now if we want to find the magnetic field, we'll use the general formula. We say as magnetic field is equal to mu naught by 4 pi. Then we say I divided by R. And then I'll write over here sine of theta 1 plus we say sine of theta. And I can say in this particular case, this is mu naught divided by 4 pi. And I can say this is I by R. And sine of theta 1 in this case will be sine of 90. And this will be sine of 0 degrees. Now, how much is sine 0? Sine 0 is 0. What is the value of sine 90? That is 1. So 1 plus 0 will be 1. So magnetic field will come out to be, that is simply mu naught by 4 pi. And then we say I divided by R. Mu naught by 4 pi, then we say I divided by R. So this will be the magnetic field because of a semi-infinite wire at R distance. Okay? And one more thing I just want to tell you here. What is that? That is, what is the direction? Place your thumb along the direction of current. Curl your fingers at this point, so it is getting inwards. So I can say the direction here is that clear? Is that clear? Please tell me in the chats, everyone. Everyone means everyone. And guys, if you have not liked the session yet, I would want you guys to hit the like button as soon as possible. As soon as possible. As soon as possible. Smash the like button. Smash the like button. Liking the session is mandatory. Now, guys, let's move on to the next question that we have over here. Find the magnetic field in this case. Okay. See, guys, let's suppose I give you the value over here, that is theta. This is R. You have got a wire, and in this wire, current I is flowing. This is the current I flowing. And this wire is going till infinity from one end. And another end of the wire is here. And always remember, guys, always remember, this R distance is basically the perpendicular distance. It is perpendicular. Don't say, sir, I can take the R something like this also. No. We say this R distance is the perpendicular distance. Now, current is flowing. It will create the magnetic field at R distance. We say to find the magnetic field at R distance. I would want you to tell me one thing, guys. Here, if you join this with one end of the rod, which is at infinity, don't you think that this value, this angle is given as alpha? We can say here, theta 1 is given as alpha, and that will be exactly 90 degrees. Why? Because it is going till infinity. So if you join this with one end, it will be 90 degrees. And clearly, if you join this with another end over here, so we say this will be theta over here. So theta 2 in this case will be theta. Sir, can we call this as the semi-infinite wire? Yes. We can call this as a semi-infinite wire. Don't say in case of the semi-infinite wire, the second angle is 0 degrees only. No, it can be something other than 90. It can be something other than 90. It can be 0 also, 30 also, 60 also. Similarly over here, the second angle over here is because its another end is finite, visible. We can see it over here. It is defined. It is not defined. So I can say here magnetic field will come out to be, that is mu naught I divided by, we say 4 pi R. And then I'll write sine of theta 1 plus we say sine of theta. Now guys, in this particular case, I can say this magnetic field is mu naught I divided by we say 4 pi r. And what is the value of sine of theta 1? That is sine of 90 plus. What is the value of sine of theta 2? So I can say that is sine of theta only. So here magnetic field will come out to be that is mu naught I divided by 4 pi r. And I can say over here sine 90 is 1 plus and this will be sine of theta. As simple as that. I hope this is crystal and clear to each and every single student out there. Okay? Is this clear? Is this clear? Is this clear? Let's talk about this question. Find the magnetic field at point P. Sure. And if I just tell you in this particular case, this angle and this angle is not given. Theta 1 and theta 2 is not given over here. Sure, in this case, alpha and beta are given. Sure. In this particular case, I can say here alpha and beta are given. Means angle between this and this. So this angle and this angle, but this angle is not given over here. How we are supposed to solve this particular question? Let me just tell you, my dear. See. Let's suppose this angle over here we call as theta 1. This angle we call as theta 2. Let's assume the angles theta 1 and theta 2. Okay, yes, absolutely cool. Now guys, see, we don't know the value of theta 1. Let's first find out the value of theta 1. Let's first find out the value of theta 1. See, let's take a look at this upper triangle. We say from the upper triangle, this one. Could you please tell me what is the sum of all the angles of the triangle? You say, sir, that is 180 degrees. So in this case, I say sum of all the angles is 180 degrees. So that will be this angle plus this angle plus this. This is 90 over here. So I can say 180 means this angle alpha. So first I'll write 90 plus I'll write over here alpha, then plus I'll write over here theta 1. Sum of all the angles of a triangle will be equal to 180. Now, if you take it over here, so it will become 180 minus 90 and alpha will be over here, minus alpha will be equal to theta 1. 180 minus 90, so that will be 90 minus alpha will be equal to theta. So, you got the value of this theta 1, that is 90 minus alpha. Similarly, from the lower triangle. Similarly, from the lower triangle, we say theta 2 will come out to be 90 minus this beta. Using the same approach, 90 minus this beta. Now, you got the value of theta 1 and theta 2. Now, it's easy for you to find out the magnetic field. So, I can say magnetic field will be mu naught I divided by 4 pi r. And then I'll write over here sine of theta 1 plus I say sine of theta. And in this case, I can write magnetic field is simply that is mu naught I divided by we say 4 pi r. And sine of theta 1 is 90 minus alpha. So I can write over here, this is sine of 90 minus alpha, then plus sine of 90 minus b. I hope this is visible, 90 minus b. Okay. And further, you can write in this particular case, this magnetic field will come out to be mu naught I divided by 4 pi r. And then you can say over here, sine 90 minus alpha is cos alpha. So I can say this is cos of alpha plus sine 90 minus beta will be cos of beta. So you can make it something like this. So if, my dear friends, from now onwards, this angle and this angle are given, you can directly use cos of alpha plus cos of beta. Or you can write this only, this also. But in that case, you'll have to do 90 minus alpha or 90 minus beta. Please tell me in the chats if everything is crystalline. Please tell me in the chats if everything is crystalline. Everyone, guys, let me know in the chats if everything is crystalline clear. Great, great, great. Now, we have got a question over here. This alpha angle in this particular case is given as 30 degrees and beta in this case is given as 60 degrees. So whenever alpha and beta are given in that case, what you guys are supposed to do is magnetic field will be mu naught I divided by 4 pi r. Then you will write over here, we say cos of alpha plus we say cos of beta. As simple as that. As simple as that. As simple as that. And here, I can say this magnetic field will be mu naught I divided by 4 pi r. And then cos of alpha is 30. So cos of 30 plus we say cos of 60 because beta is given as 60. Can I say in this particular case, cos 30 is root 3 by 2. Cos 60 is 1 by 2. So you can put up the values also. So mu naught I divided by 4 pi r. And I can say in this particular case, this will be root 3 by 2 plus I can say 1 by 2. So this will be the value of magnetic field in this particular case. And if you find the direction over here, direction of magnetic field will be inwards. Place your thumb along the direction of current and curl your fingers at this point. That will give you the direction inwards. So I can say it is cross over here. I can say it's crossover. Okay. You can find it in terms of sign also. That will be 90 minus 30. That will be 60. So sine of 60 plus sine of 30. Sine 60 plus sine 30. Give me the signal in the chats if this is crystalline clear to each and every single student. Everyone means everyone. Everyone means everyone. Great, great, great. Now, guys, if I ask you, what is the magnetic field? What is the magnetic field because of a square loop at the center? Guys, if we talk about this square loop, it has got the side L. This square loop is made of 4 wires. We say square loop is made up of 4 wires. It is made up of 4 wires. So square loop is made up of 4 wires. If we find the magnetic field because of a 1 wire, don't you think that we'll multiply it with 4, we'll get the net magnetic field? Please don't say 0. No. 0 will not be the answer. We say, sure. I can say net magnetic field will be whatever is the magnetic field because of 1 wire, multiply it with the 4 because here you have got 4 wires. So that will be the net magnetic field. 4 times magnetic field due to 1 wire. 4 times magnetic field due to 1 wire. Now, guys, I would want you to focus exactly over here. See, if you have to find the magnetic field because of this wire at this point, so the first and the foremost thing is, you have to define the perpendicular distance. Sir, that will be this perpendicular distance as r. And if the side is L, don't you think that this r from here to center, this will be L divided by 2? Exactly, it will be L by 2. Now, I would want you to join this with one end of the rod. I would want you to join this with another end of the rod. Okay. So I can say this will be the value of theta 1, this will be the value of theta 2. Guys, I'm finding the magnetic field because of 1 wire and then I'll multiply it with 4, we'll get the net magnetic field. Okay. So I can say in this particular case, this r will be L divided by 2. R will be L by 2. Now guys, so this angle over here is theta 1, this angle over here is theta 2. Could you please tell me, guys, see. I can say over here as let's find the magnetic field due to one wire. Let's find the magnetic field due to one wire. So sure, I can say in this particular case, theta 1 is equal. Guys, in case of the square, this total angle is 90 degrees. So this angle would be, this theta 1 would be 45 degrees. So I say this is 45 degrees and theta 2 will be also 45 degrees because total is 90. 45 plus 45 is 90. And in this case, what I can say is because of this wire at this point, magnetic field will be, that is mu naught I divided by 4 pi r. And then I'll write over here sine of theta 1 plus I can say sine of theta. Because this is the general formula by which we can find the magnetic field because of a wire. And I can say in this particular case, this magnetic field will come out to be, that is mu naught I divided by 4 pi r. And then I can say, what is the value of theta 1 in this case? That is 45. So I can write over here sine of 45. Then we say plus sine of 45 in this case. So sine 45 plus sine 45. And instead of this r, I would want you guys to write. Instead of this r, I would want you guys to write. What? Guys, what is the value of r? That is L by 2. So mention it L by 2 over here. So I can say this is 4 pi L divided by 2. 2 ones are 2 twos are. Now guys, tell me what I can say in this particular case, this magnetic field will be, that is mu naught I divided by, this is 2 pi L. And sine 45 I can write over here, that will be 1 by root 2 plus sine 45 is 1 by root 2. So 1 by root 2 plus 1 by root 2. Don't you think that it will become 2 by root 2? Yes, it is 2 times. So I can say magnetic field will come out to be mu naught I divided by 2 pi L. And over here, this will be 2 divided by root 2. Okay. Now guys, this 2 and 2 you can cancel out over here. So this magnetic field will come out to be, that is mu naught I divided by over here root 2 pi into L. And this is the magnetic field because of one wire. We are supposed to find the magnetic field because of the 4 wires. So magnetic field net will be simply, that is 4 times magnetic field because of one wire. Because of one wire, how much we got? Mu naught I by under root of 2 pi L. So this will be simply mu naught I divided by root 2 pi into L. This is what we got. Yes. Now, I would want you guys to rationalize it. Multiply with root 2 and divide with root. Okay, again, you can cancel it. It is one and the same. Now, guys, always remember I have told you previously, root 2 into root 2 becomes 2 because a root 2 multiplied by root 2 will be root 2 whole square. This square and root will cancel, so it will be 2. Now, can I say this root 2 and root 2 is 2? 2 ones are 2 twos are 4. So I can say this will come out to be net magnetic field is 2 root 2, that is mu naught I divided by, we say, pi into L. So I would want you guys to keep this in a box. This will be the magnetic field because of the square loop exactly at the center. Now the question is, sir, what is the direction of the net magnetic field? See guys. Let's first find the magnetic field direction because of this. Place your thumb along the direction of current, curl your fingers at this point, it is inward. Now, because of this wire, this is the direction of current. Guys, see, this is the direction of current. Place your thumb along the direction of current, that is this, curl your fingers, it is inward. Now, because of this, place your thumb along the direction of current, so curl your fingers, it is inwards. Because of this, here, this is the direction of current, this. Place your thumb along the direction of current, curl your fingers, it is inwards. So because of all the 4 wires, it is inwards. That's why we are adding the magnetic field because of 4. If it was outward, inward, then we would have subtracted. So I can say this is in. So that is cross. Guys, tell me in the chats if everything is crystalline clear. Tell me in the chats if everything is crystalline clear. You have got a question on the screen. You have got a question on the screen. The question says, find the magnetic field at the center. Okay, this is the center P. Due to the infinite wires. Guys, see, in this case, you have got a wire, it is going till infinity. And from here also, it is going till infinity. You have got this wire, it is going till infinity. From here also, it is going till infinity. Okay. Okay. So because of these two infinite wires, in this current is flowing 5 ampere. In this current is flowing 2.5 ampere. You guys are supposed to tell me what is the magnetic field at this point. Okay. And this distance is given in this case as R. This distance is also given as R. Such that the distance between the two wires is given as 5 meters. It is 5. It is 5. I see. I would want you to focus. We say as. Let's say this is the wire 1 and let's suppose this is the wire 2. When it comes to the net magnetic field, we say net magnetic field at point P will be because of the wire 1, it will be because of the wire 2. See, let's find the direction. Guys, see, place your thumb along the direction of current, curl your fingers at this point, it will be inwards. It will be inwards. Now, guys, because of this, place your thumb along the direction of current, curl your fingers, it's outwards. Magnetic field of wire 1 is inwards. Magnetic field of wire 2 is outwards. So when the two vectors are in the opposite direction, we subtract. When the two vectors are in the same direction, we add. Here we need to subtract. So I can say magnetic field due to 1 minus magnetic field due to 2. And this magnetic field is inwards and this magnetic field is outwards, cross and dot. And why did I do B1 minus B2? The reason for that is we say B1 is greater than B2. Why? Because more current is flowing in this one, so it will create more magnetic field. Less current is flowing in this one, it will create less magnetic field, and that's the reason I did B1 minus B2. Bigger minus smaller. We always do bigger minus smaller, not the smaller minus big. Now tell me, guys, let's write the magnetic field because of this wire at a distance. So I can say net magnetic field will come out to be magnetic field due to 1, that is mu naught I divided by, we say 2 pi R. And here current in this case is 5 ampere, so I call it I1 minus mu naught I2 divided by, we say 2 pi R. Why? Because in this case, we say current is flowing as 2.5 ampere, so that's why. That's why. I am simply saying in this case, magnetic field because of this wire at this point will be inwards. Why? Place your thumb along the direction of current, curl your fingers, it is in. Magnetic field because of this wire will be outwards. And magnetic field because of this wire will be more. Why? Because 5 ampere current is flowing. Here only 2 ampere current is flowing. More is the current, more is the magnetic field. Less is the current, less will be the magnetic field. Guys, net magnetic field means how much is the magnetic field because of both. If I say this is a block over here, 10 Newton force is acting in this direction, 5 Newton force is acting in this direction. How much is the net force? 10 minus 5, that is 5 Newton. If I say this is a block over here, 10 Newton force, 10 Newton, this 10 Newton force, 5 Newton force in the same direction. How much is the net force? 15 Newton. Why? Because you are adding over here. If the two vectors are in the same direction, you add. If the two vectors are in the opposite direction, you subtract. So I can say, in this case, mu naught, what will you take common over here? Mu naught divided by 2 pi R. Because this R is same in both. So you can say I1 minus, you say I. Now guys, you will write mu naught divided by 2 pi. What is the value of R? Guys, from here to here it is 5 meters. Don't you think half of this will come out to be R that is 2.5 meters? So you can write over here this is 2.5. And I1 minus I2, I1 is 5 ampere minus I2 is 2.5 ampere. 5 minus 2.5 is 2.5 and 2.5. So net magnetic field will come out to be mu naught divided by 2 pi. This is the net magnetic field. This is the net magnetic. Okay. Even you can multiply with 2 and you can divide with 2. It'll become, we say 2 times of mu naught divided by 4 pi over. If you multiply and divide, once again you can cancel. Now guys, mu naught by 4 pi is how much? 10 raised power minus 7. So you can say net magnetic field will come out to be 2 into 10 raised power minus 2 into 10 raised power. Is this clear? And what is the direction of net magnetic field? We say direction of net magnetic field is always the direction of bigger magnetic field, bigger vector. That is B1 is bigger, so inward. So it will be in. I hope this is crystalline clear. I hope this is crystalline clear. Next, we have got this question over here. We have got this question over. See guys, a straight wire of finite length carrying current I subtends an angle of 60 degrees at point P. You have got a wire in this case in which current flowing is I. Hey guys, give me the signal in the chats if everything is crystalline clear till over here. I would want you guys to tell me in the chats if everything is crystalline clear till over here. Let me know in the chats. Let me know in the chats if everything is crystalline clear till over here. Great. We say a straight wire, you have got a straight wire over here. You have, guys, we have a lot of questions that will come, okay? Chill scenes. If there is a confusion in any part because 1 or 2 students are having the confusion, you guys can watch that part later on, okay? We have a lot of questions that I'll be solving, okay? That'll clear all the confusions, that's for sure. So right now, focus on this one. See, guys, I'll make the figure over here. Chill. I'll make the figure over here. We have got a wire. This is the wire. And it says that in this wire, current is flowing. And this wire is creating an angle at point P. This wire is creating an angle at point P. Here, wire is creating the angle exactly over here, and that is 60 degrees. That is 60 degrees, point P. This distance is X and this distance is X. And we say current I is flowing in the wire. Okay. Now, guys, we are supposed to find the magnetic field over here. This is not a triangular shaped structure. No, it's only one wire. From one end till over here, it is X. From here, it is X. We have to find the magnetic field because of this at this point. Guys, see, what is the first thing we do? We draw the perpendicular distance. Let's suppose this is the perpendicular distance. Okay. And this will be R. Because of this wire, you have to find the magnetic field at point P, which is at what distance? Which is at R distance. Yeah, I hope, is this visible that I'm making over here? Forget about the question. Forget about the question. Is this visible that I'm making over here? I can see it is perfectly visible. There is no problem in that. Tell me, guys, is this visible properly? Okay. We have to find the magnetic field at point P. First, we draw the perpendicular distance R. Guys, tell me, if whole angle is 60 degree, how much will be half of this? That will be 30 degree. How much will be half of this? That is 30 degree. And I can say, If you join this with one end of the rod, and this will be theta 1 angle. If you join this with another end of the rod, this will be the theta 2 angle, 30, 30. So here, I can say theta 1 is 30. Here I can say theta 2 is. In this case, I'm saying theta 1 and theta 2 both are 30 degrees. Let's find the value of this r also, because r is not given, x is given. We say from the triangle. From the triangle. Which triangle? Let's take any of these triangles. Let's take this triangle. Could you please tell me what is the value of cos 30? Sir, cos is base by hypotenuse. So I can say cos of 30 degree will be base. Base is r. Sir, I think base is this. No, it depends upon the angle. If you are taking this as angle, then this we will consider as base. If you are taking this as angle, then this will be the base. Here, base will be in this case r, and we say hypotenuse in this case will be x. Now multiply it over here. Cos 30 is how much? Root 3 by 2. So this will be root 3 by 2 is equal to r divided by x. So r will come out to be root 3 by 2 into x. This is the value of r. Now guys, if you got the value of r, we say now, what is the formula for the magnetic field because of the wire? We say magnetic field is mu naught I divided by, we say 4 pi r. And then I'll write sine of theta 1, that is sine 30, plus we say sine of 30. Because theta 1 is 30, theta 2 is 30. And I can say in this particular case, this magnetic field will come out to be mu naught. Current is flowing I divided by, we say 2 pi. Instead of r, I can write over here root 3x divided by 2. And sine 30 is 1 by 2 plus we say 1 by 2. 1 by 2 plus 1 by 2 is 1. So 2 1s are, 2 2s are, 2 and 2 will get cancelled out over here. So I can say in this particular case, this is 4 pi r, this is 4 pi r, this is 4 pi r. This is 4 pi. So this is 4 pi. So 2 1s are, 2 2s are 4. So I can say magnetic field will come out to be, that is mu naught I divided by, you see 2 pi root 3. 1 by 2 plus 1 by 2 is 1. So it will come out to be 2 pi root 3, 2 pi root 3 into x. So this will be the value of magnetic field in this. And if you find the direction, place your thumb along the direction of current, curl your fingers at this point, it will be inwards. So magnetic field is inwards. Even if options are visible to you, which option is mu naught I divided by 2 pi root 3x, mu naught I divided by 2 pi root 3x, option 1 is coming out to be the correct option. Is this clear? Is this clear? Tell me guys in the chats, is this clear? Please tell me in the chats if everything is crystalline clear till over here. Tell me guys. Great. Now guys, listen to me very carefully. Listen to me very carefully. See, now we need to find the magnetic field. Now we need to find the magnetic field because of this wire at this point P. And this wire is still from A to B only. Wire is from A to B only, and you have to find the magnetic field at point P. You have to find the point P. Cos came because of this, Cos came because we wanted to find the value of R. In the question, this X was given. That's why we wanted to find the answer in terms of X, not in terms of R. Now see guys. We have to find the magnetic field because of this wire at point P. Okay. Guys, what is the first thing you guys are supposed to do? We say join this point with one end of the rod, that will be over here. And then you say angle between this line and this perpendicular distance r, this you simply call as theta 1. What is the next thing you guys are supposed to do? Join this point with another end of the wire. So you call this angle as theta 2 over here. I can say this is theta. Okay. Now guys, I would want you to tell me one thing. I can say wire is from A to B only, and let's suppose this is C over here. So this is the empty part over here. No wire is present in BC portion. If you find the magnetic field, guys, see, if you write if you write the magnetic field in this case, B is equal to mu naught I divided by 4 pi r, then you are writing the sine of theta 1 plus you are writing sine of theta 2. We said this would be incorrect. Why? Because when you say theta 1 means you are taking the complete wire from here to here, because theta 1 is from this line to this line, that is covering the wire from A to C. So means you are writing the magnetic field of A to C wire. But here in this case, wire is present only from A to B. And then you are writing from B to C, adding this magnetic field plus whole magnetic field. That is incorrect. Guys, what I'm trying to say in this case is, let's suppose if you have a wire over here. And if I'm saying you have to find the magnetic field at r distance, what will you do? You'll say, sir, I'll join this with one end of the rod. I'll join this point with another end of the rod. So I call this as theta 1. I call this as theta 2. So then what will you do is, magnetic field is mu naught I divided by, we say 4 pi r. And then you say sine of theta 1. What does this sine of theta 1 mean? It means all the elements of the rod which come from center to this end. From this, let's suppose this is A, from A to B. So basically, when you are multiplying sine theta 1 over here, you are finding the magnetic field because of this half of the rod. And then when you plus sine of theta 2, when you do this, you are adding the magnetic field because of the rest of the rod, these elements. Same is the case over here. If you are saying magnetic field mu naught I by 4 pi r sine theta 1, you are finding the magnetic field because of AC wire. And then if you say, instead of addition over here, if you do subtraction, sine of theta 2 means now you are subtracting the magnetic field of BC, because theta 2 cover the BC elements. Theta 2 covers this much of the rod. So AC minus BC will give you the magnetic field because of this. So I say here theta 1 covers the AC portion. And theta 2 covers the BC portion. So means theta 1 is giving you the magnetic field because of AC. Theta 2 is giving you the magnetic field because of BC. Please tell me in the chats if this is clear. Guys, let me know in the chats if everything is crystal and clear till over here. Now guys, let's take a look at this question. Find the magnetic field at point B. See, you have got wire 1 over here, which is till infinity. You have got wire 2 over here, which is till infinity. Okay, it is till infinity. And you guys are supposed to find the magnetic field at this point B over here. You guys are supposed to find the magnetic field at this point B over here. At this point B.
Okay, 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 okay. Just a second. I'll make it bit beautiful. So, what we are supposed to find out in this particular case is, we say this distance over here is given as, let's suppose, r, and this is given as r. You are supposed to find the magnetic field at point P. Let's call this point as P. Let's call this point as P. At point P. At point P. Now, guys, see. You have got a wire over here. You have got another wire over here. Don't you think that in this particular case, these two wires which are given over here are semi-infinite? So if you have to find the magnetic field because of these two semi-infinite wires, we say, sure, let's find here in this case, let's suppose this is the direction of the current. This is the direction of the current over here. This is the current flowing, and it goes something like this. Guys, magnetic field because of this wire, place your thumb along the direction of current, curl your fingers. Magnetic field because of this, place your thumb along the direction of current, curl your fingers, it's inward. So magnetic field because of both is inwards. So I can say when it comes to the net magnetic field over here, I can say net magnetic field is 2 times magnetic field due to one wire. You find magnetic field because of any of the wires over here, you will get the net magnetic field. Guys, see, let's find the magnetic field because of this wire, with this wire. What you are supposed to do in this particular case is, you join this point with one end of the rod. That's over here. No, where is that? That is at infinity. So I'll make it something like this. You'll find the magnetic field because of this. And so we say this is the theta 1. Okay. Now you join this point with another end of the rod that is over here. And clearly this will be over here, theta 2. Guys, could you please tell me what is the value of theta 2 in this particular case? That will be 45 degrees. Why? Because total angle is 90 and this angle would be also 45 degrees. This angle is 45. And theta 1 will be 90. Guys, see. What I'm trying to say is that you find the magnetic field because of this wire at r distance. Join this point with one end, that is going till infinity. Join this point with another end. So this will be theta 2, this will be theta 1. So I can say here magnetic field due to one wire. And we say if you consider this one wire as over here, I can say in this particular case, you can clearly say theta 1 will be equal to 90 degrees and theta 2 will be equal to 40. So theta 1 is 90 degrees and theta 2 is 45. Now let's find the magnetic field. So magnetic field will be simply, that is mu naught I divided by 4 pi r. And then I can write sine of theta 1. Sine of theta 1 is 90 plus sine of theta 2 is 45. And I can say in this particular case, this will come out to be mu naught I divided by, we say, 4 pi r. Sine 45 is 1 plus sine 90 is 1, sine 45 is 1 by root 2. Now, this is the magnetic field because of one wire. You guys are supposed to find the magnetic field because of the two wires. Because magnetic field due to this and magnetic field due to this, that will be inverse because of both. So I can say net magnetic field in this case will be, that is 2 times over here, that is mu naught I divided by 4 pi r, and further you can write over here 1 plus 1 by root. Either you can keep it like this also, or you can further simplify it, but this will be the answer. And when it comes to the direction would be inward. Sir, how? Place your thumb along the direction of current, that will be inwards. Place your thumb along the direction of current, curl your fingers, it will go inwards. We say net magnetic field is in. Please tell me in the chats if everything is crystalline clear. Guys, tell me in the chats if you got it. Tell me in the chats if everything is crystalline clear. If everything is crystalline clear.
Great. When I say you guys have to give, when I say you guys give me the signal in the chats, it means that you guys are supposed to give the signal in the chats. Because with that, teacher is able to understand that yes, students are understanding. If there is a student who never put up something in the chat, but at that point of time, it is his responsibility that he has to send the thumbs up or the fire emoji, whatever it may be. Now, guys, let's take a look over here. Let's take a look over here. Find the magnetic field at the center. Find the magnetic field at the center. I would want you guys to do one thing. I would want you guys to do one thing. Let's suppose we have got a structure over here, which is what we call the hexagon. And this hexagon is made of 6 wires. And this hexagon is made of 6 wires. So this is the first wire, second wire, third wire, fourth wire, fifth wire, and sixth wire. And all of these are similar, okay? Equal. The length of these wires are equal. You guys are supposed to tell me what is the net magnetic field at the center. Okay? Okay. Don't you think, guys, if this side is L, this will be L. This will be L. Even in case of the regular hexagon, we say the center from this to the corner, this side is also L. From here to here, this is also L. This is also L. Okay. Now, if I say this is the direction of the current, here 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 this is the direction of the current, this is the direction. Let's find out the magnetic field because of this wire at the center. Let's first talk about the direction. Wait, guys. We say, place your thumb along the direction of current, curl your fingers at this point, it is curling outwards. So magnetic field because of this is outwards. Let's find because of this. So place your thumb along the direction of current, curl your fingers at this point, it is outward. Let's find magnetic field because of this direction. So curl, it will be outwards. Okay. Now, guys, in this particular case, I can say magnetic field will be outwards. This is the direction of the current, magnetic field will be. So because of all the wires, magnetic field at the center is outward. So means I can add the magnetic field because of all the wires over here. I can say, in this case, net magnetic field will be simply, that is 6 times magnetic field due to 1 wire. 6 times magnetic field due to 1 wire. If you find out the magnetic field because of 1 wire, and if you multiply it with the 6, you will get the net magnetic field. Let's find the magnetic field because of this one. So we say magnetic field due to 1 wire. Due to 1 wire. Guys, let's talk about this wire. In this particular case, we say join this point with one end of the rod. This is what we call the theta 1 over here. Okay. And this is what we call theta 1. Join this point with another end of the wire, and this is what we call the theta 2 over here. And I can clearly say here, theta 1 is equal to 30 degrees. In this case, in the regular hexagon, we take it 30 degrees. No, not 45, it is 30. And we say theta 2 will be also, that is 30 degrees. That is 30 degrees. Yes. Let's find this R also. Guys. We say from this triangle, we say, already we did this question. So we say from the triangle, could you please tell me what is the value of cos 30? So I can say cos of this theta 1 or cos of 30. That is base by hypotenuse. That will be equal to R divided by L. Now take it over there. So cos 30 is root 3 by 2. This is root 3 by 2 is equal to R by L. So can I write this R will come out to be in this case? That will be simply, that is a root 3 by 2 into L. So we got the value of R over here. Now I would want you to put up this in the main equation. What is that as? What is the formula? That's what we need to use. So we say that is D is equal to mu naught I divided by 4 pi R. And then I can say over here sine of theta 1 plus I can say over here sine. And here I can write B is equal to mu naught I divided by 4 pi. What is the value? What is the value of r in this case? Guys, what is the value of r in this case? We got as that is a root 3 L divided by 2. And sine theta 1 is 30, theta 2 is 30. So that will be 1 by 2. Sine 30 is 1 by 2 plus I'll write 1 by 2. Sine 30 plus sine 30. Now, 2 ones are 2 twos are 4. So magnetic field will come out to be that is mu naught I divided by, we say 2 pi root 3 into. So this is the magnetic field because of one wire. You want to find magnetic field because of these 6 wires. So I can say net magnetic field in this case will be 6 times magnetic field due to one wire. That is mu naught I divided by, we say 2 pi root 3 into L. So now 2 ones are 2 threes are 6. So this will come out to be 3 times mu naught I divided by, we say root 3 pi into. Okay. Okay. So you can basically keep it like this also, or you can rationalize it also. So I can say in this particular case, because in case of the regular hexagon, we take this total angle as 60 degrees. So this will be 30, this will be 30. Similarly, here also, this will be 60. Okay, it becomes an equilateral triangle. And what is the direction? Direction is outward. Is this clear? I would want you guys to tell me in the chats. Is this clear? Is this clear to each and every single student? Great, great, great. Now, guys, let's suppose you have got a question something like this. You have a wire over here. In this wire, current I is flowing. And you are supposed to find the magnetic field at point P such that this point P lies on the same line of the wire. Point P lies on the same line of the wire. It is along the wire. We say here, point P lies on the axis of the wire, on the axis of the wire, or along the wire, axis of the wire. So in this case, point P lies on the axis of the wire or along the wire. And in this particular case, we say magnetic field at point P will be 0. Why? Because we see. You say, guys, you say magnetic field is mu naught I divided by 4 pi r. Then you say sine of theta 1 plus sine of theta 2. How do you define theta 1 and theta 2 in this case? You say, sir, you join this point with one end of the rod and theta 1 will be 0 degrees over here. Why? Because between this r distance and this wire, this line, it is 0. Now join this point with another end of the rod. So between this r and this wire, again theta is 0. So sine 0, 0, this whole magnetic field will come out to be 0. Or we simply say we cannot define the perpendicular distance over here. Okay? So magnetic field, whenever from now onwards, you see a point which is along the wire, you say magnetic field because of that will be 0. Even if you see it something like this, this is the wire in which current is flowing. I say, what is the magnetic field at this r distance over here? You simply say, here also magnetic field is 0 because of this wire. Why? Because the line is along this wire, because the line is along this wire, because the point is along this wire. Guys, is this clear? Please tell me in the chats. Please tell me in the chats. Hajan Nagar, you are confused in every question. I don't know why. I would suggest you to watch it later on once again at 2x. So if the point lies on the axis of the wire, in that case, we consider the magnetic field 0 at that point. As simple. Now, guys, let's suppose you have a question something like this. You have got this semi-infinite wire over here. You have got this semi-infinite wire over here. Current is flowing something like this. You are supposed to find the magnetic field at point P. Guys, don't you think that because of wire 1, magnetic field at point P is 0? Why? Why? We say, if you join this point with this wire, it will lie on its axis. I can say magnetic field due to wire 1 is 0. And when it comes to the wire 2, guys, we say this point, join this point with one end of the rod, theta 1 is equal to 0. Join this point with another end of the rod, that is at infinity. So means for this wire 2, this point will behave. For this point, this wire will behave like a semi-infinite wire. So we say magnetic field due to wire 2. How much will be that? One angle is 0 degrees. Another angle is 90 degrees. So I can say that will be B2 will come out to be, that is mu naught I divided by 4 pi. Why? Because magnetic field because of an semi-infinite wire is mu naught I by 4 pi. Guys, if you join this point with one end of the wire, we are talking about wire 2, theta 1 will be 0. If you join this with another end of the wire, that is at infinity, so theta 2 will be 90. So 0 and 90, when you have the angles, in that case, magnetic field is mu naught I by 4 pi. Let's find the direction. Place your thumb along the direction of current. Curl your fingers at this point. It will be outwards. So here magnetic field is outward. Here magnetic field is out. I hope this is clear. I hope this is clear. Okay. Next. Let's talk about this one. Even I'll make it something like this. See, guys, wait. See. Okay. Here in this wire, current I is flowing and then current I is coming out. You guys are supposed to tell me what is the net magnetic field at the center. What is the net magnetic field at the center in this particular case? What is the net magnetic field at the center in this? Let's suppose this side is L. This side is given as L. Guys, you guys are supposed to tell me what is the net magnetic field at the center because of this structure. Find the net magnetic field at the center because of this structure. Guys. See. In this case, we say this structure is made of total how many wires? We say 6. This is 1. This is 2. This wire is 3. This wire is 4. This wire is 5. And this wire is 6. If you talk about the center point, don't you think that for this center point, we say this point lies along the axis of wire 1 and axis of wire 6. We say center point lies on the axis of wire 1 and axis of wire 6. So magnetic field because of one wire, magnetic field because of 6 at the center will be 0. So magnetic field due to 1 will be magnetic field due to 6, that will be equal to 0. Do you believe that? Yes. Now what is remaining over here? Remaining is the square loop. So we say remaining is the square loop. Remaining is the square loop. Now what is the magnetic field because of the square loop? So I can say magnetic field due to a square loop is how much? I have recently told you magnetic field because of a square loop is 2 root 2 mu naught I divided by we say pi into. This is the magnetic field because of the square loop at the center. And what is the direction? Place your thumb along the direction of current, it is inwards. Because of this also it is inwards. Because of this also it is inwards. So I can say this is cross over here, that is in. So it is cross over here, that is inwards. Next. Let's talk about this one. Find the net magnetic field at the center. Guys, see. This structure is also made of 1, 2, 3, 4, 5, and 6 wires. When it comes to the center, we say this center lies along the axis of this first wire. And this center lies along the axis of this fourth wire. So I can say magnetic field due to 1 is equal to magnetic field due to 4, it will be 0. It will be 0. Now, what about this one? Guys, see. Magnetic field because of 2 and 3. Listen to me very carefully. Magnetic field because of 2 at the center will be inwards. Magnetic field because of 3 at the center will be what? Inwards. And magnitude will be same. We say magnetic field due to 2 and magnetic field due to 3 is inwards. Tell me one thing. Let's talk about, see, this is 2I current coming. I is going in this direction, I is going in this direction. Now, if we talk about the magnetic field because of 6, place your thumb along direction of current, curl your fingers, it is pointing outwards. Because of this wire, place your thumb along the direction of current, curl your fingers, it's pointing outwards. And we say magnetic field because of 6 and magnetic field because of 5 is outward. So, magnetic field because of these two will cancel out with the magnetic field because of 5 and 6. So, they will cancel out each other. They will cancel out each other. So, if they cancel out each other, we say net magnetic field will come out to be. Then net magnetic field will come out to be. Is this crystalline clear to each and every single thing? Yes, magnitude will be also same because this wire is similar to this wire. Okay, so length, distance from here to here is equal to distance from here to here. Magnetic field of this will cancel with the magnetic field of this. Magnetic field of this will cancel with the magnetic field of this. Now guys, next we have this one. Magnetic field on the axis of a circular current carrying loop. Magnetic field on the axis of a circular current carrying loop. We are done with all of the straight wires. I have shown you enough number of questions when it comes to the straight wire, infinite wire, semi-infinite wire. Okay. Now guys, magnetic field on the axis of a circular current carrying loop. Let's suppose I have got a loop over here in which current I is flowing. So what is this loop? Loop means the closed coil, a circular coil in which current is flowing. So we say you have to find the magnetic field because of this at x distance. I'll write over here. Since the current is flowing, in the loop, so it will create, so it produces the magnetic field. So it produces the magnetic field, that is B. And then the next point I'll mention over here, to find the magnetic field at x distance, We are supposed to find the magnetic field at x distance. We are supposed to find the magnetic field at x distance. Now guys, when it comes to this, previously, if you remember, we had a ring something like this, and charge was distributed on the ring. And I asked you to tell me what is the magnetic field at x distance. You said, sir, it is kqx upon r square, x square plus r square whole raised power 3 by 2. But when it comes to the magnetic field over here, we say this magnetic field will be, that is mu naught I into r square divided by, we say 2 into r square plus x square whole raised power 3 by 2. This is the magnetic field because of this ring at the x distance. Because of this ring at the x distance. This is the magnetic field because of this ring at the x distance. Oh, what is mu naught? Permeability of free space. What is this I? I is the current flowing in the loop. And what is this R? R is the radius of the loop, capital R. And what is this X? X is the distance at which you guys are supposed to find out the magnetic field. So we say this is the magnetic field because of it is like this. It is like this. This is a coil. This is a current carrying wire. And you guys are supposed to tell me at this point, magnetic field. Now see guys. This is the magnetic field at x distance. We say this is the magnetic field at x distance. If I ask you what is the magnetic field at center, guys, as you move away from the center, x will increase. And as you move towards the center, we say x will decrease. And exactly at the center, I can say the value of x is 0. So we can say over here at center, we say value of x is 0. Now, if I put x is equal to 0, let's find out the magnetic field at the center. So magnetic field will come out to be, this is the general formula, that is mu naught I into, we say r square, then we say upon, we say 2 into r square plus x square, x will be 0. So I'll write over here whole raised power 3 by 2. Now this 2 and 2 will cancel over here. So I can say in this particular case, this magnetic field will come out to be, that is mu naught I into r square divided by, so this will be 2 times of r cube. Now tell me one thing, this r square and this cube will cancel out over here. So I can say magnetic field comes out to be, so it will be mu naught I divided by, we say, this is the magnetic field that you have got over here. This is the magnetic field that you have. Okay, this is the magnetic field that you have. Okay, this is the magnetic field at the center of the ring, Now guys, you have two cases in this case. The case one. I'll write over here case one. Case one is very close to the ring. And in this case, we say x is much less than capital R. Guys, what I'm trying to say is that, see, I'll make you understand. What I'm trying to say is that you have got a ring over here. Okay. The radius of the ring is, let's suppose I'm saying the radius of the ring is, let's suppose R, capital R. Okay. The radius of the ring is capital R. I'm asking you to tell me the magnetic field because of this ring in which current I is flowing. At what distance? We say at very close distance, very close to the ring. Means if this is the ring just outside of the center, not far from the ring, not exactly at the center, just outside of the ring at very minute distance, such that here this R is very greater than, we say this R is much greater than x, or x is much less than R. In such cases, we have to find the magnetic field. We say magnetic field will be mu naught I into r square upon 2 times of r square plus x square whole raised power 3 by 2. This is the general formula. Guys, see. If I say I have got a very small quantity, that is x over here, and it is added to a very large quantity, we say it will not create any difference. It's like
You are adding a bucket of water to the ocean. Ocean has got the billions of liters of water. If you add a bucket of water to the ocean, it will not create any difference. So adding a very small quantity to a very large quantity will not create any difference. So X is bucket of water, R is ocean. It will not create. So I'll ignore this X. So I can say this magnetic field will be mu naught I into R square upon, we say 2 into R square whole raised power 3 by 2. This 2 and 2 will cancel. So magnetic field again will come out to be mu naught I into R square divided by 2R cube. And this cube will cancel. So magnetic field will come out to be mu naught I divided by 2. Guys, whatever is the magnetic field exactly at the center, same is just outside of the center. Same is just outside of the center. And if you clearly see, current is constant, mu naught is constant, radius of the ring is constant. We said 2 is constant, so the whole magnetic field will be constant. Now, the second case in this one we discuss is, we say case 2. Case 2. That case is what we discuss is very far from the ring. Far from the ring. Very far from the ring. And in this case, we say R is much less than X. R is much. What I'm trying to say is that, let's suppose I'll make this diagram over here. Let's suppose this is the ring. This is the ring. Okay. And this is the radius of the ring over here. And I'm saying that you have to tell me the magnetic field very far from the ring. Far from the ring means this is X and this is. Can I say in this particular case, we say X is much greater than R? Yes. So use the general formula. The magnetic field will be, that is mu naught I to R square divided by 2 times of R square plus X square whole raised power 3. Then you can write further you can write over here. This magnetic field will come out to be mu naught I into R square and divided by 2 times of. Guys, if R is if R is very small, so you can ignore R. Adding a very small quantity to the very large quantity will not create any difference. So I can ignore this R over here. So I can write X square whole raised power 3 by 2. Again, this 2 and this 2 will cancel. So this will come out to be mu naught I into R square upon, we say 2 times of X. So here I'll write B is equal to mu naught I into R square divided by 2 times of. And here B is inversely proportional to, we say, X cube. Where B is inversely proportional to X cube. So this is the magnetic field because of a ring at very far distance. This is the magnetic field because of a ring at very close distance. And one more thing is, if somebody asks you to plot the graph between B versus R, if somebody asks you to plot the graph between B versus R, magnetic field versus R, you can simply say this will be the magnetic field and this is magnetic field versus X, sorry. So, guys, when it comes to the center, magnetic field is constant because here at center we say X is equal to 0. Value of magnetic field exactly at the center is mu naught I by 2R and it's constant and it is constant. Okay. And same is very close to the ring. Same is very close to the ring. So at exactly center, magnetic field is constant. So I can say B is constant. And when you move away from the ring, magnetic field will decrease. So we can say B is inversely proportional to X square. It is very far, at very far distance, and this is very close. Please tell me in the chats. If everything is crystalline clear. Guys, tell me in the chats if everything is crystalline. Give me the signal in the chats. And smash the like button, guys, if you have not liked the session yet. I would want you to smash it as soon as possible. Now, guys, let's take a look at this question which we have over here. It says that find the magnetic field at distance x is equal to root 3r due to a circular wire of radius r given, it is given over here. The magnetic field at the center is B naught. So we are supposed to find the magnetic field because of this ring at what distance? Root 3r distance. So x in this case is given as, that is a root 3r distance. Okay, yes. Now guys, we say at x is equal to root 3r. We know the magnetic field because of the ring. We know the general formula. We say as. When it comes to the magnetic field, it is mu naught I into r square upon 2 into, we say r square plus x square whole raised power 3 by 2. Absolutely clear, sir. Now tell me, I can write over here B is equal to mu naught I into r square divided by. So I'll write over here 2 into, and this will be r square plus. What is the value of x over here? That is root 3r square. Now guys, if you are saying root 3r square, so this square and root will cancel, so this will become 3r square. So this is 3r square and then whole raised power 3 by 2. Yes. Next step, if I just write over here, I can say magnetic field will come out to be, and that is mu naught I divided by r square. And then over here, 3r square plus r square will become 4r square. So 2 into, we say 4r square whole raised power 3 by 2. 4r square whole raised power 3 by 2. Guys, I would want you guys to look over here. See. Can I write it something like this? This is 4r square whole raised power 3 by 2. I'll write 4r square whole raised power 3 by 2. Can I do a bit more calculation over here? I'll write it. This is 4r square whole raised power 1 by 2 multiplied by 3. It's one and the same thing because 3 into 1 becomes 3 by 2 once again. Now. What does this mean? 4r square whole raised power 1 by 2. We say the value of root is 1 by 2. So if it is 1 by 2 in power, it means it is root. So 4 root, I can write it something like this. 4r square, it means root. Because of 1 by 2, I'll write root, whole cube. And then I can write over here, this guys, 4 root is, we say 2 square, and this will cancel 2r, and it is whole cube. Now 2 cube is 8, r cube is r cube. So instead of all of this, I'll write 8r cube. So this magnetic field will come out to be mu naught I into r square upon, we say 2 into, will be how much? That is 8r. Guys, this square and this cube will cancel. So I can write in this particular case, this you can write separately, okay? Keep this thing separate over here. Then you can say in this particular case, this magnetic field will come out to be, that is mu naught I divided
Check, check. Am I audible now? Am I audible now? Am I audible now, guys? Okay, great, great, great. So I can say in this particular case, this is mu naught I divided by 2r. Instead of mu naught I divided by 2r, this is the magnetic field at the center. Am I audible? I guess I'm audible now. Why are you saying not audible? So I say mu naught I by 2r is the magnetic field because of the ring at the center. So that is given over here B naught. So instead of this, I'm writing B naught divided by 8. Next. Now, guys, take a look over here. Find the magnetic field due to a segment of the ring. Guys, first and the foremost thing is, if you remember the chapter electrostatics, over there, I made you understand one thing, that is the segment of the ring or the arc. See, let's suppose we have got a ring over here. This is what we call the complete ring or the complete circle. Audio is not clear. Audio is not clear. I made you understand one thing, that is the segment of the. Let's suppose we have got a ring. Here's what this happens sometimes. Just a Is it fine now? Is it fine now, ladies and gentlemen? Ladies and gentlemen. Great. Now take a look over here. No, battery is not dead. Yeah, it's fine. See. We say this is the complete ring that we have exactly over here. Okay. Now, guys, if I want you to cut this ring in two parts, so you can cut it something like this. So this is what we call this semicircular ring. This is the semicircular ring. If I want you guys to cut this in 4 parts, so we say you'll cut it something like this. So we say this is chord, 4 chords. Now, if I say you cut some part of the ring, cut it from here to here, this is what we call the segment of the ring. Some part of the ring. It's not the complete ring, it's not the chord, it's some part of the ring. So I can say from here to here, this is the radius. From here to here, this is also the radius. Okay. Now, if I take this segment of ring over here and if I place it over here, and now current flowing in this part is, we say, I. Now, guys, you have to find the magnetic field at point P. We say to find the magnetic field at point P, due to an arc. Now, I would want you guys to join this point with one end of the ring. Join this point with another end of the ring. Now, angle between these two is what we call the theta. Now, magnetic field because of this segment of the ring at this point will be, that is B is equal to, that is mu naught I divided by 2r. Then we say theta divided by 2 pi. I is the current flowing in the ring. R is the radius of the ring from here to here. Theta is the angle between these two, this radius and this radius. So this will be the magnetic field exactly because of this segment of ring at point P. This is the magnetic field because of the ring because of the segment of the ring at point P. Now guys, let's find out the direction also. When it comes to the direction, in case of the straight wire, what do we actually do is we place the thumb along the direction of current, then curl our fingers. But right now, here, we say curl your fingers along the direction of current. Guys, here, these are your fingers. It is just the opposite of the previous one. Over there, we used to place the thumb along the direction of current and then curl our fingers. But right now, I say curl your fingers along the direction of current. So this is the direction of current, curl your finger, curl your finger. So check where the thumb is pointing. Thumb is pointing outwards. So that will be the direction of magnetic. That will be the direction of magnetic field. So I'll just write over here. We say curl your fingers along the direction, curl your fingers along the direction of current. Then thumb gives the direction, and thumb gives the direction of magnetic field. Then we say thumb gives the direction of the magnetic field. And here it is, we can say it is outwards. Here it is outward. Here it is outward. Next. Let's suppose if I say this is the arc over here. And in this arc, if I say direction of current is this, what will be the direction of magnetic field at this point? What will you do? Curl your fingers along the direction of current. Thumb is pointing inwards. So here magnetic field will be inwards. Magnetic field will be inward. Let's talk about the semicircle. Guys. If you take a complete semicircular wire over here, don't you think that you have to find the magnetic field at this point P? Okay. So we say to find the magnetic field at point P. Can I say in this particular case, I would want you to understand one thing. Guys, see, we say join this point with one end of the wire, and this is what we call R. Join this point with another end of the wire. This is what we call the R. And angle between these two is what we call the theta. This is how we define the theta in this case. And clearly, between this R and this R, you can say the theta here is 180 degrees. 180 degrees in radians means pi radians. In degrees, we call it the 180 degrees, and in radians, you call it the pi radians. Now, you will have the general formula, that is, this is the general formula that we need to use to find the magnetic field. So I can say, I'll use the general formula, magnetic field will be mu naught I divided by 2R. Then we say theta divided by 2 pi. So I can say this magnetic field will be mu naught I divided by 2R. Instead of theta, I can write pi divided by over here pi. This and this will cancel. 2 into 2 becomes 4. So magnetic field will be mu naught I divided by, we say, 4R. Magnetic field is mu naught I by 4R. Even in case of the complete circle also, you say, guys, let's suppose in case of the complete circle, you are starting from this point. So then, so another point, we say here in case of the complete circle, what is the value of theta? That is 360 degrees. So you say theta is equal to 360 degrees, and that is 2 pi. Guys, we have to find the magnetic field because of the complete circle at the center. We have already calculated this, mu naught I by 2R. See, here we got it, mu naught I by 2R. Mu naught I by 2R, magnetic field because of the complete ring at its center, mu naught I by 2R. Let's check if we are getting the same result by using this formula. So I can say B is equal to mu naught I divided by 2R, theta divided by 2 pi. Instead of theta, I'll write 2 pi over here. B is equal to mu naught I divided by 2R, 2 pi divided by 2 pi. This and this will cancel. So magnetic field will come out to be mu naught I divided by 2R. And how do you find the direction? Curl your fingers along direction of current. Thumb is pointing outwards, so it is outwards. Next, because of the chord. Guys, clearly you can see over here, if you join this point with one end of the chord, if you join this point with another end of the chord, we say theta here is coming out to be 90 degrees. Theta is coming out to be 90 degrees. So we can say magnetic field is mu naught I divided by 2r, theta by 2 pi. Theta is 90 degrees means you can also say it is pi by 2 radians. Either you call it the 90 degrees or you call it the pi by 2, that's one and the same. And I can say over here, this will be, instead of theta, I'll write pi by 2 and then we say 2 pi. Because it is theta divided by 2 pi. So I can say this pi and pi will cancel. So magnetic field will come out to be mu naught I divided by 2 into 2 into 2 is say 8r. So this is the magnetic field because of the chord at its center, mu naught I by 8r. Because of the semicircle, it is mu naught I by 4r. Is this clear? Give me the signal in the chats, guys. We have a question over here in front of you. Tell me in the chats if this is crystalline clear. Direction will be same. Curl your fingers along the direction of current. Thumb will give you the direction of magnetic. Okay. Tell me. We'll take the break exactly at 8 o'clock. We have to find the net magnetic field at O. See guys. If you take a look at this structure, we said this structure is made of a chord, a straight wire, a semicircle, a straight wire, another chord, another straight wire. Okay. Now, in this case, we say, let's call this as 1. Let's call this as wire 2. Let's call this as wire 3, wire 4, wire 5, and wire 6. We have to find the net magnetic field because of all of this at the center. Tell me one thing. Don't you think that, sir, this center point is along this wire 2? It lies on the axis of the wire 2. The center point lies along the axis of the wire 6. The center point lies along the axis of the wire 4. So I can say magnetic field due to 2 will be equal to magnetic field due to 6 will be equal to magnetic field due to 4. That will be 0. Because center is along, we say wire, which one? 2, 6, 4. Center is along wire 2, 6, and 4. 2, 6, and 4. Now see, we say magnetic field will be because of this chord, bigger chord, which has got the radius of 4r. Magnetic field will be because of this semicircle, which has got the radius of how much? 2r. And magnetic field will be because of this chord, which has got the radius of r over here. Now guys, tell me one thing. Can I say as net magnetic field over here will be magnetic field because of 1 plus magnetic field because of 3 plus magnetic field because of 5, this chord. And most importantly, guys, let's find the direction first. Why am I adding? Because the direction is same. Curl your fingers along the direction of current, thumb is outwards. Now, because of this magnetic field, let's check. Curl your fingers along the direction of current, thumb is pointing outwards. Because of this, curl your fingers along direction of current, thumb is pointing outwards. So because of all of these, magnetic field at the center is outwards. Now see, magnetic field due to 1, this is a chord. Because of the chord, we recently got the magnetic field as mu naught I by 8r, where r is the radius. So here I can write mu naught I divided by 8r. But right now I can see over here this r, radius of this is given as 4r. So instead of this, I'll write 4r. Okay? And then I say plus magnetic field because of the semicircle. So that is mu naught I divided by 4r. But right now, the radius of this semicircle is given as 2r. So instead of r, I'll write 2r. Then this chord, because of the chord, it is mu naught I divided by, we say, 8r only, because it has got the radius of r only. Okay. Now it becomes mu naught I divided by 8 fours are, that is 32r, plus 4 twos are 8, mu naught I divided by 8r, plus mu naught I divided by 8r. Is this clear? Please tell me in the chats, everyone out there. Is this clear? Please tell me in the chats, everyone out there. Okay. Now you can write this 2 times also. Further also you can simplify. So B net will come out to be, this is mu naught I divided by, we say, 32r, plus this is 2 times mu naught I divided by, we say, 8r. And here it is 2 ones are 2 twos are 2 fours are 8. Okay. And what you can take common is mu naught I divided by r. And here it is 1 by 32 plus, we say, 1 by 4. Plus 1, we say 1 by 4. So this will be net. You can do the cross also. So this is the net magnetic field over here. Okay. Okay. Is this clear? Please tell me in the chats. Please tell me in the chats. And direction would be outwards. Guys, give me the signal in the chats if everything is crystalline clear. Next. This was the question asked in NEET 2018. And it says that, I hope this is visible. I hope this is visible. I'm not sure if this is visible or not. I'm not sure if this is visible or not. Yes. Charge Q is uniformly, it says that charge Q is uniformly separate on a thin ring of radius r. It says that we have got a thin ring over here. We have got a thin ring over here. This is a thin ring. And charge Q is present on this thin ring. And the radius of this ring is given as r. The ring rotates about its axis. The ring rotates about its axis. It is rotating something like this with a frequency of f. Frequency is given as f. The magnitude of magnetic induction at the center. We have to find the magnetic field at the center. Guys, see. We say here the ring rotates, which has Q charge on it. If Q charge is present on the ring and this ring is rotating, don't you think that charge is also rotating? So whenever the charge rotates, moves, it will produce the current. So current is produced. Current is produced. Guys, if current is produced in the ring, don't you think that it will create the magnetic field? So it creates magnetic field at the center. If it creates the magnetic field at the center, what is the value of magnetic field at the center? B is equal to mu naught I divided by, we say, 2r. We recently got magnetic field because of a center. In case of a ring is mu naught I by 2r. Now tell me one thing. Here, charge is not given but current is given. Sorry, current is not given but charge is given. We say as. We say current is charge upon time, Q divided by T. We say current is charge upon time, Q divided by T. So Q divided by T. And we know that when it comes to the frequency and time period, we say this time period is inverse of frequency, as time period is inverse of frequency. So I can write this current will come out to be, that is Q upon 1 upon frequency. Take this in the numerator, it will become Q into F. Now you got the current as Q into F, put in equation first. I say put in equation first. I would want you guys to put in equation first. So I can say this magnetic field will come out to be. So it is mu naught. Instead of this current, I can write over here that is Q into F divided by, and over here it will be 2R. It is 2. So I guess option 1 is matching over here. I guess option 1 is matching. This is the magnetic field in terms of charge and frequency. Now guys, take a look at this question. Take a look at this question. Find the magnetic field at the center. You guys are supposed to tell me what is the magnetic field at the center. You have got this ring over here. You have got a second semicircular ring. Smaller one, bigger one. Guys, tell me one thing. Tell me one thing. If I talk about this entire structure, we say it is made of 1, 2, 3, and 4 parts. These are the straight wires. Here, if the direction of the current is this, so this will be the direction of current. This will be the direction. Now, when it comes to the center, we say this point lies on the axis of this wire. This point lies on the axis of this wire. So I can say magnetic field due to 2 is equal to magnetic field due to 4 will be equal to 0. Why? Because center point lies on the axis of 2 and 4. That's why we are saying 0. So I can say net magnetic field in this case will be simply, that is because of this third wire, that is B3, and because of this wire, that is B2. Because of this and because of this. Now tell me one thing, guys. Tell me one thing, guys. See. If I say magnetic field because of this wire at the center, how do you find it? Curl your fingers along the direction of current, thumb is pointing inwards. So magnetic field because of this will be inwards. So I say this is B1. I'll write over here that is B1 is okay. This B1 will be inwards. I'll write it cross. Let's find the magnetic field because of this. Curl your fingers along the direction of current, thumb is pointing outwards. So I can say magnetic field because of this B3, it is outwards. So B1 minus B3. Why am I subtracting over here? Because the magnetic fields are in the opposite direction, inward and outward. That's why I'm subtracting. Now the question is, sir, why did you subtract B1 minus B3? Why did you not do it like B3 minus B1? We say because B1 is greater than B3. Why, sir? See, guys, how do you find the magnetic field because of a semicircular ring? B is equal to mu naught I divided by 4R. Magnetic field and R, it is inversely proportional. So this is having the radius R. Its radius is less. If R is less, magnetic field will be more. This bigger one has the magnet radius 2R. So if radius increases, magnetic field will decrease. So that's why B1 will be more, B2 will be less. Now I can write over here, net magnetic field will be, because of this smaller one, how much is the magnetic field? Mu naught I divided by over here 4R. Instead of R, I can write this will be 4 into this small r is given, I'll take small r only. And then my dear friends, if you talk about the bigger one, minus mu naught I divided by 4R. Because this is also the semicircle, because of a semicircle it is mu naught I by 4R. Now my dear friends, instead of R, I can write over here 2R because the radius of the bigger one is 2R. So I can write over here 2R. So net magnetic field will come out to be, that is mu naught I divided by 4R minus 4 into 2 is 8. This is mu naught I divided by, we say 8R. Now guys, it is 1 by 4 minus 1 by 8. It will come out to be 1 by 8. Don't say it will be 1 by 4. No, it is 1 by 4 minus 1 by 8. I can say over here net magnetic field will come out to be, that is mu naught I divided by, we say 8. And direction is inwards. Why? Because we consider the direction of bigger vector will be the direction of net. Is that clear? Is that clear? Please tell me in the chats.
Tell me in the chats if it is crystalline clear to each and every single. I see. In this case, this is the direction of the current, and here this current will flow something like this. And this structure is made of 1, 2, 3, and 4. You guys are supposed to tell me what is the net magnetic field at the center. What is the net magnetic field at the center? Guys, clearly here also magnetic field because of 2 and 4 will be 0. Magnetic field because of 2 is equal to magnetic field because of 4, it is 0. Why? Because the center point lies on the axis of these two wires. Then comes this bigger wire and you have got this wire. See guys, let's find out the magnetic field because of this. Let's find the direction. Curl your fingers along the direction of current. Thumb is pointing inwards. Because of this, magnetic field at the center is inward. Let's find the magnetic field because of this. We say curl your fingers along the direction of current. Thumb is pointing inward. So magnetic field because of this at the center will be inwards. Magnetic field because of this at the center is inwards. Magnetic field because of this at the center is inwards. So are we supposed to add or subtract? Please tell me in the chats. Are we supposed to add or subtract? Add or subtract? Please tell me in the chats. B1 plus B3 or B1 minus B3? B1 plus B3 or B1 minus B3? Why is that guy writing subtract? Vijay. No, add. Magnetic field because of this is inwards. Magnetic field because of this is inwards. So I can say simply that is B1 plus B3 because this is inwards, this is inwards. If the two vectors are in the same direction, we add. If they are opposite, we subtract. Now tell me. This is a semicircular wire which has got the radius 2r. So I can say in this case, magnetic field will be mu naught I divided by 4r. Now r in this case will be 2r. Then plus. In this case, magnetic field because of this will be how much? That is mu naught I divided by, we say 4r. Because of the semicircular wire, it is mu naught I by 4r. So here r is 2r, that's why I mentioned 2r. So I can say in this particular case, this will be mu naught I divided by, this is 8r plus mu naught I divided by, we say 4r. 8r plus. And what will be the direction? Direction will be the inverse. Please tell me in the chats if everything is clear till over. Okay. So finally, if you, it will be basically mu naught I divided by r, and what will you take common? This is 1 by 8 plus 1 by 4. If you do it, so net will come out to be, that is 3 by 8. Do the cross multiply, it will be 3 by 8 mu naught I divided by, and direction will be inward. Direction will be inward. Direction will be inward. Tell me the answer of this question, guys. Tell me the answer of this question, guys. The figure below shows the current loop having the circular arcs. Okay, I'll make it over here. I'll make it over here. Don't cry. Please don't cry in the chats. I'll make it over here. You have got an arc. You have got one more arc. I've got one more arc. Okay. And it is something like this. It is something like this. And there is a point over here. There is a point over here. From here till here. From
here till here. And in this particular case, it says that current flowing in this is I, and then it goes over here as I. And this is given from here to here. The radius of the smaller arc is given as A, and the radius of the bigger arc is as, we say, sir, B. B. You are supposed to find the net magnetic field at O. Guys. And this angle in this particular case is given as theta. The structure is something like this. This is the structure. Current is flowing in the structure. You are supposed to tell me what is the net magnetic field at O because of this structure. See, guys. Is this a semicircle? No, sir. Is this a chord? No, sir. Is this a complete circle? No, sir. Is this an arc or the segment of the ring? Yes, sir. So in this particular case, I would want you guys to use the formula that is the segment of the ring. That is the segment of the ring. We say, here, let's call this as 1 and let's call this as 2. Because of this wire and this wire, magnetic field at the center will be 0. Why? Because this point lies on the axis of this wire. This point lies on the axis of this wire. Now, tell me one thing. Magnetic field because of this arc at this point will be in which direction? Curl your fingers along the direction of current. Thumb is pointing inwards. Because of this, it is inward. Okay. Now, magnetic field because of this, curl your fingers along direction of current, thumb is pointing outwards. So I can say when it comes to the net magnetic field over here, that will be magnetic field because of this, that is B2. Magnetic field because of this, that is B1. Because of this. And direction because of this is curl your fingers along the direction of current, thumb is pointing outwards. So this is outwards. Because of this, magnetic field is inwards. If they are in the opposite direction, we are supposed to subtract these two. That is B2 minus B1. That is B2 minus B1. Okay. Now. Sir, magnetic field because of B2 will be greater. So we say B2 is greater than B1. Why, sir? Because this radius is less. So we say because A is less than B. If radius is less, we say magnetic field because of that wire will be more, because I have told you this previously. Now tell me one thing. Since this is an arc and this is an arc, use the formula for the arc. So I can say net magnetic field in this case will come out to be, that is magnetic field because of the second arc. That is mu naught I divided by 2r. Guys, what is the magnetic field because of the arc? B is equal to mu naught I divided by 2r, theta divided by 2 pi. So I can say because of this arc, it will be mu naught I by 2r. What is the radius of this arc? That is 2a. Theta by 2 pi. Theta is given as theta divided by, we say, 2 pi. Then we say minus magnetic field because of this bigger arc. So that is mu naught I divided by 2b. Because r over here is, for this bigger arc, it is b. And then I can write over here, this is theta divided by 2 pi. I would want you guys to take out common what? Mu naught I by 2 theta divided by 2 pi. This we can take common over here. So I can say net magnetic field is mu naught I divided by 2 into 2 is 4 pi. Mu naught I divided by 4 pi. And then here it remains 1 by A upon 1 by B. 1 by A, okay, theta also. Then it remains 1 by A minus 1 by B. So we can write it as mu naught I theta divided by 4 pi. Now this is B minus A upon A into B. I guess this will come out to be the net magnetic field in this case. Mu naught I theta divided by 4 pi B minus A, just a second, B minus A upon A minus B. I guess option second is matching. Option second is matching. Okay. Okay, great. Let's move on to the next one. Let's move on to the next one. This question we have over here. This question we have over here. See, guys, in this case, you have got a semi-infinite wire. You have got a semi-infinite wire. And there is this ring over here. This is not the complete ring, because these are the three parts of the ring. If you join this chord also, it will become the complete ring. So one chord, second chord, third chord, three chords. Okay? And this is we have over here. Guys. In this particular case, if you check the magnetic field at point O, see. We say magnetic field because of this semi-infinite wire at the center will be 0. Why? Because this point lies along the axis of the wire. So I'll first write this point only. We say magnetic field due to 1 is equal to 0, because point O lies on its axis. Then when it comes to the net magnetic field, guys, net magnetic field will be because of this third part of the wire and the second part of the wire. Tell me one thing. What is the direction of magnetic field because of this wire? Curl your fingers along direction of current, thumb is pointing inwards. So magnetic field because of this is inwards. And then we have why it is 0, because this point lies on the axis of this wire. It is along this wire. That's why magnetic field because of first is 0. Magnetic field because of this wire at the center. Guys, current is flowing in this direction. Place your thumb along the direction of current. Curl your fingers at this point, it is inwards. So magnetic field because of this is inwards. Magnetic field because of this is inwards. So we say we are supposed to add. So I can say magnetic field due to 3 plus magnetic field due to 2. This is inwards. This is also inwards. Now guys, tell me, how to find the magnetic field because of this? It is not a semicircle. It is not a chord. It is a ring, but not the complete ring. We say consider this as a segment of a ring. I would want you guys to consider this as a segment of a ring. Use the formula over here. B is equal to mu naught I divided by 2r, theta divided by 2. Now the question is what you are supposed to take the value of theta. I say join this point with one end of the wire. Join this point with another end of the wire. This will be the value of theta. Guys, always remember, let's suppose this is a complete circle. We say if you are moving from this point to this point, how much is the angle? 90 degrees. If you are moving from this point to this point, how much is the angle? 180 degrees. If you are moving from this point to this point, this point to this point only, how much is this angle? 270 degrees. 270 degrees. No. Complete. I'm saying from here to here only. From here to here only. This is 270 degrees. And when you take the complete circle, it is 360 degrees. So this 270 degrees comes when you have one chord, two chords, three chords. Here, one chord, two chords, three chords. So this angle in this particular case should be here. Theta should be 270 degrees. And in pi radians, you can call it 3 pi divided by 2. 3 pi by 2. 3 pi by 2 radians. Okay. 3 pi by 2. Now guys, use the formula. So I can say this B3 is a segment. So that is mu naught I. Okay. And if you put the values directly, we'll find it over here. So this magnetic field will come out to be, that is mu naught I divided by 2r. Put the value of theta as 3 pi divided by 2, and then you have got 2 pi. Now this pi and pi will cancel. 2 into 2 is 4, 4 into 2 is 8. So magnetic field will come out to be 3 by 8 mu naught I divided by r. So we say magnetic field because of this third comes out to be 3 by 8 mu naught I divided by, we say, R. Then we say plus magnetic field because of the second. This is a semi-infinite wire. Because of the semi-infinite wire, magnetic field is mu naught I by 4 pi R. So it is mu naught I divided by 4 pi, we say sir, R. Because you are finding at R distance. And in this case, you can say, what you can take common is, I can say mu naught I divided by, we say 4R. 4R you can take common. What remains in the first one? 3 by 2, and in the second one will be 1 divided by pi. So this will be the net magnetic field in this case. Guys, please tell me in the chats if this is crystalline clear. Please tell me in the chats if this is crystalline. Tell me, guys. I need the signal from every single student. Whosoever is watching this lecture, I want this signal. I would want you guys to tell me in the chats if this is crystalline clear, Let's move on to this one. Find the net magnetic field at the point O. We say this is a semi-infinite wire, Okay. Guys. In this case, we say this is semi-infinite wire, this is semicircle. Tell me one thing. If I say magnetic field because of this at this point will be in which direction? Direction of current is this. Place your thumb along the direction of current, curl your fingers. So place your thumb along direction of current, curl your fingers. Your magnetic field is inwards. So when it comes to the net magnetic field over here, that is magnetic field due to wire 1, magnetic field due to wire 2, magnetic field due to wire 3. Now let's first check the direction, then only we'll do add or subtract. Magnetic field because of this is inwards. Now let's check because of this. Curl your fingers along direction of current, thumb is pointing inwards. Because of this, it is inwards. So B1 is inwards, B2 is inwards. Magnetic field because of this. Place your thumb along the direction of current. Curl your fingers here. So it is also inwards. In case of a straight wire, we place the thumb along the direction of current. In case of a curved wire, okay, or a ring, we curl fingers along the direction. So all of these are inwards, so we add over here. So I can say magnetic field because of the first wire, that is mu naught I divided by, we say 4 pi. At what distance you are finding? R. Because magnetic field due to a semi-infinite wire is mu naught I by 4 pi R. Because this is semi-infinite. This is also semi-infinite. Okay, one end is at 0 degrees, another end is at infinity. So here also, one end is at 0 degrees, another end is at infinity. So mu naught I by 4 pi R. And then we say plus. This is semicircular wire. So it is mu naught I divided by 4R. Because of the semicircle, I'm sorry. Magnetic field is mu naught I by 4R. Okay. And then we say because of this semi-infinite wire, it is mu naught I divided by 4 pi R. This and this is 2 times. You can write 2 times mu naught I divided by 4 pi R. Then we say plus mu naught I divided by 4R. You can take the common also, or you can keep it like this also. This will be the magnetic. You can take common over here, mu naught I by 4R. Then, okay. Further you can write it. Let me write that also. P net is equal to mu naught I divided by 4R. Here it remains 2 by pi plus 1. Okay, let's talk about this one. Guys. In this particular case, you have to tell me what is the net magnetic field at O. See, This is the first part and this is the semi-infinite wire. This is also the semi-infinite wire. And here you have got, it is this portion of the wire is exactly like this. Yeah, it is similar. And we already got its magnetic field as 3 by 8 mu naught I by r. Now tell me one thing in this case. Guys. This center point is along this wire. This center point is along this wire. So I can clearly say in this particular case, magnetic field due to 1 will be equal to magnetic field due to 2. That will be equal to 0. Because of this wire and because of this wire, it is equal to 0. Why? Because this center lies along the axis. Because the center lies along the axis of the wire 1 and 2. Now guys, we say net magnetic field in this case, I can simply say as that will be magnetic field due to third part of the wire. And when it comes to the third part of the wire, we have already calculated its magnetic field, that is 3 by 8 mu naught I divided by r. If you want to check it, you can check it over here. If you want to check it, you can check it over here. Here is the complete detail. This angle, we considered this as an segment. This angle we took as 3 pi by 2, then calculated. This is mu naught I by this. And what will be the direction? Curl your fingers along the direction of current. Thumb is pointing inwards. So direction is. Okay. This is the last question, and after this we'll take the break. This is the last question, and after this we'll take the break, because then after this we'll be moving on to the next topic, that is Ampere's law. Find the net magnetic field at O. Okay. This is a very good question actually. This is a very good question. Guys, see. You have got a semi-infinite wire, then a semicircular ring, and then this semi-infinite wire. Okay. Guys, see, in this particular case, I would want you guys to understand one thing. See. It is like you have got a semi-infinite wire that is entering the board over here. Because see. Here, this was supposed to be, sir, y-axis. But in the question, they have mentioned this is z-axis. This was supposed to be x-axis. But in the question, they have mentioned this is y-axis. This was supposed to be z-axis. But in the question, they have mentioned this is x-axis. Okay. Now, guys, this question is like, there is a one wire which is entering the board. That is this first wire. I'll give you the 3D feel. This diagram is in the 3D. So the wire is basically entering the board. So current is entering the board. This is a semi-infinite wire. Okay, guys, understand this. This is the first wire over here entering the board. Then on the board, another wire is placed something like this. That is semicircular wire. Then another wire comes out of the board something like this. This is the structure. This is the structure entering and over here, then coming out. So this wire entering the board, this wire coming out of the board, and this wire is on the board, on the plane of the board. We have to find the net magnetic field at point O. Guys, tell me. I say this is a semi-infinite wire. I can write this as a semi-infinite wire. Semi-infinite. This also is semi-infinite. Semi-infinite and semi-infinite. Tell me one thing in this particular case. If I say magnetic field net over here, that will be magnetic field because of the first part of the wire, magnetic field because of the second part of the wire, magnetic field because of the third part of the wire. So that is B1, B2, and we say, sir, B3. Guys, understand one thing. Understand one thing in this particular case. See. Because of this, magnetic field will be, I'll just let's keep it plus. Magnetic field will be, so that is mu naught I divided by 4 pi at what distance? If this is r, so from this wire till here, this will be also r, this will be also r. 4 pi, we say r. Now, let's find the direction. Guys. This is the current going inwards. Place your thumb along the direction of current. Curl your fingers. So when you curl the fingers at point O, it is downwards. It is downwards. Now. It is downwards. My dear friends, if it is downwards, if the magnetic field because of this wire is downwards, we say this is the z axis. This is the z axis. And we say in the downward direction, it will be minus z. If you remember, if you remember in electrostatics, I have told you, if there is a vector which is along the x-axis, we say, let's suppose, guys, if you have got a block over here, if I am applying the force on this block, which is along the x direction, you can mention over here I cap. This I cap is the unit vector, which tells us the force is acting along the positive x direction. Okay. And if I say, if there is a force which is acting on this block in the y direction, so we say this will be the force along y direction, and we mention the j cap over here. J cap tells you the force is acting along y. And if I say the force is along z direction, we say fk cap. So this tells you the direction of the vector over here. Now, my dear friends, in this particular case, if I say, because of this magnetic field at the center is we say, sir, downward. In upward direction, we say plus z. In the downward direction, we say minus z. So I say the direction of this will be minus k cap. Minus k cap tells you the direction of this vector is in the downward direction. Okay. Tabi sabah, to samuk me stait, yeah? Erbenik. Yeah. Anyone samuk se kith kin chukim comment karan ki katen कर में मतलब कुंती जाए चीटिंग चाहे ऑफलाइन या वसीम सरन या मैं ना कमेंट करा इत पे एकस पॉइंट जुस एनर्जी ये छना आसान सु छसन बराबर ताई तो समख में ताई हा मैं समझात से मीन एनर्जी छा या वसीम सरन एनर्जी छा कुंती जाए कम आसान कुंती क्लासेस में चाहे पत शोंगमित आसो या न शोंगमित आसो and you are expecting to expect karan ki gsak expect karan ki gsak kamyab pannen teacher it can disrespect kare huh chalo now guys, so we say I'll write over here minus k cap. Now then I'll write plus over here. Magnetic field because of this wire. This is a semicircular wire. Because of the semicircular wire, magnetic field is mu naught I divided by 4r. Now what is the direction? Curl your fingers along the direction of current. Thumb is pointing inwards. If it is inwards, outward is plus x, inward is minus x. Outward is plus x, inward is minus x. So I'll write over here minus I cap. So this tells you the direction of the magnetic field because of this semicircular wire is inwards. Then we say magnetic field because of this wire. See, we say plus. Magnetic field because of this wire will be same and it will be downwards. Place your thumb along the direction of current. Thumb is pointing downwards, and it will be also mu naught I divided by 4 pi r, and this is minus k. Okay. So you can write over here minus mu naught I. And this you can clearly see this and this are twice over here. Because of this, it is in the downward direction. Because of this, also downward direction. That's why minus k cap minus k cap. So I can say in this particular case, this is 2 times mu naught I divided by 4 pi r, and it is k cap over here and it is minus over here. And then we say minus mu naught I divided by, we say 4r. This will be the net magnetic. Is that clear? Is that clear? Please tell me in the chats. Is that clear? Please tell me in the chats. Is that clear? Please tell me in the chats, everybody out there. So this will be the net magnetic. Guys, don't get confused in this particular question, because I cap, J cap, these basically tell you the direction of the vector. I cap plus I cap has the positive x direction. Minus I cap means vector has minus I cap, minus x direction. Vector is in minus x. Plus J cap means it is in the y direction. Minus J cap means it is in the minus y direction. Now guys, let's understand Ampere's circuital law. Okay, one of the important topics when it comes to the magnetism. Okay, and a lot of people are confused in this topic also, but I'll make you understand this particular topic and we'll start from the scratch. Now see, let me write over here Ampere's circuital law. Let me make you understand this Ampere's circuital law over here. See guys, when it comes to the Ampere's circuital law, the very first thing over here is, we say, I'll just write over here, it is used to calculate the magnetic field. Like we have Biot-Savart's law. Biot-Savart's law is also used to calculate the magnetic field. Similarly, we say we have got the Ampere's law. Ampere's law is also used to calculate what? The magnetic field. Now, how do we exactly use this Ampere's law? How do we calculate the magnetic field with the help of this Ampere's law? That I'll make you understand over here. Listen to me very carefully. As of now, we have studied, if we have an infinite wire, let's suppose this is an infinite wire. And because of this infinite wire, if I say current I is flowing in this one, because of this infinite wire at r distance, magnetic field, we simply say that is mu naught I divided by 2 pi r. This is the magnetic field because of the infinite wire. Now, I would want you guys to find the magnetic field because of the infinite wire, because using Ampere's circuital law. This is the expression that we got previously with the help of the Biot-Savart's law. But now we'll get the same expression using Ampere's circuital law. Now guys, see, let's suppose I'll take the same infinite wire over here. Okay, this is the infinitely long wire. This is going till infinity. And in this wire, I am saying, let's suppose current I is flowing. And we have to find the magnetic field at a distance from the wire. What I want you guys to do is, I want you to basically take, basically a loop over here. I'll make you understand what is that. Just a second. So let's suppose I'm creating this loop exactly over here. See, using Ampere's law to find the magnetic field, it says you have to apply some rules. What is the first thing? We say use
Ampere's law. Ampere's law to find the magnetic field, at a distance. Use Ampere's law to find the magnetic field at a distance. Yes. Now guys, what is the first thing that Ampere's law says? We say, according to Ampere's law. See, what does it say? It says, draw a loop. Draw an Ampere's loop. Ampere's loop. That should pass through. That must pass through that point. That must pass through that point. So if you want to find the magnetic field because of this wire at r distance, you are supposed to draw this loop such that that loop should pass through that particular point at which you have to find the magnetic field. It's not like you will make the loop something like this. No, you have to make loop in such a way so that that point lies on that particular loop. Okay. Then the next step it says that take a small element on the loop. Okay. Now take a small element on the loop. I would want you guys to take a small element dl on the loop. And let's suppose magnetic field because of this wire at this point will be, sir, B. And magnetic field due to the wire at point P. Let's suppose this is point P is B. Now, in order to find the magnetic field because of the using Ampere's law, what is the first thing we are supposed to do? We say draw an Ampere's loop such that the loop is passing through that particular point. Next, take a small element of the loop over here, that is dl. And magnetic field at r distance because of this wire is B. Then my dear friends, I'll just write over here. Then take close line integral. I'll make you understand this. Then take close line integral and make it equal to mu naught times, or directly I'll say, then make it equal to mu naught into I. Now guys, once you are done with that, then it says take the closed line integral. That is, closed line integral means this. Closed line integral B dl and make it equal to mu naught times of I enclosed. What does it mean? It says that in order to find the magnetic field using Ampere's law, what is the first thing you guys are supposed to do? Draw an Ampere's loop. So if you are drawing an Ampere's loop such that the loop should pass through that particular point, and take a small element dl and magnetic field because of this wire at this point P is, let's suppose, B, then do the integration of this B and dl and make this integration equal to mu naught times of I. What is this I? I is the enclosed current which is in the loop. Okay. Now guys, I would say in this particular case, this is what we call the Ampere's law. But sir, we didn't get the exact value. Yes, I'll tell you how do we exactly get that value. Just wait for a second. This is the Ampere's law. Now guys, in order to find, now we say, listen to me very carefully.
Let's suppose if I'm saying, sir, magnetic field because of this wire at r distance will be, sir, B. So this is a wire. At r distance, magnetic field is B. At r distance, magnetic field is B. B, B, B. Now, guys, I would want you guys to basically do one thing. Take this magnetic field out because that will be constant. Then integration of dl is equal to mu naught times of I. And what is this I? I is the current which is enclosed in the loop, which is present inside the loop. Okay. And I can say in this particular case, what is this integral of dl? If you are adding all the small elements of this loop, you will get the complete circumference of the loop. So I can say in this particular case, so this will be B into, and this will be 2 pi r, and this will be mu naught times of I. And I can say this magnetic field will come out to be mu naught I divided by 2 pi r. And we know this is the magnetic field because of an infinitely long wire. And we got this magnetic field expression using the Ampere's law. Okay. Previously, we got it with the help of the Biot-Savart's law, but right now, I'm getting this expression using the Ampere-Circuital law. Okay, I hope this is crystalline clear till over here. I hope this is crystalline clear till over here. Okay, so what does Ampere's law say? Ampere's law from now onwards says only this much. We say closed line integral B dl is equal to mu naught times of I enclosed. This is the enclosed current. Enclosed current means that current which is present inside the loop. Okay. Now you have got the question on the screen. We need to apply the Ampere's law on this question. See, guys, listen to me very carefully. You have got a loop over here. This is the Ampere's loop. And one more thing I forgot to tell you in this particular case. What is that? What is that? Always remember, guys, see, if B, magnetic field and dl, if magnetic field and dl, like my dear friends in this particular case, here, this is dl, it has some direction. Yes, dl has the direction. Sir, will it be given in the question yet? Yes, it will be given in the question. So this is the direction of dl over here. And this is the magnetic field. Always remember, if B and dl are in the same direction, if B and dl are in the same direction, then take I enclosed as positive. Then take this enclosed current as positive. And second point, if magnetic field and dl are in opposite direction, then take B and dl as negative. Then take B and dl as then take I as negative. Like it will be cleared in the question. Let's suppose we have got a question over here, guys. The direction of, here you have got three currents. This is I3, this is I1, and this is I2. Direction of I1 is this, direction of I3 is this, and this is direction of I2, and this is direction of I3. And the direction of dl in this particular case is given as this. This is the direction of dl. Now, guys, we need to use or apply the Ampere's law over here. What does Ampere's law say? Ampere's law say closed line integral B dl is equal to mu naught times of I enclosed. The very first thing over here is we're supposed to take only those currents which are enclosed in the loop. And I can see I2 and I1 are the enclosed currents, because this is the current which lies outside of the loop. So we cannot take this as an enclosed current. So here I'll just mention over here that is I1, and I'll just write over here I2. Now, guys, we have to define the sign. Is it positive or is the current negative? See, guys, this is the current. Because of this current, could you please tell me what is the direction of magnetic field over here? Place your thumb along the direction of current. Curl your fingers. So in this particular case, magnetic field will be also in the same direction. This is B1. Sir, it is inwards. This loop is also in 3D. Then direction of DL is also inwards. If you take inwards, this will be inwards. It's one and the same thing. So because of this current, this is the magnetic field B1. And you see, B1 magnetic field and DL, they are in the same direction. So this current I1, due to which this magnetic field is being produced, we take this as positive. So we take this as positive. Why? Because if B and DL are in the same direction, then we take the current as positive. Now see, this is the current. Because of this current, let's find the magnetic field over here. Place your thumb along direction of current. Thumb is pointing outwards. So outward, I'll say over here, it would be something like this. This is B2. This is the magnetic field because of the second wire. Now tell me over here, this B2 and DL are in the opposite direction. So I can say I will take this B2, I'll take this I2 as negative. Why? Because this magnetic field and this DL are in the opposite direction. This is what I mentioned over here. If B and DL are in the opposite direction, then current is taken as negative. Let me show you this. Let me show you one more question. See guys, in this particular case, you have got this loop over here. This is the direction of the loop. This is the direction of the loop. Okay. Yes. Now, here we need to use the Ampere's law. Here we need to use the Ampere's law. Now, first and the foremost thing is, when it comes to the Ampere's law, what does it say? Closed line integral B dl is equal to mu naught times of I enclosed. Now, you tell me, what are the currents which are enclosed? I1, it is cross. I2, I3, I4. I5 and I6 are not the enclosed currents. So I can write over here closed line integral B dl is equal to mu naught times of I enclosed. And in the enclosed current, I'll take I1, I'll take I2, I'll take I3, and I'll take I4. Now we have to define the direction. Okay. And in this particular case, this is the direction of DL. Now guys, this current is inward. Place your thumb along the direction of current. So because of this, magnetic field here will be, curl your fingers. So magnetic field will be in this direction. This is B1. Now see, B1 and DL, they are in the opposite direction, and I am supposed to take this current as negative. Then my dear friends, this I2. Place your thumb along direction of current. Magnetic field because of this will be also in the same direction, something like this. So this is B2. So I can say in this particular case, B2 and DL are also in the opposite direction, so it will be minus I2. Then this current, because of this current, let's find the direction of magnetic field. Place your thumb along direction of current, curl your fingers. So I can say this is the direction of magnetic field, that is B3. So because of this current, magnetic field is in this direction. Now this magnetic field and this DL are in the same direction, so this will be positive. Similarly, because of this I4, magnetic field will be also in the same direction. This is B4. Now see, B4 and DL are also in the same direction, so this will be positive. So if you have to determine whether the current is positive or negative, you have to check the direction of B and DL. Okay. Next, we have got this question over here. See guys, in this particular case also, we are supposed to use the Ampere's law. You have got the current I1 over here, which is dot, and this current is I2 over here, which is also dot. Tell me one thing. When it comes to the first case, you say closed line integral B dl is equal to mu naught times of. Guys, first and the foremost thing over here is I1 is the enclosed current, I2 lies outside of the loop. So I can say it will be I1. Now let's check if the I1 is positive or negative. Because of this I1, magnetic field over here is in this direction. Place your thumb along direction of current.
curl your fingers. So this is the direction of DL and this is the direction of magnetic field B. So they are in the same direction, so current is taken as positive. Let's apply here. So we say in this particular case, magnetic field BDL will be equal to mu naught times of. What is the enclosed current? I1 is outside, I2 is inside. So I can say, sir, this will be I2. Now, is it positive or negative? See guys, this is the direction of DL that is given over here. Now place your thumb along the direction of current. Curl your fingers because this current is inward. Then curl your fingers. So because of this current, magnetic field will be this. Now tell me, this B and DL are in the opposite direction, so it will be minus I2. Let's take a look at this question. See, it is something like this. I'll make it a bit bigger. Okay, here this is the current I1 and this is the current I2. Both the currents are in the loop and here you have got separate loops, this loop and this loop. Now tell me boys and girls, in this particular case, tell me boys and girls, see, can I say when it comes to the Ampere's law, so we say that is BDL is equal to mu naught times of. Sir, both the currents are enclosed current, so I can write over here this is I1 and I can write over here this is I2. Enough. Let me tell you in this case, what is the direction of DL? This is the direction of DL. This is the direction of DL. Because of this, let's check the magnetic field direction. Place your thumb along direction of current. Curl your fingers. This current is outwards. So curl your fingers. So this is the direction of, I can say, B. Now DL and B are in the opposite direction. So I1 will be negative. Similarly here, if I say, place your thumb along the direction of current. Curl your fingers. Curl your fingers. So this will be the direction of, we say, sir, B. And here B and DL are opposite, so it will be minus I2. It will be minus I2. Now let's apply the magnetic field. Let's apply the Ampere's law in this question. I'll make it over here. I'll make it over here. It will be something like this. It is something like this. And in this particular case, let me just check the direction of the loop. Okay. Direction of the loop is this. This is the direction of the loop. And here current is I1. This is dot, dot, cross, dot. This is dot, dot, cross, and this is dot. This is over here I2, this is I3, this is I4. And if you check in this particular case, all the currents are within the loop. This is in the separate loop, this is in the separate loop, this is in the separate loop, this is in the separate loop. And in this particular case, if I use the Ampere's law, I can say that is closed line integral BDL is equal to. Then we say mu naught times of enclosed current. What is the enclosed current I'm supposed to take? I1, I2, I3, I4. So I'll just write over here I1, this will be I2, this is I3, and this is I4. Now guys, let's check the direction of magnetic field. Because of this current, what is the direction of magnetic field? Place your thumb along direction of current. Curl your fingers at this point. So we say direction of magnetic field is this. This is B1. Now see, B1 and DL are in the same direction, so this current is positive. Okay. Now in this particular, sir, from the upper side, if you check from the lower side, sir, current is outward. So from the lower side also, this will be the direction of magnetic field. So from the lower side also, we say magnetic field and DL are in the same direction. Let's check in this case. Place your thumb along direction of current. Curl your fingers over here. So because of this, magnetic field at this point will be this. So magnetic field and DL are in the opposite direction. So this current will be negative. Check here. Place your thumb along direction of current. That is inwards. Curl your fingers.
So because of this, magnetic field would be this. So magnetic field and dr are in the opposite direction, so this is negative. Now because of this, place your thumb along direction of current, curl your fingers. So here magnetic field would be this. So magnetic field and dl are opposite, so this would be also negative. So only first current is positive, rest of the three currents we have to take negative. This is how we actually use the Ampere's circuital law. Okay. Now guys, let's move on to the magnetic field due to a hollow cylinder. Let's move on to the magnetic field due to a hollow cylinder. Okay. See, I say this is a hollow cylinder. When it comes to the hollow cylinder, we say hollow means when mass is not present inside. It is hollow from the inner side. If it is hollow from the inner side, I can say here matter is present only on its surface. So current will flow through the surface only. Current will not flow through inside. So I can say in case of a hollow cylinder, in case of a hollow cylinder, we say current flows through its surface only. Current flows through its surface only. Why? Because matter is present on the surface. Inside it is only air. Yes. Now guys, in case of a hollow cylinder, we say current flows through its surface only. Now, if current is present, so it produces the magnetic field. It produces the magnetic field. And we are supposed to find the magnetic field. We are supposed to find the magnetic field outside the cylinder at small r distance. So it produces magnetic field. To find the magnetic field outside surface inside. To find the magnetic field outside surface inside. When it comes to the magnetic field because of a hollow cylinder outside the surface, guys, see. So first and the foremost thing is I'll find the magnetic field outside the surface. Outside the surface. Tell me one thing. When it comes to the outside the surface, we say from very far distance, if let's suppose you are holding a hollow cylinder, it's a long hollow cylinder. From very far distance, 1 kilometer away, 0.5 kilometer away, you are looking at this hollow cylinder. Don't you think it will look like to you a thin rod? It will look like to you a thin wire? Yes. And here we talk about the infinitely long hollow cylinders. So we say from very far distance, it looks like to you an infinite long wire. So I can say from large distance, it behaves like a infinite wire. And what is the magnetic field because of an infinite wire? We know, sir, magnetic field because of an infinite wire is mu naught I divided by 2 pi r. So outside magnetic field will be simply this. This is the magnetic field outside the cylinder. This is the magnetic field due to a hollow cylinder outside the surface. And my dear friends, when it comes to on the surface, when it comes to on the surface, don't you think that on the surface value of small r will be equal to capital R? Value of small r will be equal to capital R. Why? Because the radius of the cylinder is, we say, sir, that is capital R.
So we'll use the same expression, but the magnetic field will be, I can say in this case, magnetic field will be, that is mu naught I divided by, we say 2 pi. Instead of small r, I'll just write capital R. Okay. Yes. And when it comes to inside the surface, guys, inside the surface, I am saying current is 0. When there is no current, don't you think that magnetic field will be 0? So I can say current is 0. So inside the surface, magnetic field will be 0. So magnetic field outside the surface, on the surface, inside the surface. And outside the surface, you can clearly see magnetic field is inversely proportional to small r. As you go from away from the surface, as you go from away from the cylinder, we say magnetic field will decrease. And this magnetic field is constant. Because mu naught is constant, current in the cylinder is constant, 2 pi is constant, radius of the cylinder is constant. So the entire expression is constant. Now guys, if I say plot the graph between magnetic field versus R, I'll just write over here, graph between magnetic field versus small r. If I say plot the graph between magnetic field versus small r, tell me one thing. Inside the surface, magnetic field is 0. Means inside the cylinder, magnetic field is 0. So this is the origin. At origin, we say R is equal to 0. Now tell me, sir, we are measuring the small r from the center, from this axis. Can I say here, small r is 0? On the surface, value of small r becomes equal to the capital R. Yes. Now, from center to surface, we say magnetic field is 0. And when you reach the surface, so I can say R becomes equal to capital R. And when it comes to that, magnetic field is mu naught I by 2 pi R. So I can say magnetic field is mu naught I by 2 pi R. We say directly magnetic field is going to increase. Okay. And then as you move away from the surface, outside the surface, magnetic field is inversely proportional to R. So the graph will become a rectangular hyperbola. So this is outside and magnetic field is inversely proportional to R. This is inside. Magnetic field is 0. This graph was asked in NEET 2021. Extremely important graph. Next, you have got a solid cylinder. Sir, what is a solid cylinder? I'll make you understand what is a solid cylinder. See guys, when it comes to the solid cylinder, I can simply say in case of a solid cylinder, matter is present inside also. It is solid. It is not hollow from the inner side. So we say in case of solid cylinder, current flows through the surface also. Current flows through the cross-sectional area also. I'll just write over here, in case of a solid cylinder, current flows through, in case of a solid cylinder, current flows through its cross-section also. So right now current is present inside also. Now guys, I would want you to focus exactly over here. Here also, to find the magnetic field, we say outside. To find the magnetic field outside, surface and inside.
We are supposed to find the magnetic field outside the surface, inside the surface, and on the surface. Okay. Now let's first talk about outside the surface. Outside the surface. Let's first talk about outside the surface. Now guys, when it comes to outside the surface, if you are holding a hollow cylinder, if you are holding a solid cylinder, and your friend is looking at you from very large distance, so for him, both hollow as well as solid will appear to him as a infinite wire, as a thin wire. Because if you're looking at this hollow or solid cylinder from very large distance, it looks like you are holding an infinite wire. You are holding a thin wire. It's one and the same thing. So we say magnetic field outside will be simply, that is mu naught I divided by 2 pi r. Sir, is it like the hollow cylinder also? Yes, it will be exactly same. Why? Because from very large distance, we consider it an infinite wire. And when it comes to the surface, on the surface, we say on the surface. Can I say on the surface, value of small r will be equal to capital R? Yes. So I can say magnetic field on the surface will be simply, that is mu naught I divided by, then we say 2 pi into capital R. Okay, this is the magnetic field due to a hollow cylinder on the surface, And then we have inside the surface. Guys, if I tell you inside the surface, we say inside right now current is flowing. Okay, inside current is flowing. So you cannot say magnetic field inside will be 0. When it comes to inside the surface, I can say magnetic field will be simply, that is mu naught I into small r. Sir, what is this small r? Small r is the distance. Inside the surface from the central axis where you have to find the magnetic field. And capital R is the radius of this. And this is the outside distance, small r, where you have to find. This small r is basically variable. For outside point, small r is large. For inside point, small r is small. It is less. So it will be mu naught I into r divided by 2 pi into capital R square divided by 2 pi into capital R square. This is the magnetic field. Due to an infinite solid cylinder outside. And clearly you can see in this particular case, B is directly proportional to R. And outside you can say B is inversely proportional to R. And one more thing I must tell you in this particular case. What is that? Sir, if we put value of small r here, if we put value of small r is equal to capital R, let's see what will happen. So we say magnetic field will become, that is mu naught I into capital R divided by 2 pi into capital R square. This and this will cancel. So it will come out to be mu naught I divided by 2 pi into capital R. So if you are putting the value of small r is equal to capital R, then you are finding the magnetic field on the surface. And you see magnetic field on the surface with the help of this formula is exactly coming out to be same. By using both the formulas. That's why this formula is also correct. Okay. Now. Let me tell you one more thing. We say as. When it comes to the magnetic field over here, see, this magnetic field is mu naught I into R divided by 2 pi R square. So outside magnetic field is B outside, that is mu naught I into R divided by 2 pi R square. Now guys, what is this pi R square? Pi R square is the area of the cross section of the cylinder. Okay, I'll just write as area is equal to pi pi r square. So can I say this magnetic field outside will be mu naught into r, okay, and divided by 2, and then I'll write I divided by pi r square. So this is current upon area. What is current upon area? I guess that is current density, J. So I can say B outside will be simply, that is mu naught R into J divided by 2. Okay, because we say current density J is current divided by area. I upon A is the current density. As simple as that. Okay, so this is basically the magnetic field over here. This is basically the magnetic field over here. Okay, and let's plot the graph in this case. I'll just write over here graph between magnetic field versus small r, and I'll just make the two axes something like this. This is magnetic field, this is small r. Tell me guys one thing, when it comes to inside the cylinder, you can clearly see inside the cylinder magnetic field is directly proportional to small r. So inside the cylinder magnetic field is directly proportional to small r. Something like this. Okay, so magnetic field is directly proportional to small r. And when it comes to outside the cylinder, we say magnetic field is inversely proportional to small r. So outside the cylinder, graph would be this. So B is inversely proportional to small r. This is outside and this is inside. Okay, so I can say this will be the surface. And this graph was asked in NEET 2020. So that's why I told you graphs in these two topics are very important. Okay, I hope this is crystalline clear. Okay. Now guys, let's move on to, we have got a question over here which was asked in NEET 2016. See what does the question say. A long straight wire of radius A carrying a steady current I. So when it says that it has got a long straight wire, means it is talking about the cylinder, long straight wire of radius A. When it gives the radius, so means it is talking about what cylinder? It has got the radius A. So it has got the radius A. The current is uniformly distributed over its cross section. Current is uniformly distributed over its cross section. The ratio of magnetic field B and B dash at radial distances A by 2 and 2A. We are supposed to find the magnetic field at 2A distance. 2A will be outside the cylinder, and A by 2 distance, A by 2 will be inside the cylinder, Okay. Okay. Now guys, tell me one thing. I would want you guys to tell me one thing. What is that? That is, see, if I say magnetic field here, the ratio of magnetic field B and B dash at A by 2, this is B over here and this is B dash over here. Now, B is inside the cylinder. If I just write inside the cylinder. Guys, we recently saw what is the formula of magnetic field inside the cylinder. Mu naught I into R divided by 2 pi R square. So I can say B is equal to mu naught I into R divided by 2 pi capital R square. Capital R is the radius and small r is the distance where you have to find the magnetic field. So this magnetic field will come out to be mu naught I. What is the value of small r over here? That is A by 2 for the inside point. So A divided by 2. And then you have 2 pi capital R square. What is the radius? Capital R over here, that is A. So it will be A square. Okay. Now this square and this will cancel. So magnetic field will come out to be mu naught I divided by 2 into 2 is 4 pi a. Now let's talk about outside the cylinder at 2a distance. I'll just write over here outside the cylinder. So can I say that will be simply b dash is equal to this b dash, and outside the cylinder it is simply mu naught I divided by 2 pi into small r. This is the magnetic field we use for the outside. And in this case, this magnetic field b dash is mu naught I divided by 2 pi. What is the value of small r? Small r for outside point is 2a. I'll just write over here 2a. So this will be mu naught I divided by 2 into 2 is 4 pi a. Now don't you think that, guys, this is b and this is b dash. So I can say b divided by b dash is simply 1:1. So answer in this case is 1. Okay. Now let's talk about magnetic force. This topic is kind of my favorite topic over here in magnetism, magnetic force. Now guys, understand very carefully this topic. Let's understand from the basics, from the scratch. See guys, what does it say? That you have got a magnetic field over here in this region B. Okay. And you are sending a charge in this magnetic field over here. You are sending a charge in this magnetic field over here with a velocity v. You are sending a charge. Magnetic field is inward. You are sending a charge over here with a velocity v. We say, if a charge is placed in a magnetic field, if you place a charge in a magnetic field and is given some velocity v and some velocity is given to it, it is not at rest. We say magnetic force acts on it. Magnetic force will act on it. And if I ask you, sir, how much is the value of that magnetic force? You say, sir, that magnetic force will be simply, that is Q. Q is the charge which you are sending in the magnetic field. And then we say into V cross B. Q into V cross B. Sir, what is V? V is the velocity and B is the magnetic field. Like previously you have studied in electrostatics, you have got the electric field. In this electric field, if you place the charge, we say, sir, force will act. Even if the charge is at rest, force will still act. But here, when the charge is placed in the magnetic field, some velocity is given to it, we say then only force will act on it. Yes. Now guys, tell me, V cross B, we say A cross B, that is the cross product of A and B. We say A cross B is AB sine theta. Don't you think that V cross will be VB sine theta? So I can say this magnetic force will be simply, that is QVB, and then we say sine of theta. And I say where theta is the angle between, we say V and B. Where theta is the angle between velocity and magnetic field. Where theta is the angle between velocity and magnetic field. Okay. Now guys, listen to me very carefully. Let's now talk about case 1. Case 1 is mentioned over here. This is case 1. Now, my dear friends, in this particular case, okay, let me make it over here. Case 1. We say case 1. Case 1. We say, and one before this, direction. Direction of force. Let's find the direction of force. If you want to find the direction of force, always remember, these are your fingers. Place your fingers along the direction of velocity. Place your fingers along direction of velocity. Curl towards magnetic field. Magnetic field is inwards. Velocity is upward. Magnetic field is inwards. So place your fingers along direction of velocity. Curl towards magnetic field. Thumb is pointing towards this side. So we say that will be the direction of magnetic force. How to find the direction? We say place your fingers along the direction. Place your fingers along the direction of velocity. Place your fingers along the direction of velocity. Then curl towards magnetic field. Thumb gives the direction. Thumb gives the direction of magnetic force. Thumb gives the direction of magnetic force. Okay. Now guys, let's suppose if I talk about case 1 over here. I say case 1. Sir, what is this case 1? I'll make you understand what is this case 1. What is this case 1? We say if theta is equal to 0 degrees. Case 1 is if theta is equal to 0 degrees. See guys, let's suppose this is the direction of magnetic field. Okay. And in this magnetic field, you are placing a charge which flows in the same direction. You are placing a charge which flows in the same direction. Now, in this case, if I talk about the magnetic force, this magnetic force will be, that is QVB sine of theta. And this magnetic force will be, that is QVB. What is theta? Theta is the angle between velocity and magnetic field. So that is 0. So sine of 0. So here magnetic force will be 0. Because sine 0 is 0. If the angle between velocity and magnetic field is 0, then we say in that case, magnetic force will be 0. Okay. Let's suppose case 2. Case 2 is theta is equal to 180 degrees. Like magnetic field is in the forward direction. Okay. And this charge is moving in the backward direction. And in this particular case, I can say this magnetic force will be, that is QVB sine of 180 degrees. Sine 180 is also 0. So here magnetic force will be 0. So in both the cases, magnetic force will come out to be 0. Okay. Yes. Okay. Now, my dear friends, case 3. Case 3, when theta is equal to 90 degrees. Let's suppose this is the magnetic field. This magnetic field is inwards. And in this magnetic field, you are sending a charge. And this charge is moving with a velocity v. Okay. Now here, magnetic field is inward. Velocity is forward. Angle between magnetic field and velocity is 90 degrees. Inward and forward. Magnetic field is inward. Velocity is forward. Angle is 90. So here, if I just talk about the magnetic force, FB is equal to QVB sine of 90. Sine 90 is 1. So I can say magnetic force in this case will be, that is QVB. Okay, this case and this case is also done. Let's take a look at this particular question, which is over here. Okay. Now guys, let's take a look exactly over here. See, a charged particle of specific charge 0.2 coulomb per kg. What does this specific charge actually mean? Specific charge means Q divided by M. Charge upon mass. Charge upon mass means specific charge. And this is given over here 0.2 coulomb per kg. Means on per kg, on every kg, how much charge is present? 0.2 coulomb. So here, I'm saying Q divided by M is given as 0.2 coulomb per kg. This is the specific charge. The velocity of the charge, velocity is given as, that is 2I minus 3j cap. Meter per second at some instant in a uniform magnetic field, and magnetic field is given as, that is 5I cap plus 2j cap. This is Tesla. This is meter per second. Find the acceleration of the particle. Now guys, listen to me very carefully. Listen to me very carefully. You have got a charge which is placed in the magnetic field, and this is the velocity. You are supposed to find the acceleration of the charge. See, we say as force on the charge, as force on the charge. F is equal to, that is QVB, and then we say sine of theta. F is equal to QVB sine of theta. Now, my dear friends, I would want you to tell me one thing. We say when it comes to as acceleration of the charge, as acceleration of the charge, we say acceleration is simply force divided by mass. Acceleration is simply force divided by mass. Now, can I write over here this acceleration is, what is force? That is QVB sine of theta divided by over here m, mass. Now, what is the value of Q by M? I can write over here A will be, what is the value of Q by M? Q by M is given as 0.2. So this is 0.2. I'll just directly write. Velocity. What is velocity over here? 2I cap minus 3j cap. Okay. Okay. And theta is not given. Instead of this equation, I would want you guys to use directly. Just a second. I would want you guys to use directly. Which one? See, we say directly use over here. That is Q into V cross B. Q into V cross B. Use this formula. Okay. So here, this is Q into V cross B. This is the force, okay, divided by mass m. Now, what is the velocity? Velocity in this particular case is given. Velocity in this particular case is given. That is 2I plus 2I minus, we say 3j. This is the velocity. Okay. And then we say cross. Velocity cross magnetic field. And magnetic field in this case is given as 5I cap plus 2j cap. 5I cap plus 2j cap. Okay. Now guys, you are supposed to find the cross product of these two and you'll get the answer. Let's find the cross product. See guys, always I'll show you how do we find the cross product. Just remember this rule from now onwards. Let's suppose you have got a vector over here. Guys, directly remember. What is the vector over here? What is the vector over here? V vector. We say in this case, V vector is, that is 2I cap minus 3j cap. I'll say over here, that is 2I cap minus 3j cap. And what is magnetic field vector over here? Magnetic field is 5 plus 2j. We say 5I cap plus 2j cap. Okay. Yes. Now guys, in this case, if I say V cross B, velocity cross magnetic field, always remember, whenever you have to do the cross product of two vectors, just make the determinant over here. Okay, just make the determinant. Okay. Then over here, you write I cap, you write over here j cap, and you write over here k cap. I, j, k. Okay. And my dear friends, in this particular case, ijk, first you have to mention the coefficient of I. What is the coefficient of I over here? That is 2. So we'll be writing over here 2. What is the coefficient of j in the first vector? That is -3. It is -3. And is it k mentioned over here? No. So you mention k is 0 over here. If k is not given, you mention 0. If j is not given, you mention that 0. So if I say a vector is 3i cap plus 9j cap plus 4k cap. Okay. So you'll say here I will be 3. Here j will be 9. K will be 4 in that case. And then take this another vector b. So what is the coefficient of I over here? That is 5. What is the coefficient of j over here? That is 2. And k is not mentioned. So I'll write over here, this is 0. And what is this ijk? Guys, you guys should know this I cap is the unit vector along x-axis. Means if this is a block, I am applying the force, this force is in the x-axis direction, along x-axis. So I can say this is Fi cap. If the force is acting along the x-axis, then we mention over here I cap. If the force is acting along y-axis, then we say this is j cap. Sorry, this is minus Fi cap. Minus Fi cap, negative. And if I say force is acting along y-axis, then you can mention j cap. So this I, j, k, these are basically telling you what is the direction of the vector. If it is along the plus x, if it is along the minus x, if it is upward, if it is downward, in which direction the force is acting, it is telling you basically that only. Okay. Now guys, let's take a look in this particular case. You say you have got 2, 3. Now what we are supposed to do is this V cross B. It will be simply first solve it for I. I'll just write over here, this is I cap. Now guys, if this is, you are solving it for I, let me show you how. Hide this column in which I is present and hide that row in which I is present. So these two. What remains over here? -3, 0, 2, 0. So do the cross multiplication of these. -3 into 0 is 0. 2 into 0 is this minus 2 into 0 is 0. Now solve for j and then I'll write over here minus j cap. Minus j. First I, then minus j. Now hide that column in which j is present. Hide that row in which j is present. What remains over here? 2, 0, 5, 0. 2 into 0 is 0. 5 into 0 is 0. So 2 into 0 is 0. 5 into 0 is minus. This will be also 0. Then hide that column in which k is present. Hide that row in which k is present. Now these four are 2 into 2 is, we say, now plus, I'll just write over here k cap. Now 2 into 2 is 4. 5 into 3 is, then we say minus. 5 into 3 is minus 15. So I'll write over here minus 15. Always remember you put minus over here. Okay. And here in front of j you put minus, here you put plus. And this will be I and this will be 0. This will be 0, this will be 0 and this. Now guys, minus into minus is plus. 15 plus 4 is 19. So it will become 19 k cap. So V cross B came out to be 19 k cap. Now, let's move on to the previous. So can I say, so when it comes to the acceleration, it will be, so this is 0.2. And what is the cross product of this V cross B directly? You'll simply say, sir, when it comes to the V cross B. So instead of this, you'll directly write over here V cross B. And we got the value of V cross B as 19 k cap. So it will be 19 k cap. What does k cap mean? K cap means it is along the positive z direction. So 19 into 0.2, it will be 3.8. We say meter per second square, and this will be k cap. Okay, or we write it something like this. First we write k cap. First we write k cap, then meter per second square. So this will be the acceleration in this particular case. Next question. A charged particle is projected in a magnetic field. B is equal to 3I cap plus 4J cap into 10 raised power 2 Tesla. We have got a charged particle which we have placed in a magnetic field, and the value of the magnetic field is given over here. Cool. And the acceleration of the particle is found out to be, this is the acceleration of the particle. Cool. The value of x is, we have to find the value of this x. Guys, see. Let's suppose you have got a vector A, okay, and you have got a vector B. We have two types of multiplication products. First is cross product in vectors, then you have dot product in vectors. Cross product means A cross B, we say AB sine theta. Dot product means if you put the dot over here, this is also multiplication of two vectors, but which one? Dot product. So you say this will be AB cos of theta. And if I say A cross B, then it becomes AB sine theta. If I say, my dear friends, over here, if theta is equal to 90 degrees, angle between A and B is 90, then in that case we say this A vector dot we say B vector will come out to be, we say this is AB cos of 90, over here cos of 90. So I say cos 90 is 0, so we say it will come out to be 0. So means dot product of two vectors is 0 if the two vectors are perpendicular to each other, if the angle between the two vectors is 90. So if angle between the two vectors is 90, then we say their dot product is 0. Guys, in this particular case, we say this is magnetic field and this is acceleration. We say as we know, magnetic force, we say when it comes to the magnetic force, okay, and magnetic force and magnetic field are perpendicular here, Why? Because what I'm trying to say in this particular case is this one. Magnetic field is inward, magnetic force is something like this, so basically they are at 90 degrees. Now guys, whatever is the direction of magnetic force, same will be the direction of acceleration, because force is equal to mass into acceleration. If force is forward, acceleration is forward. So I can say acceleration and magnetic field are perpendicular. If the two vectors are perpendicular, then we say their dot product is 0. So I can say A vector dot B vector is equal to 0. And what is A vector over here? A vector is given as, that is xi cap plus 2j cap. And then dot B vector over here is 3i cap plus 4j cap, okay, into 10 raised power minus 2 is equal to 0. It will go over there, it will become 0 only. Now do the dot multiplication, sir. How do we do the dot cross? In case of cross multiplication, we make the determinant that I have shown you over here. A cross B, we make the determinant. But when it comes to the dot product, directly do the multiplication. This with this, x into 3, so it will be 3x. Okay, x into 3, like over here I cap, x into 3 is 3x. Then we say plus. Sir, 4 into 2 is 8 is equal to 0. Now take this over there, we say 3x will be equal to minus 8 and x will be equal to minus 8 by 3. X will be equal to minus 8 by 3. Okay, x will be equal to minus 8 by. So this is the value of x over here. Now, find the direction of force in the following cases. This is a very good question. Here I have placed the 4 different cases. Okay, just a second. Now guys, take a look. Take a look over here. Find the direction of the instantaneous force. See, in this case, you have got the magnetic field over here, and this is the charge. Okay. See. It is something like this. I'll make you understand. See, you have got a charge over here. You have got a charge over here. This is minus q charge. Okay. And this minus q charge is moving in the downward direction. Okay. This is the velocity. This is the velocity of the minus q charge over here. This is the velocity of the minus q charge over here. And it is moving in the downward direction. And this magnetic field is outward. You are supposed to tell me what is the direction of force. Guys, what are we supposed to do? Place your fingers along the direction of velocity. Okay. And place your fingers along direction of velocity. Velocity is downward. Curl towards magnetic field. Magnetic field is outward. Curl. So thumb is pointing in this direction. So thumb is pointing in this direction. But if this is the force on positive charge, always remember this is the force on positive charge. And when it comes to the force on negative charge, we say force on negative charge will be simply, force on negative charge will be simply the force in opposite direction. Guys, if I am saying force on positive charge is towards right, then consider automatically force on negative charge will be opposite. Here, if I am using the rule, velocity is downward, magnetic field is outward, V cross B, thumb is pointing towards left, but this is a negative charge, make the direction of force opposite. So this will be the direction of force. Let's talk over here. In this case, magnetic field is towards right. This is the charge. It is going up. So place your fingers along the direction of velocity and curl towards magnetic field. V cross B. Thumb is pointing inwards. So I can say in this particular case, this is the magnetic force. Magnetic force is inwards. Let's talk about this question. Guys, see, here I am saying magnetic field is upwards. Here magnetic field is upwards. And charge is moving inwards, cross. Velocity of the charge is inwards. Okay. In this particular case, velocity of the charge is inwards. And I can say over here, if we have to find the direction of force, sir, velocity is inwards, magnetic field is upwards, place your fingers along direction of velocity, curl towards magnetic field, thumb is pointing towards right, but since the charge is negative, so I would say force will be towards left. Let's talk about this question. We say in this question, velocity is outwards, dot, charge is coming out, velocity is outwards. Magnetic field is towards left. So it is V is outwards, V cross B, thumb is pointing upwards. So we say here magnetic force is upwards. So this is the direction of magnetic force in all the four cases. Now take a look at this particular question, at this topic. Motion of a charged particle in a magnetic field. Okay. Now guys, see, let's suppose I am saying you have got this magnetic field over here. And in this magnetic field, you are sending a charge. This is the charge you are sending over here, and I say you are sending it perpendicularly. So this is the velocity, and I'm saying magnetic field is inwards, velocity is forward. What is the angle between velocity and magnetic field? 90 degrees over here. Angle between velocity and magnetic field is 90 degrees. Could you please tell me what is the direction of force? So I say, place your fingers along direction of velocity, curl towards magnetic field. Force will be upward. Force is upward. This is the force. Now guys, this charge is moving in the forward direction. Velocity is upwards. Velocity is upwards. Velocity is upwards. We say velocity is forward, force is upward. Charge wants to go forward, but because of the force, it will be dragged in the upward direction. So it will create its path something like this. It will create its path something like this. It will create its path something like this. So now, when the charge reaches exactly over here, okay? Now, here, the velocity of the charge is something like this. Here, the velocity of the charge is something like this. This is velocity. Magnetic field is inwards. Place your fingers along direction of velocity, curl towards magnetic field. Thumb is pointing towards left. So we say this is the direction of magnetic force over here. Now charge wants to go up, but because of the force, it will be dragged towards something like this. So this will be the path attained by this charge. And when charge reaches over here, charge wants to go forward. Charge wants to go forward. Now magnetic field is inward. This is the inward magnetic field. So place your fingers along direction of velocity, curl towards magnetic field. Force is pointing in the downward direction. So because of this force, it will be deviated. It will deviate its path something like this. Okay, something like this. And when charge reaches over here, it wants to go something like this straight. It wants to go something like this velocity. But magnetic force here is also inward. So it will again drag its path, will make it something like this. Now, don't you think that when the charge is entering the magnetic field perpendicularly at 90-degree angle, it follows the circular path? So I'll just write the same statement. When charge enters the magnetic field perpendicularly, when charge enters the magnetic field perpendicularly, when charge enters the magnetic field perpendicularly, then it follows the circular path. It follows the circular path, or it will perform the circular motion. Okay, and we say in this particular case, I would want you guys to focus exactly over here. In this particular case, see guys, we say due to the magnetic field, magnetic force FB will act. And that magnetic force will be equal to, that is QVB sine theta. Theta is 90, so QVB. And due to circular motion, we know whenever any particle performs circular motion, centripetal force will act on it. We say FC will act on it. Centripetal force will act on it. And I can say that centripetal force will be simply, that is mv square divided by r. This is equation first, this is equation second. And we say here centripetal force will be equal to the magnetic force. When it comes to the centripetal force, it will be mv square by r, which is, when it comes to the magnetic force, it will be qvb. So we say this v and this square will cancel. Okay, and take this over here. So we say r will come out to be, that is mv divided by qb. So this is what we call this is the radius of that circular path. This is the radius of that circular path. Even you can find the velocity also. I can say also as when it comes to the velocity, guys,
Can I say when it comes to the velocity, take this r over here, qbr divided by m. Velocity will come out to be qbr divided by m. This is the velocity of the charged particle. This is the velocity of the charged particle. This is the velocity of the charged particle. Okay? Okay, this is the velocity of the charged particle. Hello? Now guys, see. So this is the velocity of the charged particle. Also, let's talk about the radius in terms of kinetic energy. Radius in terms of kinetic energy. Guys, tell me one thing. We say as when it comes to the kinetic energy, we say 1 by 2 mv square. I would want you guys to multiply with m over here and divide with m over here. We say this kinetic energy will come out to be m into m becomes m square v square divided by, and this will come out to be 2m over here. Now multiply it over here, so it will be m square v square is equal to 2m kinetic energy, 2m ke. Okay, and we say over here this mv will be, take the square over here, it will become under root of 2m ke. Now guys, what is the first formula of radius? R is equal to mv divided by qb. So we say as r is equal to mv divided by qb. We say r will be equal to, what is the value of mv? You can put this as, that is 2m ke divided by, over here we say qb. This is the radius, expression of radius in terms of kinetic energy. Okay, one more thing. We say also, when it comes to the kinetic energy, I would want you guys to remember this expression as of now. We say kinetic energy is also equal to Q delta V. What is this? Q is charge. What is this delta V? We say delta V is the potential difference. Potential difference. Okay, this is also the formula of kinetic energy. Now put it over here. You can say this radius will come out to be under root of 2m. Kinetic energy will be Q delta V divided by, over here, this is QB. This is the value of radius. This is the expression of radius in terms of potential energy, in terms of potential difference, where delta V is the potential difference. Okay, and what is Q? Q is the charge, B is the magnetic field, M is the mass of the charged particle. Okay, let's find one more thing also, time period. We say time period of the charge. Sir, what is this time period? Time period simply means in how much time the charged particle will complete one circle. It is the time in which a charged particle completes one cycle. It's the charged particle in which, it's the time in which a charged particle completes one cycle. One cycle means one complete circle. Now guys, we say as speed is equal to distance upon time. Can I say time will be equal to distance upon speed?
Now tell me one thing. If a charged particle is, we say completing the one circle over here. Okay. Could you please tell me what will be the distance covered by it? Sir, that is circumference 2 pi r. So I can say this will be simply, that is 2 pi r. In one complete cycle, the distance is 2 pi r, distance covered. What is the velocity? Velocity we recently got. Velocity of the charge is qbr divided by m. So I can write over here, this is qbr divided by m. So I can say this time will come out to be, take this m over here, and r will cancel. So this will be 2 pi m divided by, we say, qb. This is the time period. This is the time in which charged particle will complete one cycle. This is the time in which charged particle will complete one cycle. Cool, cool, cool. Yes. Now let's, my dear friends, talk about, okay. Also, if you want to find the frequency, we say frequency is 1 upon time period, inverse of time period. So always remember frequency will be, that is qb divided by 2 pi m. So this will be the value of frequency. Keep this thing in your mind. An ionized hydrogen atom and alpha particle. Guys, when it comes to the ionized hydrogen atom, this means proton. This means proton. And alpha particle, it means helium nucleus. I'll tell you. See, let's talk about alpha particle. Okay. And let's talk about proton. Let's talk about alpha particle. Let's talk about proton. First, we'll talk about their charge, and then we'll talk about their mass. See, this alpha particle, it is made up of 2 protons and 2 neutrons. When 2 protons and 2 neutrons combine, we say they form alpha particle. So, what is the charge on proton? That is, we say charge on proton is E, 1.6 into 10 raised power minus 19 coulomb. 2 protons will be 2e. Neutron is a neutral particle. There is no charge on the neutron. So charge on, we say alpha particle is 2e. But when it comes to the mass, we say mass of proton is, let's suppose, m. So 2 protons will have 2m, 2 neutrons will have 2m. 2m plus 2m is, we say, sir, 4m. Remember this from now onwards. Charge on alpha particle is 2e. Mass of alpha particle is 4m. Charge on proton is E. Mass of proton is m. Now see, an ionized hydrogen atom and alpha particle have the same momentum. What is momentum? Guys, we say momentum P is equal to mv, and it is constant for both. They have got the same momentum. Enters a constant magnetic field. So it is saying that you have got the 2 charged particles. So this is the magnetic field. This is the magnetic field B. 2 charged particles enters the same magnetic field. So this one. Let's suppose this is over here alpha particle. This is over here proton. This is proton and this is alpha particle. They are entering the same magnetic field. And we know whenever the charge enters the magnetic field, it follows the circular path. So this will be the radius of alpha particle. This will be the radius of proton. You are supposed to find what is the radius of, we say, proton divided by what is the radius of alpha particle. This is what you are supposed to say. Guys, tell me one thing. We say as. When it comes to radius, we say it is mv divided by qb. Since we say here, the question says they have got the same momentum. We say mv is same. And they are entering the same magnetic field. We say magnetic field is also same. Magnetic field is also constant. So can I say this radius will only depend upon charge, that is q. So I can say if radius depends upon charge, so I can say radius of proton divided by radius of alpha particle. So it will be simply, sir, 1 upon q. So it will be 1 by e because charge of proton is e, 1 by 2e.
So Rp divided by R alpha will be, take this in the numerator, so this will be 2E divided by E. E and E will cancel, so it is 2:1. It is 2:1. Is this clear? Is this clear? Is this clear? I hope this is crystal and clear to each and every single student. I hope this is crystal and clear to each and every single student. Now let's take a look at this question, guys. Let's take a look at this question. We have got over here a proton and an alpha particle accelerated through the same potential difference, enter in a region of uniform magnetic field with their velocities perpendicular to the field. Compare the circular paths. Compare the circular paths. See guys, this is a good question. I'll make you understand this question also. See, in this case, it says a proton and an alpha particle accelerated through same potential difference. Guys, enters a uniform magnetic field. You have got this magnetic field, and in this magnetic field, it is saying a proton is entering, so it will follow the circular path. Alpha particle is entering, it will follow the circular path. Okay, and I'm saying, let's suppose this is proton over here and this is alpha particle over here. So this will create the radius, that is radius of proton. This will create the radius, that is radius of alpha. We know if they are entering the magnetic field, this will be the, we are supposed to compare their circular paths. What is the radius basically? Ratio of radius we are supposed to find out. Guys, see. When it comes here, it is mentioning in the question, they are accelerated through the same potential difference. Means delta V in this case is constant for both, same. Enter in a region of uniform magnetic field. Both are entering the same magnetic field, so magnetic field is also constant. Okay. Now, tell me the formula of radius in which potential difference is present. I recently told you this is the formula of radius in which potential difference is present, and we'll be using the same formula. We say as we know. Can I say in this particular case, I'll say a radius will be equals to, that is, we say under root of, we say 2m q delta v divided by, we say qb. 2m q delta v divided by, we say qb. Yes. Now guys, I would want you guys to make it bit simple over here. We said delta v is constant, magnetic field is constant, so we say this radius will be proportional to, I can say under root of m remains, sir, mass of the proton and alpha particle is definitely different, so mass is different and charge is different. Okay, mass is different and charge is different, divided by this charge q. Rest 2 is constant, delta v is constant, magnetic field is constant. Now this q is in the numerator, denominator, it doesn't look good. Do one thing, multiply with root q and divide with root q, one and the same thing. Now this root q and root q becomes q. Okay, because we say root q into root q becomes root q whole square. This and this will cancel, it will come out to be q. So this q will cancel with this q. So radius will be proportional to root m by root q. That is root m divided by root q. Now guys, tell me one thing. We have to apply the same equation. Now, can I say in this particular case, when it comes to the radius of proton divided by radius of alpha particle, so it will be equals to, guys, root m by root q. So can I say in this particular case, this will be under root of, for proton mass is m and for proton charge is e, m by q divided by, we say under root of, for alpha particle, I can say mass is 4m and for proton
For alpha particle charges, we say 2e. So we can write it something like this, under root of m by e into under root of, if you take in the numerator, it will become 2e divided by, we say 4m. Okay. Now, this e and e goes. Okay. So I can say this rp divided by r alpha will come out to be. Now here this e, this m, this m. So it will become under root of 2 divided by root 4, that is 2. Now, can I say in this particular case, multiply with root 2 and divide with root 2? So root 2 into root 2, do the rationalization, that will become 2, and this 2 and this 2 will cancel. So it will come out to be 1 divided by root 2. So this is the correct ratio and this is the difference. I hope this is crystal clear to each and every single student out there. Next, let's talk about this one. This is charged particle projected at an angle theta from the magnetic field. Charged particle projected at an angle theta from the magnetic field. Guys, we discussed all the cases. When theta is equal to 0, magnetic force is 0. When theta is equal to 180, magnetic force is 0. When theta is equal to 90, magnetic forces in that case, particle follows the circular path. Now, let's talk about if, I'll just mention over here, if we say particle is projected at some angle, that is, this is the charge over here. This is the charge over here, okay? And you are sending the charge something like this with a velocity v. And magnetic field over here is this, that is b. Such that it is creating the angle with the magnetic field as theta. This angle is given as theta. Guys, don't you think that if the charged particle is sent at some angle, we say here, this velocity will have two components. This will be v cos of theta and this will be v sine of theta. Now, because of v cos theta, the charge will move forward. Because of this forward velocity, charge will move forward. And because of this v cos theta, see, this v sine theta is perpendicular to the magnetic field. Whenever the velocity is perpendicular to magnetic field, charge performs the circular motion. Because of this v sine theta, this charge will perform the circular motion. It will follow the circular path. Because of this v cos theta, charge will move in the forward direction. So what will be the resultant path? Because of v sine theta, it is performing the circular motion. Because of v cos theta, it is moving forward. So the resultant path will be the helical path. It is moving in the circle as well as it is moving forward. So I can say the resultant path in this particular case will be something like this. This is what we call the helical path. So I can say due to v sine theta, which is perpendicular to magnetic field, charge follows circular path. Charge follows circular path. And then I'll write over here due to v cos theta, charge moves forward. Charge moves forward. So I can say resulting in the helical path. So I can say resulting in the helical path in this particular case. Okay. Now when it comes to the radius, now guys, let's talk about radius of the circle. Now let's talk about a radius of the circle in this particular case. Let's talk about radius of the circle in this particular case. What is the see, if it is following the circular path, what is the value of radius? Guys, we say as when it comes to the radius, you say, sir, radius is mv divided by qb. This is the general formula of radius. But here, if you check, this radius is being created because of v sine theta. Because v sine theta is that velocity due to which it follows the circular path. So I can write over here radius in this case will be, that is m v sine of theta. Then we say divided by qb. Because of this, it would follow the circular path. So that's why I'll just write over here v sine theta. Okay. And my dear friends, when it comes to the time period, guys, we said time period was, that is 2 pi m divided by what was that? I forgot. 2 pi m divided by qb. 2 pi m divided by qb. We say that is qb. We say 2 pi is same over there, 2 pi is same over here. Mass of the charge will remain the same in both the cases. Sir, charge will remain the same in both the cases. Magnetic field here is B, over there also it was B. But when it comes to the velocity here is V sine theta. So we said time period will remain same because all the quantities in the time period remain same. So can I say, we say time period remains the same. Remains the same. And when it comes to the frequency, so frequency will be, that is qb divided by 2 pi m. It will also remains the same. Remains the same. Remains the same. So, and one more thing we discuss over here, that is pitch. We discuss over here pitch. What is pitch? What is pitch? What is pitch? I'll tell you what is pitch. We say it is the horizontal. It is the horizontal distance covered. It is the horizontal distance covered in one rotation. It is the horizontal distance covered in one rotation. Means if see guys, if a particle is performing the circular motion, so it is not only performing the circular motion, but it is moving forward. In case of the helical path, we say the particle is creating the circle as well as moving forward. If I say it is complete, see, it started from here, it is completing the circle over here. Okay, so in this one cycle, one rotation, one complete cycle, how much it has moved the horizontal distance? How much it has moved the horizontal distance? That is pitch. And when it comes to this pitch, how do we find this pitch? See guys, we say this pitch or horizontal distance is simply, that is velocity, horizontal velocity, that is v cos of theta into time, because distance is speed into time. And because of v cos theta, it is moving forward. That's why I'm taking v cos theta. Into time period, time will be the time period. So we can say this pitch will be, that is, time period will be simply, that is 2 pi m divided by, we say qb, and then we say v cos of theta. Then we say v cos of theta. I hope this is crystal clear to each and every single student. Okay. So this is what we call the pitch in this particular case.
Now we have a question over here. A beam of protons with a velocity of 4 into 10 raised power 5 meter per second enters a region of uniform magnetic field of 0.3 Tesla. Let's suppose we have got a proton over here, okay? And this proton is entering with a velocity of v is equal to 4 into 10 raised power 5 meter per second, okay? At an angle of we say 60 degrees, at an angle of 60 degrees. In a magnetic field, what is the magnetic field? In a region of uniform magnetic field of 0.2 Tesla, 0.3 Tesla, okay? Now guys, in this particular case, if I say, and then further it says, find the radius of the helical path. We are supposed to find the value of r by the proton beam and pitch of the helix. We are supposed to find the radius and pitch. See guys, if this proton is entering with the velocity 4 in 10 raised power 5 meter per second, we said this velocity will have two components. First one is this, second one is this. This component will be v cos of theta, and this will be v cos theta. How do we find this v cos theta? V is 4 into 10 raised power 5 cos theta, that is cos of 60. Cos 60 is 1 by 2. So 1 by 2, 2 will cancel. So 2 into 10 raised power 5 meter per second. And this component will be v sin theta, v sin 60. So what is v? V is 4 into 10 raised power 5. Sin 60 is a root 3 by 2. And then, my dear friends, I can say over here, 2 1s are 2 2s are 4. So it will become 2 root 3 into 10 raised power 5 meter per second. So this is the value of v sin theta. This is the value of v cos theta. Let's first find the radius. Guys, we say as when it comes to radius, we say that is m v sin theta divided by, we say, qb. Okay. You got the value of v sin theta, and then you have got the mass of the proton in this particular case. Okay. And along with that, you have got Q and B. What is Q? Q is the charge on a proton. B is the magnetic field. So just put the values. R will come out to be. What is the mass of a proton? We say it is 1.67 into 10 raised power minus 27. Mass of a proton is 1.67 into 10 raised power minus 27 kgs. V sin theta. What is the value of V sin theta? That is 2 root 3 into 10 raised power 5 meter per second divided by, what is charge? What is charge over here? Charge on proton, we know, sir, that is 1.6 into 10 raised power minus 19 coulomb. Then magnetic field is given over here 0.3 Tesla. And here in this case, the radius will come out to be, we can say, 1.2 centimeters. Radius will come out to be 1.2 centimeters. And then if we talk about the pitch, we say as, when it comes to the pitch, that will be simply 2 pi m divided by qb, and then when we say v cos of theta. Recently we got the value of pitch, 2 pi m by qb into v cos of theta. Now pitch will come out to be 2 pi. Pi is 3.14. Mass of the proton is 1.67 into 10 raised power minus 27. And v cos theta, what is the value of v cos theta? 2 into 10 raised power 5. We say 2 into 10 raised power 5. Then we say divided by qb. Q is 1.6 into 10 raised power minus 19 coulomb. And B is the magnetic field, that is 0.3. Okay. So this pitch comes out to be equals to, solve it. Okay. I'll just directly write the answer, that is 4.4 centimeters over here. So it is 4.4 centimeters over here. Just you have to do one thing in this particular case. You have to resolve the velocity in two components. Once you are done with that, you would be able to find pitch and this. And one more question you have over here. Two particles A and B of mass MA and MB respectively having the same charge are moving in a plane. A uniform magnetic field exists to this plane, perpendicular to this plane. Let's suppose this is a uniform magnetic field over here. This is the uniform magnetic field over here. Okay. And in this uniform magnetic field, this is the path of A particle. Okay. This is the path of A particle. This is the path of A particle. And this is the path of B particle. This is the path of A particle and this is the path of B particle. Now, it says that in the question, the speed of this particle is VA. Okay, it is moving in this path. The speed of this particle is VB. And it says here, have the same charge moving in the plane. A uniform magnetic field exists perpendicular to the plane. Okay. Speed of the particle are VA and VB respectively. The trajectories are shown in this particular case. Guys, see, don't you think that the radius of this path will be smaller than the radius of B path? I am saying here, radius of A is less than radius of B. Radius of B particle is bigger. Now tell me, as when it comes to radius, we say, sir, it is MV divided by QB. Now, if you check the question, both are in the same magnetic field B. Both are in the same magnetic field B. Magnetic field is same. And both have got the same charge. We say Q is same. Same for both. Now, I can say radius is directly proportional to mass into velocity. The one which has more radius will have more momentum, M into V. So I can say in this particular case, M A V A is less than M B V B. Simply, this was the relation we were supposed to calculate over here. Basically, there were four options given. MAVA is equal to MBVB, MAVA is less than MB, and then you are supposed to mark this option as correct option. Okay. So this was basically about the force on a charge placed in a uniform magnetic field. Force on a charge placed in a uniform magnetic field. Okay. Now guys, let's take a look exactly over here. We have got the next topic, that is what we call the force on a wire. Force on a wire. See guys, when it comes to force on a wire, and I'll just write force on a wire placed in a magnetic field. Force on a wire placed in a magnetic field. So now let's talk about this topic. Okay. Let's suppose I have got a magnetic field exactly over here in this region. Let me just show you. I have got the magnetic field over here in this region. This is the magnetic field. Yes. And what is the value of this magnetic field? Let's suppose this is B. And in this magnetic field, we are actually placing what? We are placing a wire over here. We are placing a wire over here. Okay, this is a rod or a wire. And when it comes to this wire, we say current I is flowing over here. Current I is flowing in this wire. I is the current flowing in this wire. And length of the wire is L. Length of the wire is L. So it is placed in the magnetic field. So guys, always remember, whenever we place a wire in the external magnetic field in which current is flowing, we say force acts on it. We say whenever, I'll just write over here, whenever a wire carrying current I is placed in an external magnetic field, it experiences force. Okay. And if you ask me, what is the value or what is the magnitude of that force? I'll just say magnitude of that force is simply F is equal to, that force will be F is equal to, we say I is the current flowing, I into L cross, we say B, I into L cross B. Now, if you ask me, what is this I? I is the current flowing in the wire, L is the length of the wire, and B is the magnetic field in the wire. Okay, B is the magnetic field in which wire is placed. Now, guys, I can also write it something like this. F is equal to, we say, sir, this is I. And L cross B, we can write, this will be LB, and then we say sine of theta. LB sine of theta. Okay, because L cross B is LB sine of theta, A cross B is AB sine of theta, where theta is the we say angle between we say L and B, where theta is the angle between magnetic field and length, Okay, now guys, listen to me very carefully. One more thing, if you ask me, sir, what is the direction of the force over here? I'll just write direction of force. See, guys, like previously when we were placing the charge in the external magnetic field and charge was moving with some velocity, over there we used to calculate the direction of, we used to find the direction of force. How? We say place your fingers along the direction of current, curl towards magnetic field, thumb gives the direction of magnetic force. Now see here, I say place your fingers along the direction of current. If current is upward, place your fingers along the direction of current. Curl towards magnetic field is inward, so I say from current to magnetic field. Thumb is pointing towards left, so that will be the direction of magnetic force. I'll say place your fingers along current. Then curl towards magnetic field. Then curl towards magnetic field. Thumb gives the direction of magnetic force. Okay. In this case, it is from I to B, that will be towards left. Now, my dear friends, I just want to show you one thing over here. One small thing over here. What is that? If I say, if theta is equal to 0 degrees, let's suppose this is the magnetic field over here, okay? And in this magnetic field, this is the wire placed, which has got length L, and this is the direction of current over here. Don't you think that length and magnetic field, if you say theta is equal to 0 or 180 degrees, guys, here length and magnetic field are parallel. If you consider the length along forward direction, positive x-axis, then we say theta is 0. What will be the value of magnetic force in that case? Magnetic force will be, that is ILB sine of 0 degrees. So that will come out to be 0. If theta is equal to 180, in that case, magnetic force will be ILB sine of 180. Sine 180 is also 0, so this will also come out to be 0. So when theta is 0 and 180, then in that case, we can say magnetic force will be 0.
one more thing I just want to tell you over here. What is that? What is that? Let's suppose if I ask you, find the force on the given wire, on the given wire. Okay. In this particular case, my dear friends, the wire is, this is the magnetic field present over here. This is the magnetic field B. And in this magnetic field, I am placing a wire that is something like this. This is the wire which is placed in the magnetic field, something like this. And the length of this is the radius. Radius of this semicircular wire is given as, let's suppose it is R, and current in this case is I. And when it comes to the structures which are not straight, in that case, I would recommend you guys to take the effective length. I would recommend you guys to take the effective length over there. And when it comes to effective length in this particular case, you say L effective will be join the initial point with the final point. That will be, we say, sir, what? L effective. This is L effective. And L effective is R plus R, and that will be over here 2R. L effective in this case is 2R. So here, when it comes to the magnetic force, you say magnetic force will be simply, that is I L B sine of. Guys, what is the angle between effective length and magnetic field? Angle between effective length and magnetic field. Effective length is along x-axis, magnetic field is inward. So I guess angle between these two is 90 degrees exactly over here. Yes, so I can say this is 90. And when it comes to the effective length, don't you think effective length in this case is 2R? R plus R will be 2R. So I can say magnetic force will be over here. That is I 2R into, we say, sir, B. This will be the value of magnetic field in this magnetic force in this particular case. Yes, this was the value of magnetic force in this particular case. Now guys, next thing over here is, let's suppose if somebody asks you the question something like this. Find the net force on the wire. Find the net force on the wire. Let's suppose that not on the wire, on the square loop, You have got a square loop which I have placed in this external magnetic field. This is the external magnetic field that I am showing over here. Okay, and in this external magnetic field, you are placing this square loop. Okay. Now guys, and its side is L. Current in this square loop is flowing as I. It will flow something like this. Now, when I ask you to find the magnetic field in such case, in this case, you simply say, guys, listen to me very carefully. You simply say, over here, magnetic force will be, guys, we say this is made up of 4 wires. Don't you think that when it comes to the magnetic force on 4 wires, let's find the direction. What will be the, see. If I tell you find the magnetic force on this wire, you say, sir, ILB sine theta. Theta is 90, ILB. On this also it will be ILB. Now the question is direction. Guys, see, force on this wire will be, place your fingers along the direction of current, curl towards magnetic field. Thumb is pointing in the upward direction. So I can say this will be the direction of magnetic force. Yes. Now, when it comes to this wire over here, we say force on this wire will be, place your fingers along the direction of current, curl towards magnetic field. It is pointing towards left. So force on this wire is towards left. This is magnetic force. Similarly, when it comes to this, we say force on this will be in the downward direction. Okay. And similarly, if you check force on this, it will be something like this. Guys, why? Because current is flowing something like this, curl towards magnetic field, it's towards left. Don't you think that this force is opposite to this force? Yes, and they are equal, they will cancel out. This will cancel out with this one. So I can say net force in this particular case is 0. So from now onwards, if you ever see the closed loop placed in the external magnetic field,
Okay, we say in that case, net force comes out to be equal to 0. Now, guys, let's move on to an important question that we have exactly over here. One of the beautiful questions. See, a square of side 2 meters. You have got a square over here. Its side is 2 meters. Its side is 2 meters. Is placed in a uniform magnetic field of 2 Tesla. This magnetic field is given as 2 Tesla. In the direction perpendicular to the plane inwards. Equal current of 3 ampere flows. Guys, this is the direction of current over here. This is the direction of current over here. In this current is direction something like this, something like this, something like this. We are supposed to find the net magnetic force on this loop. Since, sir, you said when it comes to the closed loop, we say net force on a closed loop is always 0. But here, that is when you have the loop and current flows in a unique direction, it goes something like this in the anti-clockwise direction over here. But if you check over here, in this wire, current is going clockwise and here current is going anti-clockwise. So net force in this case will not be equal to 0. Let me just tell you. Guys, this structure is basically made up of 3 parts. This is the first part, this is the middle part, and this is the lower part. Let's find the force on upper part. Force on upper part. If we find out force on this upper part, guys, listen to me very carefully. It is something like this. Don't you think that whenever you have the structure something like this, you take its effective length. So I would want you guys to take its effective length. Okay. Now, guys, if I say this side is 2, what will be the length of this diagonal? Obviously, it will be root 2. If this is A, this will be root A. And what is the diagonal? Now, guys, we said this is the effective length and this will be the direction of current. Because if the current is flowing something like this, from right, we say this point to this point, okay, from left to right, something like that. So here also current will be flowing from left to right, same. Now, magnetic field is inwards. What will be the direction of force on this one? Guys, you say, place your fingers along the direction of current, okay, and curl towards magnetic field. Force is something like this. So this will be the direction of force. And this is the direction on its effective length. Means I'm saying this will be the direction of force on the original part. This is the direction of magnetic force. And if you ask me, what is the value of this magnetic force over here? You say, sir, this magnetic force will be, that is IL, this will be ILB and sine 90, that is ILB. Okay. Now, let's take a look at the middle part. I'll say force on the middle part. Let's talk about force on the middle part. Now guys, middle part is this one. So we say simply, sir, force on this will be, sir, in this direction only, So this will be so this is the middle part. So force will be in this direction only. And what is the direction of force? That is ILB. And when it comes to L is the length of this one. L we are taking over here as this length, that is root 2 of what is the side over here given as? What is the side over here given as? That is 2. So 2 root 2 of 2. Okay. And in this case, sir, what I am supposed to take this length? Same, because we are taking the L effective over here. L effective. So that will be root 2. Okay. So here also on this force will be, that is I, L, and this is B. Then let's talk about this force on this part. We say force on lower part. Force on lower part. Now guys, when it comes to the lower part, I'll make it something like this. So we say here also we have to take the effective length. So that will be also the middle wire, middle length. And that is 2 root 2. Okay, and this is the direction of the current. If this is the direction of the current, similarly, you have to make the direction of the current here. Now tell me, what is the direction of force? Place your fingers along direction of current, curl towards magnetic field. Thumb is pointing in the upward direction. So this is the direction of magnetic force. And here also, this magnetic force will come out to be current. That is 2 ampere. How much? We say 3 ampere. L, length over here is 2 root 2.
and magnetic field in this particular case, so I'll write just directly ILB. Now see, force on all the three wires is same, so on this wire also we say magnetic force is something like this. Okay, magnetic force is something like this. So don't you think that these three forces will not cancel out over here? Why? Because they are in the same direction. So I can say net force in this case will be, that is 3 times of F, and that is 3 times of ILB, and I can say over here that will be 3 into current in this particular case is how much? Current in this particular case is 3 ampere. Okay, length of this is in this particular case that is 2 root 2. Okay, and magnetic field in this case is that is 2 Tesla. Now 3 into 3 is 9, 9 twos are 18, 18 twos are 36, so we say this is 36 root 2 Newton. This will be the value of net force in this particular case. I hope this is crystalline clear. Okay, then you have got a structure something like this. Guys, see, a straight wire of length 30 centimeter. This is a straight wire which has length 30 centimeter. And mass is 60 mg. Okay. And lies in the direction 30 degree east of north. This angle in this case is given as 30 degree over here. The magnetic field, sir, the Earth's magnetic field, what is this? Nothing. The magnetic field at the site is horizontal and has a magnitude of 0.8 Gauss. So this magnetic field, this is the direction of magnetic field. Okay, guys, it is something like this. This is the magnetic field in which wire is placed, and this magnetic field in this particular case is given as 0.8 Gauss. Okay, it's not in Tesla, it's in Gauss. And when a current of, we are supposed to find the current. What must be the current passed through the wire so that it floats in the air? It says that what should be the value of current in this wire so that it floats in the air? Floats in the air means the value of upward force should be equal to the value of downward force. Then only it will remain in the air. If downward force becomes more, it will fall down. If upward force becomes more, it will go up. So we say in this particular case, simply, we are supposed to find the value of current over here. Okay. Yes. Now guys, when it, see. First and the foremost thing is, we say the wire should be in the equilibrium. The wire should be in the equilibrium. Means upward force should be equal to downward force. So now tell me, what is the force in the upward direction? Guys. In the downward direction, it has mg. And in the upward direction, don't you think magnetic force will act? Guys, what is the direction of magnetic force? Magnetic field B is something like this. This is the direction of magnetic field, kind of inwards. Okay. And we say length rod is something like this. Current is flowing something like this. Guys, see, we say if you go from current to magnetic field, okay, I say I to B. Thumb is pointing in the upward direction. So upward will be the magnetic force over here. And when it comes to the magnetic force, we say here magnetic force should be equal to, we say, sir, mg. And what is the value of magnetic force? That is ILB sine of theta should be equal to mg. Because condition, they are saying that it should remain in the equilibrium. So I can say in this particular case, this current will come out to be, and here I can write this is mg divided by, so we say this is LB sine of 30 degrees over here. Now you are supposed to put the values in this particular case. What is the mass over here giving? Mass is given as 60 mg. So if you convert it into the kgs, it will be 60 into 10 raised power minus 6. Okay. So we say this will be simply, instead of mass, this will be 60 into 10 raised power minus 6. Okay. And acceleration due to gravity is 9.8 meter per second square. or you can take it 10 also. Directly take it. It is saying take G as 10. Okay. And divided by length into magnetic field. Okay. Okay. Length is given as 30 centimeters. So 30 into 10 raised power minus 2. Because it's in the centimeter, converting to meter, multiply with 10 raised power minus 2 multiplied by, sir, magnetic field is in Gauss. If you convert in Tesla, so 0.8 into 10 raised power minus 4. Okay. And sine theta is 1 by 2, that is 0.5. Okay. And if you solve this, I should come out to be equal to, that is 50 amperes. So this is the answer to this particular question. Next question we have over here. Now, guys, look at this. When it comes to this question, in the figure shows a semicircular loop. Okay, you have got the magnetic field over here, and then you have got this semicircular loop in which your current is flowing something like this, and it is complete loop. It is not over here open from the bottom side, from the lower side. It is a full semicircular ring, and current is flowing something like this. I have told you previously that if a current on this loop, guys, let's find the value of force on this upper part. Current, see, when it comes to the upper part, we take its effective length, that will be this much. Let's find the direction of force. Sir, for this is the direction of current. Curl your fingers from current to magnetic field. Thumb is pointing in the upward direction. So we say force on this will be upward. And what is the force on this part, upper part? I'll just write over here, force on upper part. Guys, tell me. We say force is equal to, F is equal to ILB sine theta. Theta is 90. Why? Because length is in the x-axis, magnetic field is in the z-axis. So angle is 90. ILB. So what is the current over here? That is 2. What is the length over here? Effective length of this one will be, that is, guys, if radius is 1, if this is 1 meter, this is 1 meter. So 1 plus 1 is 2. So 2 into 2. Okay. And ILB. What is B? ILB. What is the value of current? Current is 2. Okay. And this length is 2 and magnetic field is 1. So 2 into 2 into 1. So force in this particular case will come out to be 4 Newton. Now let's talk about the force on this lower part. Guys, current is flowing towards left. Place your fingers along direction of current, curl towards magnetic field, thumb is pointing in the downward direction. Don't you think that in this particular case, force on this will be in the downward direction? And I can write over here, force on lower part. I say force on lower part. And that force will be also how much? 4 Newton. Because ILB, current is 2 ampere, length is 2, 2 into 2 is 4. And we say upward, for this is in the upward direction, this is in the downward direction. So could you please tell me? So I can say net force in this case will come out to be 0. So this is for this loop. Let's talk about loop 2. In second loop, let's talk about this loop. Now guys, tell me one thing. When it comes to this loop, we say current is flowing something like this. See. Okay, this and this. Now, here. Listen to me very carefully. I say force on this will be in the upward direction. Force on this part will be also in the upward direction. So this is F and this is F. And effective length of this is this only. So in this particular case, I can say net force will be equal to 2F. And I can write over here 2F, that is I, L and B. And I can write 2 into, what is the value of current in this particular case? That is, current in this case is, that is 2 ampere. Okay. And length over here is 2 meters. Magnetic field is 1. So it will come out to be 8 Newton. Net force is 8 Newton. Individually on this is 4. 4 plus 4 is 8. Next, let's talk about this one. This is also a very good question. See guys, in this case, it says that
A PQ wire of mass 10 grams. You have got a wire over here. This is the wire, PQ wire of mass 10 grams, is at rest on two parallel metal rails. It is at rest on two parallel metal rails. These are the metal rails. Okay. The separation between the rails is 4.9 centimeter. This separation gap is given as 4.9 centimeter. Okay. A magnetic field of 0.80 Tesla. This magnetic field is given as 0.80 Tesla. Okay, is applied perpendicular to the plane of two rails. This is something like this. Okay, the resistance of the circuit is slowly decreased. This is a kind of circuit, you can say. Guys, see here. This is a circuit. Battery is connected. You have got resistance over here. Okay, so this is a kind of complete circuit. And it says that over here, it says that a magnetic field of 0.80 Tesla is up. Okay, the resistance of the circuit is slowly decreased. This resistance of this circuit is not constant. It is changing. It is slowly decreased. That's what it is saying. It is slowly decreased. Okay. When the resistance decreases to below 20 ohm, when resistance becomes 20 ohm, the PQ wire begins to slide. This wire begins to slide. It starts sliding. It starts moving. Okay. The PQ wire begins to slide. Calculate the coefficient of friction. Guys. When the wire is about to slide, or when the wire begins to slide, it has not started sliding yet. It has not started moving yet. It is about to slide. It is about to move. So then, in that case, then the resistance is at that point, resistance is 20 ohm. And when the wire is about to slide, don't you think that at that point of time, the forward force on this wire will be equal to the backward force? Sir, when this wire starts sliding, when it is moving, in that case, we say forward force will be greater than backward force. But when it is about to slide, it has not slided yet. It's about to slide. Forward force equal to backward force. See. What is the forward force over here? This is the battery connected. So current always move from positive terminal. It comes out of the positive terminal. So this is the direction of current in the wire. Now, if current is downward, magnetic field is inward. So we say it is I cross from I to B. Curl your fingers from I to B. So this will be the direction of magnetic force. This will be the direction of magnetic force. So force on this wire towards right is magnetic. And if this magnetic force is forward, rod wants to slide in the forward direction, we say friction will act in the backward direction. Friction will act in the backward direction. Okay? So we say here, and when the rod is about to slide, we say this friction is equal to, that is magnetic force in this case. Friction is equal to magnetic force in this case. Yes. Now guys, can I say when it comes to the friction, what is the value of friction? We say, sir, it is mu mg. Mu into n is equal to, what is the value of magnetic force? That is, sir, I, L, and this is B. I, L, and this is B. Okay. Yes. And could you please tell me what is the value of mu? Mu will come out to be, sir, I, L, B divided by M into G. That's it. We are done with the question. You were supposed to calculate the coefficient of friction between the wire and the rod, between the wire and the rails. Okay. And now you can put the values in this particular case. Put the value of current over here. Current in this case is given as, okay, where is the current? Okay, current you can find in this particular case. How to find the current? We say current is I is equal to V divided by R. V is given and resistance is 20 ohm. So you can say V divided by R. This is LB and divided by, we say, M into G. Now V is how much? 6. R is 20. L is given in this particular case as length. Length of this wire is given as 4.9 centimeters. Okay. Magnetic field is given as 0.80 Tesla. Mg. M is given as mass of the wire is given as, where is mass? 10 grams. Okay.
Okay, convert to the kgs, 10 into 10 raised power minus 3. G is 10 meter per second square. So you can put the value. I'll just directly write the answer over here. Just do the calculations from your end. So I'll say this mu will come out to be 0.12. So it is 0.12. Keep this thing in your mind. Just you have to put the values now. Next, we have got this question. See, the magnetic field existing in a region given by B is equal to B naught x by L plus x square by L square into K cap. A square loop of L. Guys, see. My dear friends, my dear NEET aspirants, what I'm trying to say is that you have got a square loop over here. Okay? And in this region, magnetic field is present. What is the value of magnetic field? That is B naught. Okay? And then we say x divided by L plus x square divided by L square. This is the magnetic field. And this magnetic field is present in this region and it is varying with x. It is not constant. See, when x is 1, magnetic field is 1 by, let's suppose when x is 1 by L plus 1 square by L square into B naught. This will be the magnetic field. If x is 2, put the value of x2 over here, magnetic field will change. Okay. You are supposed to find in this case, in this magnetic field outward, which is in the outward direction, a loop is placed over here. We say this is the direction of current in the loop. This is the direction of current in the loop. You are supposed to tell me, what is the net force on the loop? You say, sir, current is flowing something like this in a proper loop. So we say net force on this should be 0. No. Here magnetic field is different. On this, here magnetic field value is 1 and here magnetic field is value is different. So we say force on this wire will be something else. Okay. And force on this wire will be something else. It will not be same. Keep that thing in your mind. Force, value of force here will be different. So that's why force will not cancel each other. Now guys, one thing I just want to say, let's talk about force on AB wire. See guys, we say force on, first let's find the magnetic field. Magnetic field at, see, we say, write it something like this, force on AB wire, force on AB wire. We are supposed to find force on this AB wire. So could you please tell me what is the force? We say, sir, force is I, L and B. And what is the magnetic field, value of magnetic field here? I say here, x is equal to 0. We say at x is equal to 0 because this is the origin. At origin, x is equal to 0. This wire is present at x is equal to 0. Could you please tell me what is the magnetic field? We say magnetic field will be, this is B naught. Put x is equal to 0. 0 by something is 0. 0 by something is 0. 0 into this magnetic field will come out to be 0. So can I say force will come out to be 0? So means force on this part of the wire is 0. Cool? Yes. Now let's talk about force on this part of the wire. Let's talk about force on this part of the wire. We say, I'll just write over here, force on CD wire. Guys, at here, at x is equal to, could you please tell me CD is present at what distance from the origin? L distance, because it's L, x is equal to, at x is equal to L. So magnetic field will be, this is B naught. Put x is equal to L. This will be L by L plus L square by L square. That is 1 by 1 plus 1 by 1. That is 2. So magnetic field will come out to be 2 times of B naught. So can I say force in this case will come out to be, I, L, B, and F is equal to, we say I, L. And what is the value of magnetic field? That is 2 times of B naught. Okay. Now we got the force on CD wire. We got the force on AB wire. Could you please tell me what is the force on BC and AD? See here in this particular case, we say force on BC is equal to force on AD. Guys, because they are parallel to each other. Here. No doubt this is, see. If you take this point of the wire over here, it is at some distance, let's suppose 2 meters. Similarly, this point of the wire is also at 2 meters. So force on this will be exactly same as the force on this wire. Here it will be in the upward direction, here it will be in the downward direction. So we say force on this part of the wire is upward. Force on this part of the wire is downward. We say these two will cancel each other. And force on BC is equal to force on AD and are opposite. So they cancel each other. So guys, force on this part of the wire will cancel with this one. Force on this part is 0. What remains? So net force is this. So I can say net force in this case will be, that is IL 2B0. This is the answer in this particular question. Cool. I have shown you enough number of questions in this topic. Let's move on to this one. Let's move on to this one. Okay. See guys. Let's suppose you have got a wire over here. This is a wire. Okay. This is infinitely long. And current in this wire is, let's suppose, I1. And let's suppose you have got one more wire over here. And current in this wire is, we say, sir, I2. Length of this is L. Okay. And distance between these two wires is, let's suppose, we say, sir, R. Guys, tell me one thing. These two wires are placed parallel to each other. Don't you think that? We say, because of this wire, magnetic field will be present over here. Why? Because whenever the current flows through the wire, it creates the magnetic field. We say because of this wire, magnetic field here, I call that as B1. And how to find the direction? Place your thumb along the direction of current, curl your fingers. So when you curl it, it will be inwards. So magnetic field here will be inwards, B1. Okay. So I can say over here, due to the wire 1, magnetic field is present. Magnetic field is present at R distance. And don't you think that in that magnetic field, this wire 2 is placed? In which wire 2 is placed? Yes. Now guys, one thing I want you to understand. What is that? We say whenever a wire is placed in an external magnetic field, in which current is flowing, we say it experiences force acts on it. So force will act on, we say, wire 2. And what is the value of that force? We say F is equal to, that is ILB sine theta. Theta is 90 over here. Magnetic field is inward. Wire is in y-axis, so 90 degrees. And now, I say this is the force on wire 2, on this wire 2 is equal to. And my dear friends, listen to me very carefully. We say force on this wire 2 is simply, that is current in this wire. You have to take now current of this wire, that is I2. Length of this wire is given as L. And magnetic field here, that is this magnetic field. Yeah. Tell me, how much is the magnetic field due to B1? Sir, magnetic field due to wire 1 is mu naught I1 divided by 2 pi R1. Because due to an infinitely long wire, magnetic field at R distance is mu naught I1 divided by 2 pi R. And here I can say this will be over here, that is mu naught, we say I1 divided by 2 pi R. So I can say this force F2 will come out to be, so can I say this is mu naught I1 I2 divided by 2 pi R into, we say, sir, L. Okay. Yes.
Yes. Mu naught I1 I2 divided by 2 pi r into L. Okay. Now, so we say this is the force on wire 2 due to wire 1. This is the force on wire 2 due to 1. Now guys, listen to me very carefully. This is the net force on wire 2 due to wire 1. If somebody asks you to find the force per unit length, force per unit length. What is force per unit length? That is total force divided by total length. So I can say that is force on the unit length of this wire. So I can say what is the force value of force over here? That is mu naught. We say I1, we say I2 divided by, we say 2 pi r. And then you have over here L. This is the net force. Divided by total length. What is the total length of the wire? That is L. L and L will cancel. So force per unit length will come out to be force per unit length. Length will come out to be mu naught I1 I2 divided by 2 pi r. So this will be the force on the unit length or force per unit length. Okay. Yes, sir. This is the force per. And in the maximum questions, we are supposed to find the force per unit length only. Okay. And when it comes to the total force, guys, always remember in this case, when it comes to the total force, they will give you the infinite wire over here. Another one will be the finite wire. But if they ask you the force per unit length, in that case, you can take finite wires. Both the cases you can, in both of the two wires, you will be taking over here as finite. Okay, there is no problem in that. But when it comes to the total force, we say one wire you have to take infinite in that case, because then only you can mention the magnetic field due to an infinite wire, something like this. Okay, now guys, listen to me very carefully. Listen to me very carefully. Let's find the direction of force. We say direction of force on this one will be, how to find the direction of force? Place your fingers along direction of current, curl towards magnetic field, thumb is pointing towards left. So we say this is the direction of magnetic force. Okay. Now, don't you think that, guys, listen to me very carefully. Listen to me very carefully. If I say you have got this wire over here in which I1 current is flowing, you have got this wire over here in which I2 current is flowing. Because of this wire, magnetic field here is inwards. This is B1. Now, in this magnetic field, this wire I2 is placed. So this will experience force. Place your thumb along direction of current, curl towards magnetic field. Thumb is pointing towards left. This is the direction of magnetic force. Now, one more thing. We say, because of this wire, magnetic field is present over here. Place your thumb along direction of current, curl your fingers. So due to I2, magnetic field here is outwards. This is B2. Now in this B2, this wire is placed. In this B2, this wire is placed. And don't you think that now this will experience force? Yes. How to find the direction of force? Guys, place your fingers along direction of current. Curl towards magnetic field. Thumb is pointing left. Thumb is pointing left. So this will be force on wire 1. So from now onwards, you will remember that if the current flowing in the two wires, if the current flowing in the two wires are in the same direction, guys, if the current flowing in the two wires are in the same direction, then the two wires attract each other with magnetic force. Then two wires attract each other with a magnetic force. On this wire it is towards left, on this wire it is towards right. So they are attractive. The force will be attractive in nature. I hope this is crystal clear to each and every single student whosoever is watching this. Okay. Now, let's talk about this one. This was the question which was asked in NEET 2017. See, you have got a wire. I'll make the new figure. This is the wire over here. This is wire B. And this is wire over here. This is wire C. Sir, what kind of wire is this? This is the wire which is coming out of the board. Dot means it is coming out. Direction of current over here is outwards. Direction of current over here is outwards. And this is the wire over here. This is A. And direction of current here also is outwards. They're in the outward direction. And in this particular case, I'm saying over here. I'm saying over here. In this case. See guys, I'm saying. We say this is the distance between the two wires, that is given as D, that is given as D. And we are supposed to find the net force on the wire B. How much is the net force on the wire B? Don't you think that whenever the two wires are parallel to each other and direction of current in the two wires is same, this is outward, this is outward, the two wires attract each other. So means on this B, this I will be attracting it. This C wire will be attracting it towards itself with the force F. And force on this wire will be towards this wire A. So we are supposed to find the net force on C. So A will be attracting, B will be attracting. And we are supposed to find the force per unit length over here. Magnitude of force per unit length. Yes. So this is F, this is F. Now tell me, on this wire B, one force is acting in this direction, another force is acting in this direction, and the forces will be equal. I1, I2 are equal. Here I1, I2 is similar. D, separation between the two is similar. And we say this is F, this is F. Don't you think that if the two forces are at 90 degrees, then the resultant of these two forces will be under root 2 of F, under root 2F. This will be the resultant. Yes. And my dear friends, I can say, if I say over here, this net force is under root 2F, you'll simply say this is a root 2. What is the force per unit length? Force per unit length we recently got mu naught I1 I2 by 2 pi r. So it is mu naught I1. What is the value of current in this wire? I. So it will be same. So that is I square, I1 into I2 divided by 2 pi. And what is the distance between the two wires? That is given as D. Okay. Now I would want you guys to rationalize, multiply with root 2 and divide with root 2. So now root 2 into root 2 becomes 2. That 2 will cancel with this 2. So it will come out to be mu naught I square divided by, we say root 2 pi into D. So this will be the net force. This will be the net force. I hope you understood each and every single thing very properly. Okay. Now, let's move on to the next question. Take a look over here. Guys, see, in this particular case, A and B are the two infinitely long parallel conductors. Okay, A and B are the two infinitely long. This is infinitely long. This is infinitely long. C is the another straight conductor of length L. This has the length of 1 meters. C is the another straight wire of length 1 meters. Capped parallel to A and B, which is capped parallel to A wire, which is capped parallel to B wire, as shown in the figure. Then the magnitude and direction of the force. We are supposed to find magnitude and direction of force experienced by C. What is the magnitude and direction of force experienced by this C wire over here? We are supposed to find the magnitude and direction. Now, when they ask you to find the force only, not force per unit length, then I told you they will give you one wire as infinite, another wire as finite. Now guys, see. Let's suppose this is wire A. This is wire C.
Because of wire A, force will be on this wire C. This is, let's suppose, F1. Okay, because the two wires are parallel to each other and the direction of the wire, direction of the current is same. So they will attract each other. So this wire also attracts this wire C towards itself. So this will be F2 force. This is F1, F2. We are supposed to find net force on the wire C. Find the magnitude and direction of force experienced by C. Now let's find the value of F1 first. Okay, how to find the force? Force on this wire due to infinite wire. Let's see the expression what we have over here. See guys, mu naught I1 I2 by 2 pi r into L. Same expression I'll be using over here. Can I say this will be mu naught I1 I2 divided by 2 pi r and then we say L. Okay. Yes. Now guys, we say this F1 will come out to be value of, this is mu naught. When it comes to the mu naught, we write mu naught is equal to 4 pi into 10 raised power minus 7. Okay, I'll just write over here 4 pi into 10 raised power minus 7. Okay, what is the value of I1? I1 over here is 2 ampere. Okay, I'll just write 2 only. Okay, what is the value of I2? I2 is 3 divided by, and L, what is the value of length of this wire? That is given as 1 meter, so it is 1. And then we say 2 pi, okay, r. What is the value of distance between two wires? That is 5 centimeters. So it is 5 into 10 raised power minus 2. Just I'm putting up the values over here and I'll get the answer in this particular case. Okay, I'll get the answer in this particular case. Nothing complicated. Okay. Okay. So I say this wire, this force in this particular, if you solve it, 2.4 into 10 raised power minus 5. Okay, this will be the force in this particular case, that is Newton. Now let's find the force due to this, that is F2. F2 is equal to, okay, this is the force due to wire B on C, that is mu naught I1 I2 divided by 2 pi r into L. So this F2 will come out to be mu naught. What is the value of mu naught? That is 4 pi into 10 raised power minus 7. What is the value of I1? That is 3. What is the value of I2? That is 4 divided by 2 pi r, 2 pi. What is the value of r? 8 into 10 raised power minus 2. 8 into 10 raised power minus 2 into. What is the length of the middle wire? That is given as, length of the middle wire is given as 1. So if you solve it, it comes out to be, that is 3 into 10 raised power minus 5 Newton. Now, how to find the net force? Sir, net force in this case will be, that is F2 minus, we say F1. F2 is 3 into 10 raised power minus 5, 2.4. So 3 minus 2.4 is 0.6 into 10 raised power minus 5 Newton. So this will be the net force experienced by the middle wire. Let's talk about this question. A uniform wire, a uniform conducting wire AB, lying in XY plane, okay? You have got a wire over here. This AB, ABC. This is A, this is B, and this is C. This is 4 centimeters, this is 5 centimeters, okay? And it is placed in the inward magnetic field. Okay? And my dear friends, its mass is given as 10 grams. A current of 2 ampere flows through it. So this is the direction of current over here. It says the current of 2 ampere is flowing through it. Okay. A current of 2 ampere flows through it. The wire is kept in a magnetic field of 2 Tesla. Okay. We are supposed to find the acceleration of the wire. Okay, see. We say as force is equal to mass into acceleration. Acceleration will be simply, that is force divided by mass. Now the question is, what is the force on this? We say Whenever you place a wire in the external magnetic field, it experiences the magnetic force. So we say, sir, magnetic force will be BIL divided by mass M. Okay, 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 yes. So I can say this acceleration will be. Now the question here is, what is the value of magnetic field? That is given as 2 Tesla. Okay. What is the given value of current? Current in this case is given as 2 Ampere. Okay. And what is length? Guys, I told you, if you have the structure something like this, you are supposed to take the effective length. So join the initial point with the final point. It will be effective length. If this is 4, this is 5, this side will be 3 centimeters. Okay, by Pythagoras theorem, you can find it. And we can say it is 3 centimeter, 3 into 10 raised power minus 2 meters divided by mass. Mass is given as 10 grams. Converting to kgs, it will be 10 into 10 raised power minus 3 kgs. So I'll just write over here, this is 10 into 10 raised power minus 3 kgs. Now guys, see. 10 raised power 1, 10 raised power minus 3. It will become 10 raised power minus 2. This 10 raised power minus 2, this 10 raised power minus 2 will cancel. Now 3 into 2 is 6, 6 into 2 is 12. So it will come out to be 12 meter per second square. Now you have to find the direction of the acceleration also. Guys, tell me one thing. What is the direction of force here? This is the direction of current. So if the direction of current is from right to left, from left to right. So here also it will be from left to right. In the effective length, you have to take it left to right. Don't close the loop over here. No. It will be something like this. Now, place your fingers along the direction of current. Curl towards magnetic field. Thumb is pointing upwards. So direction of force is, we say, sir, upwards. So whatever is the direction of force, same is the direction of acceleration, because force and acceleration have same direction. So we say here, acceleration is along positive y-axis. So answer is 12 meter per second square along along positive y-axis. Okay. This is over here in this particular case. Okay. You have got this. Let's move on to the next one. If I say, yeah, let's take a look at this particular question over here. See you guys. Now guys, let's take a look over here. A circular coil ABCD carrying current I. You have got a circular coil, which it is something like this. It is carrying current I, okay, is placed in a uniform magnetic field. If the magnetic force on the segment A, this is A, this is B, this is C, and this is D. It says that, okay, if the magnetic force on the segment AB is F, magnetic force on this segment AB is F, it says that magnetic force on this segment is F. Then force on remaining segment will be, guys, we know when it comes to the net force on the loop is 0. And here. Net force on the loop is 0. We know, sir, if the direction is something like this, net force on the closed loop is 0. Now tell me, in this particular case, we say when it comes to the net force in this case, that will be force on AB, plus we say force on BCDA, plus force on B, C, D and A. Okay. And this is 0 over here will be equal to force on AB. Force on AB is given as F. This is F plus F, B, C, D, A. Now take it over there.
force on B, C, D, A will come out to be minus F. It will come out to be minus F. Now we have got over here a solenoid. What is a solenoid? One of the important topics in the magnetism. What is a solenoid? That is what we need to discuss now. Okay, one of the important topics in the solenoid, in the magnetism. See guys, let's suppose I say you have got a coil over here. Okay, in this coil current I is flowing. You have got the coil over here. In this coil current I is flowing. And how many turns are in this coil? Only one. If I say make another turn, lot of turns in the coil, something like this, lot of turns in the coil. So that is what we call the solenoid. This is the coil of n turns. This is the coil. It is the coil of many turns. A solenoid is basically a coil of many turns in which magnetic field is produced. Okay. Now guys, listen to me very carefully. We know if there is a coil in which current is flowing, it produces the magnetic field at the center. How to find the direction? Curl your fingers, guys. Curl your fingers along the direction of current. Thumb is pointing out inwards. So direction of this is inwards. If direction of current is this, then magnetic field will be outwards. Now, when it comes to this solenoid over here, in this solenoid, I am saying the current is entering something like this and the current is leaving. So the current goes in, it flows and leaves. Don't you think that here current flows in the solenoid and here also magnetic field will be produced? Yes, I say here current flows in the solenoid. So magnetic field is produced. Now, what will be the direction of this magnetic field? I would want you guys to understand this. What will be the direction of this magnetic field? Guys, this is the direction of current. Curl your fingers along the direction of current. Thumb is pointing something like this. So I say, in this particular case, if I just make the direction of the magnetic field over here, that will be something like this. This will be the magnetic field which will be produced over here. This will be the magnetic field which is produced over here. Okay, so this is the magnetic field which is being produced over here. This is the magnetic field, and it is produced along the axis of the solenoid. This magnetic field is produced along the axis of the solenoid. This is the axis of the solenoid. Okay, yes sir, this magnetic field is produced along the axis of the solenoid. So if you have the solenoid, sir, where will be the magnetic field? Along the axis. And we say outside the solenoid, like this area, outside this cylinder, outside the solenoid, magnetic field is 0. We say no magnetic field is present outside the solenoid. It will be produced only inside the solenoid. So outside magnetic field is 0. Yes. Now guys, let's take a look in this particular case. You have got the two cases. First is finite length solenoid. Finite length solenoid means solenoid is this long from one end to this end. Okay, we can see. Another one is infinite. Finite and infinite. Now guys, see, this is a solenoid made over here. Sir, this is dot and cross. How this is solenoid? I'll tell you. Look at this. Guys, in this particular case, the current flows something like this. At the top, we say current is coming out. It is something like this. Current flows something like this.
At the top, current is coming out. So we say here current is coming out, that is dot. And then it flows, flows, flows. At the bottom, it goes in. So here we say current is cross. At the top, current comes out. At the bottom, and while here, this is the direction of current. Here, going down, it goes inside. So similarly, I'm saying dot means the current is coming out. This is the current. Cross means the current is going in. That means this is the current going in. Okay. Now, guys, and this is the axis of the solenoid. This is the axis of the solenoid. I want you to basically draw a line over here. This is the line. And join this center point with one end of the solenoid. It would be something like this. Or let me show you here only. 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 Oh. Yeah. Let me show you here only. Guys, what I'm doing is that I'll basically cut it something like this. Okay? Yes. Now, my dear friends, now what I'm doing in this particular case is, I want you to join with one end of the solenoid. I want you to take this center point and join it with another end of the solenoid. Okay? So I am saying, in this case, we say this angle is what we call alpha. This angle is what we call beta. That is how I have shown it over here. Or that one is alpha or beta. This one is alpha and this one is beta. This is alpha and this one is beta. One and the same thing. Okay, this angle is alpha and this angle is beta. Now, we say magnetic field inside the solenoid. I'll just write magnetic field inside the solenoid. Magnetic field inside the solenoid produced will be, guys, see, this magnetic field is equal to, this magnetic field is equal to, we say it is 1 by 2, then we say mu naught Ni, and then we say sine of alpha plus sine of beta. This will be the magnetic field which is produced over here. This will be the magnetic field which is produced over here in this particular case. This is the magnetic field due to a solenoid. Okay? And this is inside the solenoid. Okay? Cool. Now, let's talk about the solenoid, my dear friends, in case of an infinite solenoid. Sir, what is infinite solenoid? Infinitely long. Don't you think that infinitely long, this will go till infinity. Infinitely long, this will go till infinity, its end. So what is the value of alpha and beta in that case? We say, sir, you have to increase this alpha. So for infinitely long, alpha will come out to be 90 and beta will also come out to be 90. Yes, because you have to match this, join this with at infinity. So then it becomes 90. What will be the value of magnetic field? So we say it is 1 by 2. Then we say mu naught Ni. And then I'll write over here, this is sine of 90 plus I'll write over here, this is sine of 90. Sine 90 is 1, sine 90 is 1, 1 plus 1 is 2. So this will cancel with this 2. So magnetic field due to a solenoid will be mu naught N into I. Now, my dear friends, this mu naught is permeability of free space. N is number of turns per unit length. I is the current flowing in the solenoid, where N is the number of turns per unit length. Okay, where N is the number of turns per unit length. Okay, one more thing I just want to tell you in this particular case, where N is the number of turns per unit length. One more thing I just want to tell you in this particular case. See, guys. See, when it comes to the number of turns per unit length, we say it is total number of turns On the unit length, how many number of turns is present? That is small n. It is total number of turns divided by total length. Total length of the solenoid. It is mentioned over here, N by L. So N will come out to be capital N divided by L. Now put it in the expression. We say this magnetic field will come out to be mu naught capital N I divided by, we say, L. This is what we call magnetic field due to a solenoid in terms of total number of turns. This is number of turns per unit length. This is number of turns per unit length. Yes, this is also done. This is also done. Now guys, listen to me very carefully. This is what we call, and this is the magnetic field at the center. This is magnetic field at the center of the solenoid, Okay. Sir, what about the ends of the solenoid? Guys, if we plot the graph between magnetic field versus distance, we say graph, this is magnetic field and this is the end of the solenoid. When it comes to magnetic field at the ends of the solenoid, guys, always remember, whatever is at the center at the ends, it will be half. This is magnetic field inside. So you will simply say this is mu naught Ni divided by 2. Now, if we plot the end inside the solenoid, we consider this magnetic field as constant, and it is constant. If you plot the graph between magnetic field versus this distance, now at the center, we say center, at center, B is constant. At center, B is constant. At the ends, we say, sir, magnetic field at the ends, okay, is 1 by 2 of magnetic field inside. Magnetic field at the ends, okay, like from solenoid is from here to here. So at the ends, magnetic field is half. At the center, it is constant. And then outside, B outside, we say magnetic field is 0. Okay. And these are some points. Please keep these things in your mind. I have already told you this. Next, let's talk about this one. A long 0.8 meter solenoid has 800 turns. Here, has 800 turns means capital N is 800. Total number of turns. You have got a solenoid. Total number of turns are 800. And has a field density of, it is creating the field inside, that is 2.52 into 10 raised power minus 3 Tesla. This is the magnetic field at its center. Find the current in the solenoid. Guys, tell me, we say as we know. When it comes to the magnetic field due to a solenoid at center, we say that is mu naught capital N into I divided by L. This is in terms of capital N. So we are supposed to find current. So current will be simply B into L divided by mu naught into N. Now I can write current will be exactly in this case. Put the value of B over here. B is 2.52 into 10 raised power minus 3. And then length of the solenoid is given as 0.8 meters. This is 0.8 divided by mu naught, it is 4 pi into 10 raised power minus 7. And then we say number of turns is given as 800. Solve it, see how much it is coming out to be. Next. Okay, this is an important question. Before this question, I want to show you this. This was the question which was asked in the NEET 2020. A long solenoid of 50 centimeter. You have got a solenoid, okay, over here, and its length is 50 centimeter. Okay, so that is 50 into 10 raised power minus 2 meters if you convert to meters. Has a current in which current is flowing as 2.5 ampere. Current is flowing 2.5. Has got 100 turns. Number of turns in this case is 100. The magnetic field at the center of the solenoid is, guys, simple. This was the question of NEET 2020. Magnetic field is mu naught capital N divided by L. All the values are given, you can find the magnetic field. Mu naught is 4 pi into 10 raised power minus 7. Okay. Number of turns in this case are given as 100. Current in this case is given as 2.5 ampere. Okay. And length of the solenoid is 50 into 10 raised power minus 2. Check out what is the value of the solenoid magnetic field inside. This one. Okay. A long solenoid produces the magnetic field B at its center. You have got a solenoid over here. We say magnetic field is present at its center, that is B. And we can write it as mu naught, we say N, we say mu naught capital N I divided by we say L. Okay. If it is cut into two equal parts, we want to cut this solenoid into two equal parts. This part and we say this part. We want to cut this solenoid into two equal parts, this part and this part. And same number of turns are wound on one part in double layer. What does that mean? If this is cut into two equal parts, now let's suppose I'll take something over here. I'll wound this part on this. I'll wound this part on this. Okay. Then I'll wound this part also on this in double layer. This is what is the meaning over here. Okay. We say it says that cut in two parts, then wound on something in double layer. Okay. Don't you think that, guys, here I can say number of turns will be n by 2. Here number of turns is n by 2. If you wound in double layer, once again number of turns n dash will remain same, n. Because now if this is n by 2, n by 2, n by 2 plus n by 2 is n. Okay. And what about the length? Length will become L dash will become L by 2. Because if the length here is L, it becomes L by 2, L by 2, here is L by 2. And we can say in this particular case, my dear friends, magnetic field will come out to be, guys, mu naught, okay, N mu naught N dash, that is N only, okay. I, current is same, I divided by L by 2, L by 2. Okay. Now, take this in the numerator. So we can say B is equal to, we say this is 2 mu naught N I divided by, we say L. So can I not say B is equal to, what is this mu naught N into I by L? So this is 2, this is B dash, B dash is 2 times of B. So magnetic field of the new solenoid will be doubled. It is doubled. Okay, now let's come on to this question. This is the important question. See guys, a copper wire having a resistance of 0.01 ohm per meter. A copper wire having a resistance of 0.01 ohm per meter. Okay, yes. You have got a copper wire over here and it says its resistance is 0.01 ohm per meter, means resistance per unit length is given as 0.01 ohm per meter. This is not the net resistance or the total resistance. It is the resistance of the unit length that is given as 0.01 ohm per meter. Yes, this is the copper wire. Its resistance is given as 0.01 ohm per meter. Okay, this is a copper wire. I'll just write copper wire. Now guys, is used to wind a 400 turn solenoid. We are basically converting this wire, okay? We are making it a solenoid. We are converting it into a solenoid. So we are converting it into a solenoid. And then it says, what is the number of turns of that solenoid? We say number of turns are 400. Okay. 400 turns solenoid of radius 1 centimeter, and radius of this turn, this circular turn has got radius of 1 centimeter. That is 10 raised power minus 2 meters. Yes. And length is 20 centimeters. Length of the solenoid is given as 20 centimeters. So I can write over here, this is 20 into 10 raised power minus 2 meters. Okay. Yes.
Find the EMF of the battery. Find the EMF of the battery, which when connected across the solenoid to produce the, okay, what does it say? It says that if we take this solenoid, same solenoid, this coil, and if we connect a battery across it, okay, such that, guys, we know this battery will send the current and this current flows in this solenoid, okay, and because of this current, we say magnetic field is produced, okay. And how much magnetic field is produced? Magnetic field is produced over here, 10 raised power minus 2 Tesla. If we are connecting a battery, battery sends the current, battery has potential difference, it sends current, current creates magnetic field. How much magnetic field is produced? 10 raised power 2 Tesla. It says that, what is the EMF of this battery? How much should be the EMF of the battery? So that 10 raised power minus 2 Tesla magnetic field is created or generated over here. Okay, the question is, what should be the value of V so that 10 raised power minus 2 Tesla magnetic field is produced in the solenoid? We are supposed to find V. Guys, the very simple thing or very simple approach is, in order to find V, guys, listen to me very carefully. We say V is equal to I into R. Simple thing. If you are supposed to find the this EMF potential difference, we say I into R. So I means the current. If you are able to find the current in this circuit, in this solenoid, and you are able to find the resistance of this solenoid, you will put the values over here, you will get the value of potential difference. Now see, let's find resistance. Let's find resistance first. Resistance first. Let's find resistance first. Okay. Let's find resistance first. Now guys, I would want you guys to listen to me very, very, very carefully. I would want you guys to listen to me very, very, very carefully over here. Okay. What I'm trying to say is, let's find resistance first. See, we have got this copper wire over here. We are supposed to find the resistance. Resistance per unit length is given. In order to find the total resistance, what we will do? We say, sir, resistance total will be resistance per unit length. Guys, if you want to find the total resistance, you will multiply this with what? Total length. So you'll say, sir, it is 0.01 multiplied by total length. This is resistance per unit length. Multiply this length over here, you will get total resistance. Yes, unit length resistance multiplied by total length will be total resistance. Yes. Now the question is, what is the total length of this? What is the total length? You say, sir, total length is given as 20. No. This is the length of the solenoid. You are supposed to find the length of the wire. This is the solenoid wounded. If you elongate it, it will become more longer. So we say, when it comes to the length, guys, see, length of the solenoid will be simply, how many number of turns are over here? 400. And what is the length? What is the circumference of one turn? That is 2 pi r. So it will be 400 multiplied by 2 pi r. This will be the total length. Now put it over here. If we put it over here, what will we get? We'll get the resistance as 0.01 into, what is the total length that we got? 400 into 2 pi. And what is the value of r? R is the radius. Radius is given as 10 raised power minus 2 into 10 raised power minus 2. Now guys, this is 10 raised power minus 2. That is 1 by 100. Okay, this 10 raised power minus 2 and this double 0 will be cancelled because this is 400. 1 by 100. 0 will cancel. I hope you know this mathematics. Okay. Now, in this particular case, this is also 10 raised power minus 2. So because this is 1 by 100, either you say 0.01, either you say this is 1 by 100, or you say 10, or you say 10 raised power minus 2, one and the same thing. So I'll write over here, R is equal to, we say 4 into 2 is 8 pi into 10 raised power minus 2 ohm. This is the total resistance. So we got the value of resistance. Let's find the current. Now, current in the solenoid. Current in the solenoid. Guys, tell me one thing. When it comes to the current in the solenoid, don't you think that for finding current in the solenoid, we say as magnetic field B is equal to mu naught Ni divided by L. This is the magnetic field in a solenoid. Now here, multiply this B into L divided by mu naught into N. It will exactly give you current. So I want you guys to put an equation first. This is equation first. So we say put in equation first. So you can say in this particular case, this current will come out to be magnetic field. What is the value of magnetic field? Okay, this current this V is equal to, what is the value of current? Current is, we say BL divided by mu naught into N, and this will be, sir, R. Now what is the value of magnetic field? Guys, see. Magnetic field is 10 raised power 2. Okay, what else do you need? Then we say L. L is the length of the solenoid, that is given over here. What else do you need? Mu naught is 4 pi and 10 raised power minus 7. Number of turns is 400. Resistance of this we recently got, that is 8 pi into 10 raised power minus 2. And if you put up all of these values that you will do by yourself, this will come out to be 1 volt. The answer is 1 volt. And you guys will have to solve this from your end. Okay? Is that clear, boys and girls, ladies and gentlemen? I hope this is crystalline clear to each and every single student out. Let's move on to this one. That is what we call the toroid. Let's move on to the toroid. Magnetic field due to a toroid. Now guys, what is this toroid? See. Let's suppose if you have a solenoid over here. This is a solenoid. This is a long solenoid. I want you to turn the solenoid and make it in the form of a circular shape. Okay? So how will it look like actually? How will it look like in that particular case? We say it will look like something like this. Okay? It will look like something like this. So this is what we call the toroid. So toroid can be considered as a ring-shaped closed solenoid. Okay, it's like an endless cylindrical solenoid. It does not have an end because it is a ring-shaped solenoid. And my dear friends, one more thing. This is a solenoid over here. If I say magnetic field in case of the solenoid was along the axis. Now, if you are turning this, don't you think that magnetic field will be also turned? So this will be the magnetic field inside the solenoid. So this is what we call the magnetic field. Magnetic field inside the solenoid. Yes, it is something like this. So here magnetic field forms kind of a ring inside. Okay. So my dear friends, listen to me very carefully. I say, whatever is the magnetic field of solenoid, we say same will be the magnetic field due to toroid. Why? Because from solenoid only we create the toroid. That's why we say whatever is the magnetic field of solenoid, same will be the magnetic field of toroid. Now tell me, sir, this magnetic field of toroid will be, that is mu naught N into, I'll just write this one, mu naught N I divided by L. What is N? N is the total number of turns. What is L? L is the length of this toroid.
Could you please tell me, guys, let's suppose from this point till this, we say this is the radius r. Means from center here, this is the radius of the solenoid. Okay. Okay. So my dear friends, could you please tell me what is this length of the solenoid? Length, that will be circumference. We say L is equal to circumference of toroid. And we say this L is equal to 2 pi r. And I'll just write this magnetic field due to toroid. It will be simply, that is mu naught Ni divided by 2 pi r. I would want you guys to put this in a box. Okay, this is the magnetic field due to a toroid. This is the magnetic field due to a toroid. This is the magnetic field due to a toroid. Okay. This is the magnetic field due to a toroid. This is the magnetic field due to a toroid. Okay. Okay. Now guys, listen to me very carefully. Let's suppose you have this toroid over here. Don't you think that from CC, it is a cylindrical tube, ring-shaped cylindrical tube. Okay, from here to here, radius is, we say, sir, R1. And from here to here, radius is R2. R2 is bigger radius. Now, don't you think that if magnetic field due to a toroid is mu naught I divided by mu naught Ni divided by 2 pi r, don't you think that magnetic field here is inversely proportional to r? Means if this radius is smaller, magnetic field will be bigger. If radius is bigger, magnetic field will be smaller. Yes. So I can say in this particular case, B maximum magnetic field. So don't you think that maximum magnetic field in this case will be at smaller radius? Yes. So I can say that is mu naught Ni divided by, we say, 2 pi r1. And when it comes to the minimum magnetic field, we say B minimum in this case will be simply, that is mu naught Ni divided by 2 pi r2. So we say at r2 distance, at r2 radius, magnetic field will be minimum. At this, we say magnetic field will be maximum. Write it because r1 is less than, we say, r2. So we say B, I'll write over here, and magnetic field is inversely proportional to r. Let's move on to this one. A coil wrapped around a toroid has an inner radius of, guys, see. In this case, I'm making this figure over here. Let's suppose I'm making this figure over here, something like this. See, I'll try to make a beautiful toroid. Yes. Now, in this particular case, guys, listen to me very carefully. It says that a toroid has an inner radius of, this is R1, okay, of 20 centimeters. R1 in this case is 20 centimeters. This is what we call the inner radius. And an outer radius of 25 centimeters. This is, we say, R2. R2 is given as 25 centimeters. Outer radius is given as 25 centimeters. Okay. If the wire wrapping makes 800 turns, means number of turns in this case is, we say, sir, 800, and carries a current of 12 ampere, we say carries a current of I is equal to 12 ampere, and carries a current of 12 ampere. If R1 is 20 centimeter, R2 is 25 centimeter, N is 800, I is 12 ampere. Find the maximum and minimum magnetic field. What will you say? Guys, when it comes to the B max, we say B max will be when radius is 20 centimeters. So what will you say? Sir, mu naught Ni. What is the magnetic field? Mu naught Ni divided by 2 pi. This is capital N, 2 pi R1. Okay, just put up the values and get the answer. And when it comes to the minimum magnetic field, you say, sir, it will be simply mu naught capital N into I divided by 2 pi R2. Here, you are supposed to use 20 into 10 raised power minus 2. Here, you are supposed to use 25 into 10 raised power minus 2. Rest current is given. Everything is given. Number of turns is given. You can put the values and get the answer. Let's move on to the magnetic dipole. Okay. Let's talk about the magnetic dipole now. See guys, listen to me very, very, very carefully. See, previously we have studied, as we know about electric dipole. We have previously studied about the electric dipole. Okay, just a second, let me clean this up. Okay, so previously we have studied about what? Electric dipole. Now guys, what is electric dipole? When it comes to the electric dipole, you say simply, you have got a negative charge over here, you have got a positive charge over here. So when a negative charge is separated by positive charge with some distance, okay, we call this as electric dipole. Okay, if you have got the negative charge, positive charge, when two equal and opposite charges are separated by some distance, it is called electric dipole. And it has got a dipole moment. We know that dipole moment, we say P is equal to charge Q multiplied by distance between them. Charge into distance between the two. So when it comes to the electric dipole, it is charge, magnitude of charge multiplied by distance. This was electric dipole. And when it comes to the magnetic dipole, guys, I would want you guys to listen. When it comes to the magnetic dipole, okay, so in magnetism, we consider bar magnet as magnetic dipole. The bar magnet which we see in the market, which we buy from the market, that is what we consider as the magnetic dipole. Okay, that is something like this. Okay, it has got south pole, it has got north pole. Okay, south pole and north pole. That is what we consider as bar magnet over here. Okay, now my dear friends, when it comes to the south pole and north pole, like here it has magnitude of charge. We say here we call it pole strength, that is minus m. Here we call pole strength as plus m. Pole strength means how stronger the pole is. If the magnet is bigger, it has got the bigger pole strength. If the magnitude is small, if the magnet is small, we say it has got the small pole strength. Okay, south pole has got minus m pole strength, north pole has got minus plus m pole strength. Okay, so we say south pole where minus m
is the pole strength of South Pole. And plus m is the pole strength of North Pole. Okay. Now, my dear friends, if I make it something like this, this is over here minus m and this is over here plus m. This is South Pole and this is North Pole. Always remember, in this case also we have got the dipole moment, and that is from we say plus m to minus m. We say here it has the dipole moment, magnetic dipole moment. Capital M is equal to m into L. Like here you have electric dipole moment, P is equal to Q into D. Here it is pole strength multiplied by distance between the poles or separation between the poles. Distance between the poles or separation between the poles in this particular case. Okay. Yes. Sir, what is this dipole moment, magnetic? It kind of tells you how stronger the pole is. More is the strongest. If this bar magnet is strong, we say its dipole moment will be strong. Okay. Yes. And its direction is from minus m to plus m. Direction is from minus m to plus m. Direction is from minus m to plus m. As simple as that. So from now onwards, what is a bar magnet? Bar magnet is, we say, what is a magnetic dipole? We say it's a bar magnet. It has got no South Pole, North Pole. South Pole has got minus m pole strength. North Pole has got plus m pole strength. And it has a dipole moment also. Now let's suppose if you take a bar magnet and if you cut this bar magnet along the length, okay, if you are cutting this, something like this in two parts, we say its magnetic dipole moment, becomes, we say, m by 2. Okay. So we say, forget about this. Its pole strength will become m by 2. Its pole strength will become m by 2. Like. If I say length of this is L and this is over here minus m and this is over here plus m. We say, what is the dipole moment in this case? You say, sir, pole strength multiplied by distance between the poles. Now, if you cut it along length, we say volume is decreased. So its pole strength will decrease. It becomes m by 2. Previously, it was m, right? It is m by 2. So right now, what is the pole strength of this magnet or this magnet? You say, sir, that is, sorry, magnetic dipole moment. That will be pole strength. That is m by 2. Distance between them is L. It is still L. It's still L. So this is ml divided by 2. So now m into L is capital M. So we say this is m dash. So m dash will become m by 2. Means its pole strength is also decreased and dipole moment is also decreased. It's halved. Let's suppose if you have a bar magnet, if it is cut along breadth, if you cut along breadth, this is the breadth. So it will become something like this. We say here, pole strength remains same. Here, pole strength remains the same. In this case, we say pole strength remains the same. Okay. Yes. Now guys, if pole strength in this case remains the same, I would want you guys to listen to me very, very, very carefully. I would want you guys to listen to me very, very, very carefully. We say pole strength in this case remains the same. Pole strength in this case remains the same. And why? Because volume is not halved. Volume remains the same. That's why. Now, what is the magnetic dipole moment previously, sir? M is equal to m into L. What is here? Sir, capital M dash, it will be equal to pole strength. What is pole strength? That is M. But don't you think, length over here is L. Length of this dipole is L. Here it becomes L by 2 for this, L by 2. Length is halved. So it will become L by 2. Now, if it is L by 2, I can say this will be ML divided by 2.
What is m into L? That is m. So I can say m dash will be m by 2. Here, pole strength remains the same, but dipole moment is halved also. In previous case, both are halved. Both are halved. You have this question on the screen. In this case, you are given a bar magnet. I'll make the figure over here. A bar magnet of length L and dipole moment m is bent. Okay. The question says you have got a bar magnet over here. Okay. Okay, this. And I'll write over here, this is minus m, this is plus m. And in this case, I say length is L. Length is L. A bar magnet of length L. Okay. And what is the dipole moment in this case? That is m into L. It says that if it is bent in the form of an arc, we say bent in the form of an arc. If it is bent in the form of an arc, I'll make it something like this. If it is bent in the form of an arc. If it is bent in the form of an arc. Okay. Okay. You are supposed to find, now this is minus m over here, this is plus m over here. Okay. You are supposed to find, and then it says that this, let me make with this one. Okay. It is bent in the form of an arc, and this angle in this case is given as 60 degrees. It says that what is the dipole moment of this arc? The dipole moment remains the same. We say no. See, it is bent. We say this minus m and plus m kind of will come close to each other. Okay. Now, distance between this minus m and plus m will be this. This is the distance between minus m and plus m. Guys, this distance is given as over here r. This is over here r. If we are supposed to find the pole strength finally, m dash, you'll say, sir, sorry, dipole moment finally, m dash, you'll say it is pole strength, that is m, multiplied by distance between the poles. Guys, see, if this is r, could you please tell me how much will be this angle? This is 30. If this is r, this will be r cos 30, and this component will be r sin 30. Total angle is 30. This will be also 30. Total angle is 60. 30, 30 plus 60. This is r. This will be r cos 30. This will be r sin of 30. Now, distance between the poles in this case is, we say r sin 30 plus r sin 30. That is 2r sin of 30. Yes. Now tell me one thing. Sin 30 is 1 by 2. So I can write m dash will come out to be m. 2r into 1 by 2. This 2 and 2 will cancel. So it will come out to be m into r. Okay, tell me one thing, guys. Tell me one thing, guys. This is m. And in none of the option is matching. Tell me one thing. Tell me one thing. In this particular case, from the figure, we say total angle is 60. We say from the arc. Could you please tell me, can I say, sir, angle is equal to arc upon radius? Okay. What is angle over here? That is 60 degrees. So I can say this is pi by 3. Okay. And what is arc? If the length of this wire is L, length of this rod is L, bar magnet is L, this length will be also L because you have bent this L only. So this will be L. And this radius in this case is given as R. What is the value of R? R will come out to be in this case, that is 3L divided by pi. Call this as equation first. Now I say put R in equation first. Put R in equation first. Okay. Put R in equation first. So I can say this m is equal to m into r, m dash. M dash will come out to be m. And what is r?
R is 3L by pi. So you can write 3L divided by pi. Okay. So I can write this is 3 divided by pi into M into L. What is M into L? M into L is original M. So I can say this will be 3 by pi into capital M. This will be the new dipole moment of this arc, and 3m by pi is the option B matching over here. This was a good question actually. Now guys, take a look exactly at this one. We are moving towards completing the chapter, and I'm not leaving a single thing in the chapter. Make sure you hit the like button, everybody out there, and then you comment, you pause the lecture right now and you comment down below. And I assure you, I'm giving you the guarantee, the content of these marathons or this marathon is unmatchable. That is the guarantee. You can check out any of the series and any of the series out there. Okay, if you compare the content of this magnetism chapter with any other series, you'll get to know the difference. Okay, I am not leaving a single topic, and more than 6, 7, 8 questions I'm showing in every single topic. Okay, you would be able to understand every single thing, provided you have that consistency. Okay. Magnetic field due to a dipole. Now guys, we have got over here, in this case, see, we say, listen to me very carefully. Magnetic field due to a magnetic dipole. Sir, if you have got a bar magnet over here, if you have got a magnetic dipole over here, we say it creates the magnetic field around it. Okay, it is simple. Sir, you bring the bar magnet from the market, you place it over here. Okay, then you place the coin near it, it will be attracted. So what does that mean? The bar magnet is creating the magnetic field around it. Okay, now we have to find the magnetic field due to a bar magnet. If I am saying you have got a bar magnet over here, that is something like this. This is the bar magnet which you have got. Okay, its dipole moment is from, we say, south pole to north pole. Okay, its dipole moment is from, we say, south pole to north pole. Let me just make it over here first. So you have got this bar magnet over here. Okay, and this is the south pole and this is north pole. Okay, similarly, I'll make it over here also. Okay, similarly, I'll make it over here also. This is the bar magnet that you have got. This is the bar magnet that you have got over here. This is the bar magnet that you have got over here. Okay, this is south pole. This is south pole. This is north pole. This is south pole. This is north pole. Now, guys, see. Previously, when it comes to the electric dipole, I would want you guys to focus completely. We say this is the electric dipole over here. Means you have got, this is the minus Q charge, negative charge, and this is plus Q charge, that is positive charge. Dipole moment is from minus Q to plus Q. Okay, yes. And in this case, over there, you might have calculated electric field, and I have shown you electric field because of the electric dipole on its axial point. Axial point means if this is the dipole, this is the point. This lies on its axis. This is the equatorial point. Axial point, equatorial point. Electric field because of a bar magnet on its axial point, on its equatorial point. This is the axial point. This is called the equatorial point, which is exactly over here, something like this. On the axial point of an electric dipole, electric field is twice Kp by x cube or r cube. Sir, what is this K? K is the dipole moment over here. Okay, dipole moment over here. Sorry, K is the constant, Coulomb's constant. P is the dipole moment. And what is this R? R is the distance at which you are finding the electric field. Sir, in this case, we say, either you say R or you say X, one and the same. Let's keep X only. This is X and this is X. So this is the X distance. Then you calculated, sir, at equatorial point, this came out to be the electric field. This came out to be the electric field. Kp by x cube. P is the dipole moment, x is the distance. This is the distance, okay, from the dipole. Then this is the general point, or we say arbitrary point. At arbitrary point, from this electric field is Kp by x cube under root of 1 plus 3 cos square theta plus 1. We have studied this previously. Similarly, you have got magnetic field because of magnetic dipole. First, you have to find on the actual point. Guys, we'll copy it from that particular topic, previous topic. See, here on the axis it is twice Kp by x cube. K is the Coulomb's constant used in electrostatics, P is the dipole moment. Come over here. Here, 2 is also here. Previously it is twice, here it is twice. Over there, we use the constant as K. K is 1 by 4 pi epsilon naught. And when it comes to the magnetism, we use the constant here, mu naught by 4 pi. 2, and this is constant mu naught by 4 pi. And then you have got the dipole moment P over here. Here you have got dipole moment M. That's it. Divided by x cube or r cube. If you are keeping this r only, I'll also keep r. Keep r. Okay, divided by r cube. Okay. And then, my dear friends, same. And then, my dear friends, let's talk about the equatorial point. On the equatorial point, you have Kp by r cube. K is the constant, 1 by 4 pi epsilon naught. P is dipole moment, r is this. Now, see here. Instead of K, you have got mu naught by 4 pi. Dipole moment M divided by r cube. Same, exactly similar. Okay, exactly similar. This is the bar magnet. Guys, because of the bar magnet at axial point, because of the bar magnet at this equatorial point, then you have got the general point in this particular case. Then you have got the general point. Okay. Now see, in this case, what is the electric field? Kp by r cube under root of 1 plus 3 cos square theta plus 1. Now see, this is the bar magnet. At r distance, magnetic field is, here you have got mu naught by 4 pi m by r cube. See, here it is Kp by r cube. Here it is constant m by r cube under root of 1 plus 3 cos square theta plus 1. Theta is the angle between dipole moment and this r. Theta is the dipole moment and this r. So this is basically the magnetic field due to a magnetic dipole at axial point, equatorial point and general point. That's it. Nothing more. Let's suppose you have got, find the magnetic field due to a dipole of magnetic moment 3 ampere meter square. So magnetic moment due to a dipole is given as 3 ampere meter square. Okay. At a point 5 meter away, means r is given in this case as 5 meters. In the direction making angle 45 degrees. So theta is given as 45 degrees. What it is saying in this case is, you have got a bar magnet over here. Okay. It is asking you, this is, since this is the dipole moment, this is south pole and this is north pole. It is asking you, you have to find the magnetic field at r is equal to 5 meters. Okay. And this angle is given as theta is equal to 45 degrees. Okay. At this particular point, tell me which point is this, axial, equatorial or general? I think this is general point. So we'll be using the general formula over here. We say in this particular case, we say here, use general formula. And one more thing I forgot to tell you, that is, from this general formula, you can calculate this and this. How? Guys, see. Here angle is theta at this point. If you decrease the value of theta, you will reach on to the axial point. So at axial point, value of theta is 0. put the value of theta 0 over here, you'll get this expression. And when it comes to the equatorial point, we say increase the value of theta. Increase the value of theta to 90. Put the value of theta over here, 90, you'll get this expression. As simple as that. Okay. You mention over here, for axial point, theta is equal to 0 degrees. And for equatorial point, theta is equal to 90 degrees. Here use general formula. What is general formula? B is equal to mu naught by 4 pi m by r cube under root of 1 plus 3 cos square theta plus 3 cos square theta. Okay, now guys, in this particular case, you can say magnetic field will be mu naught by 4 pi. Always remember, I have told you, value of mu naught by 4 pi is 10 raised power minus 7. And value of mu naught will be multiply over here, that is 4 pi into 10 raised power minus 7. So it will be 10 raised power minus 7. And what is the value of m? M is given as 3. R cube, R is given as 5 cube, that is 5. And then we say under root of 1 plus 3 cos square of 45. Cos 45 is 1 by root 2, it becomes 1 by 2. Solve it and you will get the answer value of V. Next. Now guys, look at this. Look at this. Look at this. See guys, torque on a magnetic dipole placed in an external magnetic field. Torque on a magnetic dipole placed in an external magnetic field. Okay. Guys, before this, I would want you to understand the topic that you have understood previously. We have studied torque on an electric dipole placed in an external electric field. If you have, this is the external electric field over here. This is the external electric field over here. And in this external electric field, you are placing the electric dipole. Electric dipole means this is negative charge and this is positive charge. Okay. And my dear friends, we have studied previously, if you place a negative charge in the external electric field, it experiences a force, and this force F is equal to Q times of E. And we know, sir, this negative charge will experience the force same, but in the opposite direction, Q times of E. Positive charge will experience in same direction, this in opposite direction. Don't you think it will try to rotate the dipole? Yes, these two forces will try to rotate the dipole. Yes, torque will be created. Torque will be created. Okay. So whenever there is rotation, we say, sir, torque is there. Whenever we say body moves from rest, we say force is there. We say rotation, torque, motion, force. And the value of torque here is P cross E. P is the dipole moment of this dipole. E is the electric field of this electric field. And we say PE sin theta also, where theta is the angle between P and E. Similarly, here in magnetism, we place a bar magnet over here. We place a bar magnet in this magnetic field. It has got minus M. It has got plus M. Okay. And exactly in a similar way, we say on this plus M, force will act in the forward direction. On the plus M, due to this magnetic field, force acts in the forward direction. On the minus M, force acts in the backward direction. Don't you think due to these two forces also, the dipole will rotate? Yes. So torque is produced. We say here, due to the two forces, dipole will rotate, rotate, and torque is produced. And torque is produced. Due to these two forces, the dipole will rotate and torque is produced. Yes. And that torque will be M cross B. Here it was P cross E, dipole moment into electric field. Here it is magnetic dipole moment into magnetic field. Or we say MB sine theta, where theta is the angle between, we say M and B, where theta is the angle between M and B. Okay. Okay. Yes. Now guys, if I say over here, if theta is equal to 90 degrees, let's suppose, first let's write if theta is equal to 0 degrees. What does that mean? That means this is the magnetic field, and in this magnetic field you are placing a magnetic dipole. Okay. And this is over here minus M, this is over here plus M. And dipole moment is from minus M to plus M. Here, angle between this M and B is 0 degree. What is the value of torque in this case? You say, sir, it is MB sine of 0. Sine 0 is 0, so torque is 0. So here, the dipole will not rotate. It is simple. Force on minus M is in the backward direction. Force on plus M is in the forward direction. These two forces are pulling the dipole, so they will not rotate it. It will only rotate if one force is acting in this direction, another force is acting in opposite direction, so it will rotate. Here rotation is not there. And then, my dear friends, if I say second, if theta is equal to 90 degrees, okay, if theta is equal to 90 degrees, so means this is what we call the magnetic field, and you are placing the bar magnet something like this. So this will be minus M, this will be plus M. So dipole moment is from minus M to plus M, and this will be the magnetic field in forward direction. Here angle is 90. In this case, you can say torque will be, that is MB sine of 90. Okay, sine 90. So you can say torque will be, sine 90 is 1, that will be MB, and this is maximum torque. This is maximum torque. Okay. This is the maximum torque that we have exactly over here. Next, potential energy. Guys. You need to keep your mind exactly over here to understand this also. See, let's suppose I say you have an object over here. Okay. Or you say you have a block over here. Okay, on the surface you place a block. And I want you to basically take this block and place it exactly over here. Okay. So while you are taking the block from the surface to the height h, we have studied, everyone knows it. Sir, on the surface, we consider energy as 0, potential energy as 0. On the surface, we consider potential energy as 0. Okay. Yes. Okay. Simply, you consider on the surface energy is 0. When you are taking to the height h, you say, sir, this energy is mg into h. So, while taking the object from the surface to height h, you say its potential energy has increased. It has become mgh. Previously, it was 0. Okay. So, we say here, in this case, this potential energy is increased, changed, when some external agent came and that lifted the block. If I say I do not lift the block from the surface, will the potential energy increase? No, it will still remain over here. So potential energy will be 0. So when I do the work done to lift the block to height h, we say, then only potential energy will come. So can I say
the work done by the external agent in lifting the block, is stored in the form of potential energy. Yes, sir. And how much is that potential energy? mgh. So when you did the work done, when external agent did the work done, that is stored in the form of external energy. That is stored in the form of potential energy. So I can say work done by external agent, due to this external agent's work, potential energy has been changed from 0 to mgh. We say this work done is equal to change in potential energy. Yes. Or you can also say this work done, due to this work done, potential energy is U final minus U initial. Yes. Now let's take the example. Let's take the example of the dipole, magnetic dipole. You have got this is the magnetic field, and in this magnetic field you are placing a dipole. Let's suppose something like this. You are placing a dipole something like this. Okay. Yes. Yes. Now guys, this is, let's suppose, minus m, this is plus m. Now I want you to rotate the dipole. Since you are rotating the dipole, you are using your own energy, you are using your own efforts, and you have rotated the dipole by how much? By theta. Here you have displaced it by h distance. Here it is angular distance theta. Don't you think that if you rotate the dipole in this case, you have to do the work done? Because it will not rotate by itself. You will have to rotate it. Okay. So when you rotate this dipole over here, so means you will have to do the external work done in this case. Yes. So I say here, also the work done by the external agent will be stored as potential energy. Yes. And one more thing, my dear friends. Basically, you are using your own energy. That is stored in the form of potential energy over here. And one more thing, we say due, I'll write it like this. So, due to the external work done, potential energy of the dipole is changed. Due to the external work done, potential energy of the dipole is changed. Yes. And can I say here also work done by external agent is equal to change in potential energy? This is valid here also. Yes. So we say work done by external agent, we can write U final minus U initial. Okay, now, since you are saying, sir, in this case, while you lifted the block, potential energy was changed, delta U. And how much was actually stored? That is mgh. How much is actually stored over here? I'll tell you. Guys, dipole moment of this is, we say, sir, M. This is M. Magnetic field is B. And potential energy stored will be. Guys, see, we say U is equal to minus MB cos of theta. This is the potential energy stored in the dipole when you rotate it by theta. So at theta angle, how much is the potential energy? Minus MB cos theta. At h height, how much is the potential energy? mgh. Okay. Or you can also call it U is equal to minus P dot E. Potential energy is scalar. You don't have to put the vector over here, by the way. Okay. So this will be the potential energy stored. U is equal to minus P dot E. U is equal to minus P dot E. Yes. Like. My dear friends, listen. What I'm trying to say in this case is, let's suppose previously I have told you in the electrostatics, if this is the electric field, and in this electric field, this is negative charge, this is positive charge. Okay, this is negative charge, this is positive charge. This is the electric dipole. If you rotate this electric dipole by theta, here also potential energy will be stored. Okay, here also work done is equal to change in potential energy. And here we say potential energy stored will be minus P dot E, minus P dot E. Here it is minus P E cos of theta. This is the potential energy stored in an electric dipole, and this is the potential energy stored in a magnetic dipole. Okay? Yes, yes. Now, guys, I would want you to focus exactly over here. Exactly over here. Okay? Yes. Now, guys, see. Let's suppose if I say if theta is equal to 0 degrees. If theta is equal to 0 degrees. What does that mean? What does that mean? That means the dipole in this magnetic field is placed something like this. This is minus m, this is plus m. And magnetic dipole moment is in the forward direction. Magnetic field is in the forward direction. Means they are parallel to each other, so theta is 0. In this case, I would want you guys to tell me what is the value of torque. You say, sir, torque is mb sine of theta, sine 0. So torque will come out to be 0. And guys, what is net force in this particular case? You say net force, see, on this one, force is acting in the forward direction, force is acting in the backward direction. This will cancel with this, so net force is also 0. When the net force on a body is 0, always remember it is in the equilibrium. So dipole is in equilibrium. Dipole is in equilibrium. Okay. Yes. Cool. And more specifically, if I say, if the net torque on the body is 0, if the net torque on the body is 0, the body is in the rotational equilibrium. And if the net force on the body is 0, the body is in the translational equilibrium. Body is in the, I'll write over here instead of equilibrium, I'll write over here translational and rotational equilibrium. Okay, yes. And if somebody asks you what is the potential energy of the dipole, u means potential energy, you say minus Pe cos of 0, Pe cos theta, so it will be minus Pe, minus P, cos 0 is 1, minus Pe means minimum potential energy. Okay, yes. And one more thing, I say here dipole is in stable equilibrium. Sir, what does stable and unstable equilibrium actually mean? Guys, see, translational and rotational means net torque is 0, net force is 0 means translation and rotational. Stable, unstable means, guys, see, I'll make you understand. Come here. Let's suppose you have got a ball over here. Okay, you have the ball in the bowl, and you have the ball in the on the bowl, top of the bowl. Okay, this is the bowl. Now, my dear friends, if you displace this ball over here, you are displacing this. So it will go and it will come back. If you displace in this direction, it will go and it will come back. Yes. So we said this is what we call the stable equilibrium. Why? Because if you displace an object over here, it comes back to its original position, means stable equilibrium. And here, if let's suppose this is height h, okay, we say it is at 0 height, so we say here potential energy will be minimum. So at stable equilibrium, potential energy will be minimum. And if you displace the ball over here, it will fall down and it will reach over here. If you displace in this side, it will fall down, it will reach over here. So we say This is what we call unstable equilibrium. Okay, and here potential energy is maximum. We say unstable equilibrium is that equilibrium in which the object does not come back to its original position. That's why here it does not come back, it will fall. It will move from unstable to stable actually. Okay. Now, in this particular case, guys, let's take the same example over here. Make sure you copy this in the notes also. Let's suppose you have got this magnetic field. We say here, this is minus m and this is plus m. Let's suppose if you displace this dipole, something like this. This is plus and this is minus. Now, due to this magnetic field, force will act on this plus in the forward direction. Force will act on this in a backward direction. Don't you think that it will again be rotated back to its original position due to this, and this torque will be created that will rotate it back? Yes. So we say that's why if you displace the body from stable, it will come back to the stable. So that's why we say if you displace the body from 0 degrees, it will come back to the 0 degrees original position. That's why it is stable. And unstable means if this is the magnetic field, we say here in this particular case, this is plus, this is minus, this is the dipole moment m. Now, if you displace, my dear friends, in this particular case, see, we say on plus m force acts in the forward direction, on minus m force acts in the backward direction. Now, because of these two forces, we say it will rotate and it will move to the stable equilibrium. So we say it will go something, this plus will come over here, something like this. So when body moves from unstable to stable, okay, when body does not come back to its original position, it is unstable. When body comes back to its original position, it is stable. So when body comes back to original position, when body does not come back to its original position. Okay, so we say this is stable, and over here potential energy is minimum, and here we say potential energy is maximum. Now guys, let's suppose if I say if theta is equal to 180 degrees. Okay, this is the case 2. This is case 1. When theta is equal to 180 degrees. Now guys, we say you have got this over here. You have got this magnetic field over here. Okay, you have got the magnetic field over here. In this particular case, if this is the magnetic field, and I am saying the dipole is placed something like this. This is minus m. This is plus m and this is minus m. So dipole moment is in this direction. So here m and b are opposite to each other, anti-parallel. So in this particular case, could you please tell me what is the net force? Sir, on this positive negative pole, force is in the backward direction. On the positive pole, force is in the forward direction. So clearly I can say net force is equal to 0. What is the value of net torque? Sir, net torque is equal to, that is mb sine of 180. So net torque is also 0, sine 180 is 0. So can I say here also body is in the stable, body is in the rotational and translational equilibrium. Bodies in the rotational and translational equilibrium. Yes. And my dear friends, we say potential energy in this case is minus m. Why did I write minus PE? It is actually minus MB. Minus MB. Minus MB. Because we are talking about the magnetic dipole. So it is minus MB cos of 180. Cos 180 is minus 1. So U will come out to be plus MB. So this is what we call the maximum potential energy. This is what we call the maximum potential energy. Okay? This is called the maximum potential energy. And guys, if this is the maximum potential energy, so we say this is unstable equilibrium. Okay. And one more thing, when theta, if theta is equal to 90 degrees, keep this thing in your mind. So this will be the magnetic moment in that case, that magnetic field is forward. So here we say in this particular case, torque is maximum because MB sine theta, sine 90 is 1. And potential energy will be minus. U is equal to minus, we say MB cos of 90. Cos 90 is 0, so potential energy will be 0. Okay. I hope this is crystal clear till over here. Now guys, a bar magnet is hung by a cotton thread in a uniform magnetic field in its equilibrium state. It says that you have a bar magnet over here. This is the magnetic field. In this magnetic field, you have a bar magnet placed. In its equilibrium state, means this is minus M, this is plus M, something like this. Angle between this and this is 0 degrees initially. The energy required to rotate it by 60 degrees is W. If we rotate it by 60 degrees, if you rotate this by 60 degrees, this is plus M. So if you rotate this by theta is equal to 60 degrees. If you rotate it by 60 degrees. How much energy is required? That is W, it is given. Torque required to keep this in the new position is, see guys. If you rotate it by 60 degrees, what I'm saying is that, sir, this will again apply the force in the forward direction on this minus M backward direction. Don't you think that again torque will be created which will bring the back, okay? Which will bring the back, yes. So torque will bring it back. Now to hold the dipole in the same position, you have to apply the torque in opposite direction, okay? So we say to hold the dipole at theta is equal to 60. We have to apply torque. We have to apply torque opposite. Torque in opposite direction. In opposite direction. We have to apply the torque in opposite direction. Okay? Yes. Now, my dear friends, I would want you to listen to me. How much will be that torque? That torque should be exactly equal to this torque. Because if the downward torque is 5 Newton meter, upward torque you are applying 5 Newton, so it will remain in the equilibrium. And that torque will be, that is MB sine of 60 degrees. If you find this torque, how much it will be? MB sine theta, MB sine 60. And this torque will be, that is MB root 3 by 2. Sine 60 is root 3 by 2. Okay. Now, none of the answer is matching with this. No. It says that, see. It says that the energy required to rotate it by 60 degrees W. Let's find the energy. Guys, we say as work done is equal to change in potential energy. We say work done is equal to U final minus U initial. We say the amount of work done you do over here in rotating the dipole or in holding the dipole, that will be stored in the form of potential energy, yes. And let's find that potential energy and put that potential energy equal to W, because it is saying the energy is W at 60 degrees. So we say this work done will be final potential energy minus PE cos of 60 degrees, because finally it is at 60 degrees. So final potential energy is PE cos minus MB, not PE, MB, minus MB cos of 60, then minus initial is minus MB cos of 0 degrees. Okay, so we say this will be cos 60 is 1 by 2. So this will be W is equal to minus MB divided by 2. Cos 60 is 1 by 2. Minus into minus is plus. Cos 0 is 1. Minus M plus MB. So plus MB minus MB by 2. It will be MB by 2. So work done came out to be MB by 2. MB divided by 2. Guys, this is the energy and this is the work done. Because of this work done, this much energy is stored. Okay. Now. So this is equation first. We say from equation first, can I say torque will be simply MB by 2. Instead of MB by 2, we'll put W. So W will be root 3. W root 3. So which option? Okay, we have got this. Okay. The question is, a magnetic dipole is placed at an angle of 30 degrees with the magnetic field intensity. Okay. It says that this is the magnetic field over here. Okay. And its intensity is 10 raised power 4 Tesla. Its intensity is 10 raised power 4 Tesla. It experiences, okay, this is the magnetic field over here. This is the magnetic field over here. This is the magnetic field over here. A magnetic dipole is placed at an angle of 30 degrees. In this magnetic field, a dipole is placed at an angle of 30 degrees. Okay. And then it says, experiences a torque of, here torque is acting on this as 5 Newton meter. Calculate the pole strength. We are supposed to find the pole strength. Now guys, we know as we say magnetic dipole moment is equal to pole strength into L. Length of the dipole is given as, L is given as 1 centimeter. So length we know, dipole moment we don't know. Let's find M. We say as torque is equal to MB sine of theta. Torque is given. Okay. So I say M will come out to be simply that is torque divided by B sine of theta. So M will come out to be, torque is given as 5. Magnetic field is 10 raised power 4. Sine theta is sine 30. Sine 30 is 1 by 2. So it will go over here. 2 into 5 is 10. Now guys, we say it is 2 into 5 is 10. 10 upon 10 raised power 4. It will come out to be 10 raised power minus 3. Okay. Okay. 10 raised power 4. Yeah, 10 raised power minus 3. Now guys, in this particular case, we say put here, now M will come out to be this M divided by L. So this is 10 raised power minus 3 divided by, what is the length? Length is 1 centimeter. So 1 centimeter will be 10 raised power minus 2 meters. 10 raised power minus 2 with this 3. So it will come out to be 10 raised power minus 1 ampere meter. Okay. Ampere per meter. Ampere per meter. Okay. What is this? For it is ampere meter square divided by this meter, this ampere meter. Ampere meter. Because for this it is ampere meter square. For length it is meter. So meter will cancel, so ampere meter.
Okay, this is an important question. And it's a good question. I want you to focus exactly on this. Okay? I want you to focus exactly on this. Now, guys, you solve it. I'm giving you the time of 3 minutes and I'll go to the washroom and you solve it. I'll keep it up. I'll keep the recording as it is. Okay, guys. Now, if you take a look over here, a bar magnet of magnetic moment 0.1.5 joule per Tesla is aligned. It is aligned with the direction of uniform magnetic field of 0.22 Tesla. What is the amount of work required to turn so as to align its magnetic moment normal to the field? Okay. First, it says that if this is the magnetic field over here, okay, in this magnetic field, you have got a bar magnet. Okay, and you are basically rotating this bar magnet such that it becomes normal to the field. You are rotating this bar magnet. This is minus, this is plus, such that
angle is made how much? 90. What does it say? It says that what is the amount of work required to turn the magnet? If you have to turn this magnet so as to align its magnetic moment normal to the field, so that its magnetic moment should make 90 degrees. Okay. How do we find work done? We say work done is equal to change in potential energy. We say work done is equal to U final minus U initial. We say work done is equal to final potential energy. Finally, it is at 90 degrees. It will be minus MB cos of 90 degrees minus, initially it is at 0 degrees, so it is minus MB cos of 0 degrees. Okay. Cos 90 is 0. Minus into minus is plus. Cos 0 is 1. So work done will come out to be MB. Simple. Simple. Now tell me, work done is MB. What is the value of M? M is given as 1.5. What is the value of this? 0.22 B. So work done will come out to be 0.33 joules. Done, 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 done. It's a good question. Then it says, what is the amount of work required to turn the magnet opposite to the field direction? Means this is the field. You have to make the dipole something like this, opposite. So this will be plus, this will be minus. Theta is 180 degrees. Now tell me in this case, what is the work done? Work done will be minus MB, final minus initial, minus MB cos 180. Finally, it is at 180 degrees minus, initial will be minus MB cos of 0 degrees. Okay. So I can say work done will be minus MB cos 180 is minus 1. Minus into minus is plus MB. Then we say minus. Cos 0 is 1. Minus into minus is plus. So MB. It will be 2 times of MB. So MB is 0.33. So this work done will be 2 into 0.33. That is 0.66 joules. Yes. Now, we are heading towards finishing the chapter. We have moving coil galvanometer after this. We have some magnetic properties of magnetic materials and its properties. We have hysteresis loop and vibrational magnetometer. 5-6 topics we have left and we are done with the chapter. Okay. Now guys, listen to me very carefully. Current carrying loop as a magnetic dipole. Guys, I would want you to focus and listen to me very, very, very carefully. Let's suppose you have got a loop over here. You have got a loop over here. Okay. We say in this loop, let's suppose current is flowing as I and radius of the loop is, we say, sir, R. Radius of the loop is R. Okay. We know in the loop, current I is flowing. Current I is flowing. Okay. If in the loop current I is flowing, we know it creates magnetic field. Due to a current carrying wire, it creates magnetic field. So, magnetic field is produced at the center. At the center. Yes. Magnetic field is produced at the center. We have a loop, current carrying loop, in which current I is flowing, R is the radius. We know because of this, magnetic field will be produced exactly at the center. Yes, sir. We completely do agree with you. Then, my dear friends, if magnetic field is present at the center, we can show that magnetic field with the help of a bar magnet. Because when you say, sir, I have a bar magnet over here, we say it creates the magnetic field around it. Yes. Similarly, this loop also creates magnetic field. And I will show that magnetic field with the help of a bar magnet over here at the center. What is wrong in showing that? No problem. I can show that. Okay. So I'll show that with the help of this bar magnet over here. Okay. And we say magnetic field is produced at the center. Okay. Like a bar magnet. Bar magnet. So we consider a current carrying loop, a current carrying loop as a magnetic dipole. As a magnetic dipole. So we consider a current carrying loop as a magnetic dipole. As simple as that. So if this is a loop in which current is flowing, R is the radius, so we'll consider this as a magnetic dipole. Yes, sir. We'll consider this as a magnetic dipole. Now, we know magnetic dipole has a dipole moment, and this will also have the dipole moment. And it will have a dipole moment. And that dipole moment M is equal to, we say I into A. I is the current flowing in the loop, A is the area of the loop, A is the area of the loop. Okay. And direction of this and direction of M is same as the direction of magnetic field due to the loop. So whatever is the direction of the magnetic field, same will be the direction of magnetic moment. See guys, if this is the loop, current is flowing in this direction. Curl your fingers along direction of current, thumb is pointing inwards. So we say magnetic moment will be also perpendicular to the area of the loop. Magnetic moment is also perpendicular to the area of loop. Now this is one loop over here. Can I say for n number of loops, if there are n number of loops in the coil, we say magnetic moment in that case will be, we say NIA. Magnetic moment in that case will be NIA. Okay. I hope this is crystal and clear. It's a simple concept. I hope this is crystal and clear. There is no doubt in that. There is no doubt in that. I believe so. Okay. Yes. Now, my dear friends, let's basically move on to the question. See guys, find the magnetic moment of a thin round loop carrying current I. You have got a thin round loop. It has current I in it. Okay. If the radius of the loop is, we say, sir, R, that is given as 100 mm, and magnetic field at the center is 8 Tesla. You are supposed to find the magnetic moment. Guys, we say as magnetic moment of this loop is, we say, sir, I into A. I is the current, A is the area. Area, we can say area will be simply, that is pi into R square. Area of the loop is pi R square. But when it comes to the current, how do we find the current? Guys, see, we say as magnetic field at the center of the loop is how much? Mu naught I divided by 2R. We have studied this. This is the magnetic field due to the loop at its center. Find the current over here, take it. So current will come out to be simply, that is 2BR divided by, we say, mu naught. 2BR divided by mu naught. Now put it over here. Call this as equation first. Put in equation first. So you can say this magnetic moment will come out to be, instead of current, you can write 2BR divided by mu naught into pi R square. So now this magnetic moment will come out to be, R into R is R cube. 2B, we say R cube, and then we say pi divided by, we say, mu naught. This is the value of magnetic moment. This is the value of magnetic moment. I believe everybody is able to understand.
Okay, now you can put the value of magnetic field that is given as 8 Tesla, R is given as 100 mm, pi is 3.14, mu naught is 4 pi and 10 raised power minus 7, and you can clearly find the value of magnetic moment. Next, this is a good question actually. See guys, when it comes to this question, just remember, here you are given a loop something like this. The current in the loop is flowing something like this. Okay? Okay, something like this. And it says, what is the net magnetic moment of this entire loop? Guys, see. It is something like this. It is something like this. It is something like this. Okay? I hope you are able to understand. This is the upper part of the loop. Okay? This is the lower part of the loop. Whenever you have such questions, we say break this into two loops. This is the first loop. This is the second loop. Whenever you see the question sum of something like this, we say break. I'll write over here. Break into two loops. We say break into two loops. Simply. Now guys, what I want you to do is, sir, in this, if we consider the first loop is A, B, E, F, A, B, E, F, A. And another one is B, C, D, E, B. B, C, D, E, B. This is the another loop. And my dear friends, sir, in this loop, current is not flowing. How can you break this into two loops? What we'll do is that, consider the current in this loop in this direction. Due to this loop, current flows from B to E. Okay? And due to upper loop, see, in completing the current, we say current flows something like this. This is current due to which one? Current due to second loop. Okay? This is current due to which loop? Current due to first loop. And both are equal. We say I2 is equal to I1 is equal to I. Okay? And this I2 is because of the first loop. We say I2 is due to second loop. I1 is due to first loop. And clearly you see in this particular case, net current will be 0. Yes? Now tell me one thing in this case. Guys. Now this is a complete loop. Find the magnetic moment of this loop. Guys, how do we find the magnetic moment? I say if this is the loop, current is flowing something like this. Curl your fingers along direction of current. Thumb gives you the direction of magnetic field. And whatever is the direction of magnetic field, same will be the direction of magnetic moment. Now, because of this, guys, we say current is flowing something like this. Curl your fingers, thumb is pointing downwards. So magnetic moment of this will be downwards. Okay. And when it comes to this, curl your fingers. Magnetic moment of this will be something like this, inwards. This is M. This is downwards, M. This is inward. And you can clearly see it's in 3D. First one is downward, another one is inward. They are making the angle 90 degrees. Okay. So I say it is something like this. This is M and this is M. And this over here is 90. So whenever you have two vectors which are making 90 degree with each other, resultant will be, net in this case will be under root of 2M. This is the answer. And you can write over here a root 2 I into A. Current is given as 2 ampere. Okay. This is root 2 ampere. And area will be length into breadth. Okay. Length into each side of those 10 centimeter. So 10 into 10 raised power minus 2 into 10 into 10 raised power minus 2. So this solve it and you will get the magnetic moment. Now guys, let's take a look over here. Orbital magnetic moment of an electron. Let's suppose you have got over here a ring. Okay, you have got over here a ring. Now when it comes to this ring, we say when it comes to this ring, see, in this particular case, when it comes to this ring, don't say it is a ring. Let's suppose you take an atom, okay? At the center of the atom, you have got the nucleus. And we know around the nucleus, electron is revolving. Around the nucleus, electron is revolving. This is the electron which revolves around the nucleus. And it has got mass m. It has got velocity v. And this radius is given as r. We know in an atom, at the center of the atom, we consider it as nucleus. And around the nucleus, electrons are revolving. Okay. Now I'll just write over here. We say an electron revolves around the nucleus. An electron revolves around the nucleus. And electron has got negative charge, which has negative charge. So whenever charge moves, revolves, we say current is produced, because current is produced due to the flow of charge, which has negative charge, and current is produced. Okay. So what I'm saying is that an electron is revolving around the nucleus. Electron has got negative charge. And we say when charge moves, current is produced. Okay. Now, if electron moves in this direction, current is produced in the opposite direction. You should know it. Direction of current is always opposite to the direction of electrons. Now, if the current is produced over here, don't you think it looks like now a current carrying loop, and it looks like a current carrying loop, because current carrying loop also looks something like this. Okay, so if it looks like a current carrying loop, so it behaves like a magnetic dipole. So it behaves like a magnetic dipole. So it behaves like a magnetic dipole, and it will have magnetic moment. It will have magnetic moment. Okay, yes, it will have magnetic moment. Now, my dear friends, we say when it comes to the magnetic moment, we say magnetic moment is I into A. Now, what is I? I is current. And we say here, if we want to find the current is charge upon time. And what is the charge on an electron? That is E. And what is time over here? That is T. Okay. And if we want to find the time, guys, understand this very carefully. We say speed is equal to distance upon time, and take it over here, and we can say time is equal to distance upon velocity, or distance upon speed. And if I am saying this electron is covering this complete circle, how much distance it is covering? Circumference, that is 2 pi r divided by, with what velocity, sir? With v. Okay, now put in equation first. We say put in first. If we put this in first, so we can get the value of current over here, that is E divided by, and instead of T, you can put 2 pi r divided by V and take this in the numerator. Okay, this is the value of current. Now, we say magnetic moment is I into A. So we say magnetic moment is,
What is the value of current? We say that is EV divided by 2 pi r. Okay. And when it comes to the area of the loop will be simply that is pi r square. Area of the loop will be simply pi r square. Now I can clearly say in this particular case, this pi and this pi will cancel, and this will cancel. So I can say this will be that is EV and this is R divided by 2. This is the magnetic moment of an electron. This is the orbital magnetic moment. Magnetic moment of an electron. This is the orbital magnetic moment of an electron. Okay. Yes. Now, one more thing you should know, that is, if let's suppose this is a particle, it has mass m, it is moving with a velocity v, and this is the reference point over here. So with respect to this reference, let's suppose from here to here distance is r. With respect to the p, always remember, if I say with respect to p, if observer is at p, we say this particle will have angular momentum. Please remember it right now directly. We say this particle has a momentum of mv, linear momentum. When it comes to with respect to this particle, it is moving angularly. So this particle will have angular momentum with respect to p. We say angular momentum of this particle is mvr sine of theta, where theta is the angle between r and v. If you extend this r, so this will be the theta angle. So any particle which is moving angularly, it will have angular momentum. Sir, it is moving linearly. With respect to this, it is moving angularly. See, angle is made. Now, here we say in this particular case, okay, we say angular momentum here, angular momentum of an electron revolving in an orbit. Angular momentum of an electron revolving in an orbit. We say that is L is equal to, that is mvr sine of theta. It is like guys, you have this nucleus, and around the nucleus we say this electron is revolving. This electron is revolving with velocity v. This is r, okay, and its mass is m. Could you please tell me what is the value of theta over here? 90. So here it is L is equal to mvr. Let's call this as equation number 3rd, okay, and let's call this as equation number 2nd, okay. So this is the angular momentum of an electron revolving in an orbit. Now we say divide first and second. What is that? That will be m divided by L. And what is m? M is EVR by 2. We say that is EVR divided by 2. And that what is L? L is MVR. VR will cancel. So m divided by L is what we call E by 2m. Okay. And my dear friends, this is called Gyromagnetic ratio. This is called Gyromagnetic ratio, and also you can call it or a relation between M and L. Either you call it the Gyromagnetic ratio or you call it the relation between M and L. It's one and the same thing. Either you call it the Gyromagnetic ratio or you call it the relation between M and L. It's one and the same thing. Okay. Done with this one also. Let's move on to the moving coil galvanometer.
let's move on to the moving coil galvanometer. Now see guys, when it comes to moving coil galvanometer, I would want you to understand one thing over here. What is a moving coil galvanometer? We say it is a device which is used to detect the current. And one more point, it also measures the current. It also measures the current. It is a device which is used to measure the current. It is a device which is used to detect the current, or it is a device which is used to measure the current. Yes, absolutely cool. Now guys, understand one thing very carefully. Here we have to understand how galvanometer measures the current. Okay, here we have to understand how moving coil galvanometer measures the current or measures potential difference. Now see, let's suppose first we'll do the construction. First we'll do the construction of galvanometer. See, we'll take a magnet over here. This is the north pole. Okay, this is complete magnet. This is the north pole of the magnet. And we'll take the south pole of the magnet from this side. Okay. And in between the two, we'll place a coil. We'll place a coil of n turns. In between the two, we'll place a coil of n turns. Like I'll show you. Yes, this is the exact figure. If we construct a galvanometer, you have got a north pole over here of the magnet. You have got the south pole of the magnet over here. And then we say you place the coil. This is the coil. This is the coil. I'll just show you. I'll just write it over here. This is the coil of the galvanometer. Okay, in which current flows. This is called the helical spring. Helical spring. Okay. And this over here, guys. This over here, guys. Just a second. Yeah, this one. This one is the jockey. This one is the jockey. This one is the jockey. Sir. See guys. Jockey, and this is the meter. This is where the reading is shown. So if you send the current in the coil, so basically this jockey will deviate and it will show you, sir, it is 10 ampere, so it will show you 10 ampere. If it is 15 ampere, it will show you 15 ampere. This is how the galvanometer actually looks like, and this is the construction of galvanometer that we say. Okay. Yes. Simple words, we say this is the moving coil galvanometer. Just a sec. Now guys, I would want you to understand certain things. What is that? What is that? I'll tell you. See. So basically, this is what we call the moving coil galvanometer. Now, we have to understand how current is produced, how galvanometer measures the current. Here we have to see how galvanometer measures the current. Here we have to see how galvanometer measures the current. Now guys, see, listen to me very carefully. First, when you place the coil in which current is flowing, that current which you want to measure in this magnetic field. See, magnetic field is from north pole to south pole. Magnetic field is from north pole to south pole. Keep that thing in your mind. And in this magnetic field, in between these two magnets, you place the coil. Okay. Then, my dear friends, listen to me very carefully. Don't you think that over here, we say, here, coil is placed in a magnetic field, yes, your coil is placed in a magnetic field, and that coil in which current is flowing, it behaves like a magnetic dipole.
So a magnetic dipole is placed in an external magnetic field. If current is flowing in the coil, means it behaves like a magnetic dipole. And that magnetic dipole is placed in the external magnetic field. So we can say this magnetic dipole is placed in an external magnetic field. And we know, previously I have told you, whenever we place a magnetic dipole in an external magnetic field, we say torque will be produced over here. Okay, so torque is produced in the coil. So torque is produced in the coil. And could you please tell me what is the value of that torque? You say, sir, that torque is mb sine theta. We have studied torque is mb sine theta. And tell me one thing, guys. I'm saying this is the coil placed something like this. Okay, magnetic field in this particular case, this is mb. Could you please tell me what is the direction of the magnetic moment over here, guys? If this is the coil, magnetic moment is always perpendicular to the coil. Magnetic field is forward, magnetic moment is this. Angle between magnetic field and this is forward, this is downward, is 90 degrees. So here I can say torque will be simply that is mb. Now what is this m? M is the magnetic moment of the coil, magnetic dipole moment. We say as magnetic moment of the coil is that is simply I, and I write over here n I a. If there are n number of turns in the coil, I is the current, a is the area of the coil. So this will be the magnetic moment. I can write, so this torque will come out to be NIAB. Yes. Now guys, so in this moving coil galvanometer, when you place the coil in the magnetic field, torque will be created. Since you are sending the current over here, due to current, magnetic moment will be there, and magnetic moment or magnetic dipole is placed in the external magnetic field, torque will be produced. And when torque will be produced, I can say torque will be produced in the coil, and due to this torque, guys, see, due to this torque, coil rotates. Okay, and if coil rotates, guys, this jockey is connected to this coil only, so jockey will also rotate. Coil rotates and jockey will also rotate. So jockey will also rotate and shows reading on the meter. So if jockey rotates, so I can say in this particular case, if jockey is rotating, it will show the reading of the meter. More it will rotate, more it will show the reading. So can I say in this particular case, guys, torque is directly proportional to current. If more is the current, more will be the torque produced. More coil will rotate, more reading it will show. This is how the galvanometer actually works. So basically in a galvanometer, a coil is placed in the magnetic field. So when current flows, torque is created, coil rotates, jockey rotates and shows the deflection, shows the reading. As simple as that. Now guys, since we saw how the galvanometer measures the current, now if let's suppose jockey is showing you 10 ampere, when you remove the current, you have to bring the jockey back. Yes, you have to bring the jockey back, because jockey should come back to the original position 0. It's not like you are sitting in the car. Driver is increasing the speed, it reaches 160 km per hour. While he stops the car, it is still showing 160 km. No, it should come back. Jockey should come back from on the meter. So I'll just write to bring
the jockey back, to bring the jockey back, we use helical spring. Helical spring. Okay, which creates a restoring torque. We use helical spring which creates restoring torque. Guys, because of this torque, jockey moves forward, it deviates, shows reading. Now you want to bring jockey back, you use this helical spring. Because of helical, see, it is like, let's suppose you have got the spring over here. This is the block. If you displace the block and place over here, okay, so you are applying the external force in this particular case. And if you now remove the block, it will come back to the original position. It will come back. So basically, which is getting the block back to the original position? It is spring. So spring creates the restoring force over here. And we say this restoring force is K times of X. You might have heard about it. K is the spring constant, X is the displacement. More is the value of the spring constant, more stronger the spring is, more stiff the spring is. Okay, more will be the restoring force in that case. So here, this is the helical spring. It is something like this. If you want to rotate something, you have to use a lot of torque. Now, while you remove it, it will come back. So it is coming back because of this spring, helical spring. It is bringing the jockey back because of the helical spring. It is not the normal spring. Okay. And my dear friends, listen to me very carefully. When it creates the restoring torque, we say that torque restoring will be equal to C theta. Like spring creates restoring force. That restoring force is K times of X. X is the linear displacement. If you take the block, how much you have displaced the block in case of the normal spring, that is X. Here, how much you had deviated, how much it has rotated, that is theta. Here it is K, here it is C, here it is torque, here it is force. And the C is what? Spring constant, helical spring constant, where C is helical spring constant. Where C is helical spring constant. Okay. Where C is helical spring constant. More is the value of C. We say more stiff the spring will be. I'm saying you have got the two springs over here. You have got the helical spring, another helical spring. Value of C is large, value of C is less. So now value of C is less means you can easily rotate this spring, no problem. It is not that stiff. If C is large, it is very difficult to rotate. Or if the spring, if K is large of a spring, it is very difficult to elongate. It is very difficult to compress. If it is small, easily elongate, easily compress. Okay. Now guys, we say this restoring torque should be equal to this torque. If you say this torque is more, this torque is less, so it cannot bring it back. We say this torque should be equal to this torque. If this is a block, if this is thus 10 Newton force, you have to apply, you want to bring it back, you have to apply 10 Newton or little greater than 10 Newton. Then only it will be brought back. So we say here, TR should be equal to tau. Then only spring, then only jockey will come back. Then only jockey will come back. Okay. Now guys, so we say, so I can say, what is the value of that torque? MIAB should be equal to C theta. This is called the equation. This is called the equation of moving coil galvanometer. This is called the equation of moving coil galvanometer. Okay. This is called the equation of moving coil galvanometer. Now guys, one more thing. Could you please tell me, in this case, what is the value of current? I say current in this case will be C theta divided by NAB. Yes. Now guys, let's discuss the galvanometer sensitivity. Or first one we talk about over here, current sensitivity. Current sensitivity. What does current sensitivity of a galvanometer actually mean? We say it is how much sensitive the galvanometer is. It is how much sensitive the galvanometer is. Guys, what is sensitiveness? If I say that person is very sensitive, means if you crack a little joke with him, or if you make a roast of him, he'll become very angry. He's very sensitive. You cannot crack joke with him. Or if you scold him, if you tell him something, okay, and he'll basically, he won't be able to, we say he becomes sad. Why? We say because he's very, very sensitive. You cannot say things to him which are depressing. Why? Because he's sensitive. So that's what we say, sensitivity of a galvanometer. What does sensitivity mean? If you have a galvanometer, okay, we say if you send a very small amount of current is very small, it is still able to measure that current. We say galvanometer sensitivity is very large because it is able to measure even very small currents. That is what we call the sensitivity. So can I say more is the current sensitivity? We say it can measure even very small amount of currents. Yes. Okay. So we say it is how much sensitive galvanometer is. Even if we send very small currents, it will measure those. Even if we send very small currents, we say it will measure those currents. Now guys, I want you to understand and listen. When it comes to this current sensitivity, we represent it with SI. SI means current sensitivity. Guys, tell me one thing. When it comes to equation of moving coil galvanometer, as we say C theta is equal to NIAB. We say C theta is equal to NIAB. This is the equation of moving coil galvanometer. Okay. Now, in this particular case, I want you to take this I and divide it with the current I. What will you get? That is NAB divided by C. This is what we call SI, current sensitivity. So simply, I can say, sir, current sensitivity is theta divided by I. This theta by I is current sensitivity. Okay. So you can keep this in a box, or you can say this SI is, that is NAB divided by C. Guys, now clearly you see in this particular case, see, SI is inversely proportional to spring constant. What does that mean? Means if spring constant is large, we say current sensitivity will be less. What does that mean? If spring constant is large, it is very difficult to rotate the spring. It is very, and this jockey is connected to the spring only. If C is very large, so if you send current, sir, because of the current, we say torque is produced. Okay, because of the torque, we say coil will rotate. Now, if C is large, if you are sending small currents, so this helical spring will not let the jockey to rotate. Why? Why? Because C is large. C is large. We say spring will be very stiff. It will be very difficult to rotate. If the spring is very difficult to rotate, coil will not rotate. If coil will not rotate, jockey will not rotate. If jockey will not rotate, it will not show you the deflection. It won't be able to measure the current. So if you send large current, then large torque will be produced. Okay, large torque. Then coil will rotate. Then it shows some deflection. So that's why we say C, if C is less, means this coil can easily rotate. This coil would be easily rotated over here. If the coil rotates easily, jockey will rotate easily and it will show more deflection. So that's what I was saying exactly in this particular case. See, C is large, current sensitivity will be less. As simple as that. And current sensitivity is inversely proportional to current. Even if you send very small current, sensitivity should be large. So means if a galvanometer has got good sensitivity, means it is a good galvanometer. Okay. And if magnetic field is large, current sensitivity will be large. Okay. Now let's talk about voltage sensitivity. Voltage sensitivity will be SV. Guys, tell me one thing. SI is theta by I. Don't you think that SV will be theta divided by V? Yes. Now find V. I can say V is equal to I into R, where R is the resistance of the galvanometer. I can say V is equal to, what is the value of current? Current is C theta by NAB. I can write over here C theta divided by NAB into, we say, sir, R. So we got this as V. Now put it over here. Okay, so I can say SV will come out to be theta divided by V, that is C theta R divided by NAB. Take that in the numerator, NAB. Theta and theta will cancel. So I can say in this case, SV will come out to be NAB divided by CR. Okay. Okay. This is the voltage sensitivity of the galvanometer. And one more thing I just want to tell you, NAB divided by C. NAB divided by C is SI. Also, I can say SV is equal to SI divided by, we say, sir, R. So you can say this is the relation. This is the relation between SI and SV. This is the relation between SI and SV, where R is the resistance of the galvanometer. This is what we call we are done with the galvanometer, done and dusted. There is nothing more in this one. Let's move on to the questions. Voltage sensitivity is also done. Okay, let's delete this slide. Okay, now see, current sensitivity of a moving coil galvanometer is 5 division per milliampere. This is SI in this case is given as 5 division per milliampere. Sir, what does a division per milliampere mean? See, it says these are what we call the divisions kind of. Okay. If you are sending 1 milliampere, it will show you 5 divisions. That is, a reading will be 5 division per milliampere. Okay. Okay. And in this case, it is milliampere. If you want to convert this milliampere into ampere, 1 milliampere is equal to how many ampere? 10 raised power minus 3. So if it goes in the numerator, it will become 10 raised power plus 3. That is 5 into 1000 will be 5000. So 5000 diV per ampere. Then, and voltage sensitivity is given as SV. This is NEET 2018. SV is given as 20 diV per volt. We are supposed to find the resistance of the galvanometer. Resistance of the galvanometer. Guys, see. Resistance of the galvanometer will be SI by SV. SI divided by SV. SV. What is SI? That is 5000 divided by what is SV? 20. This and this will cancel. 500 divided by 2 is 250 ohm. 250 ohm is the resistance of the galvanometer that is mentioned over here. The coil of a moving coil galvanometer has an effective area of the galvanometer is given as 5 into 10 raised power minus 2 meters square. It is suspended in a magnetic field. Magnetic field in this case is given as 2 into 10 raised power minus 2. Okay, Weber per meter square. Okay. It is basically, what kind of unit is this, sir? Weber per meter square. We say flux is equal to magnetic field into area. So we say magnetic field is equal to flux divided by area. For flux it is Weber, for area it is meter square. If the torsional constant of the suspension means value of C is given as 4 into 10 raised power minus 9 Newton meter degree inverse. See guys, I am showing you all these. Okay, tau is equal to, okay, one more thing, sir, what is the unit of magnetic moment? We say magnetic moment is I into A. Okay, for I it is ampere. Okay, and for area it is meter square. That's why I was saying ampere meter square. And what is the unit of pole strength? We say M is equal to M into L. So this small m is capital M divided by L. For capital M, it is ampere meter square divided by meter. This and this will cancel, so it is ampere meter. And torque, and let's write this, torque is C into theta. Now guys, C will come out to be tau divided by theta. For torque, what is the unit? That is Newton meter. What is theta? That is degree. So that is Newton meter degree inverse. I hope there is no confusion left, ladies and gentlemen. Okay, now, so I say this is Newton meter degree inverse. Find the current sensitivity. We are supposed to find SI. What is the formula for SI? Directly you have to use what is the formula for SI? NAB divided by C. Direct formula based question. NAB divided by C. I can simply say SI is NAB divided by C. Okay. When number of turns are not given, in that case, take number of turns as 1. So it is 1. Just put the values, guys. Okay. You can find it out. Okay. Put the values over here and solve it. Next, you have got over here this. A moving coil galvanometer has 100 turns. And each turn has an effective of 2 centimeters square. So number of turns is 100. Okay. And in this particular case, area is given as 2 centimeter square. Okay. 2 centimeter square. So if you want to convert this into meter square, what will you write? 2 into 10 raised power 2 whole square. So 2 into 10 raised power 4, 10 raised power minus 4. Okay, meter square. What will you write over here? This will be 2 into 10 raised power minus 4 meter square. Because 1 centimeter is 10 raised power minus 2 meter and its whole square. It will become this. Next, the magnetic field produced is, so magnetic field is 0.01 Tesla. The deflection, theta is given. The deflection in the coil is 0.05. When a current of 10 milliampere, I is equal to 10 milliampere. So that is 10 into 10 raised power minus 3 ampere is passed through it. Find the torsional constant. You are supposed to find the value of C. Guys, directly we say use NIAB is equal to C theta. That is the equation of moving coil galvanometer. C will come out to be NIAB divided by theta. Now everything is given over here. Put up the values, get the answer. Next. In a moving coil galvanometer, the deflection of the coil is related to the electric current by the relation. Guys, see, we say as C theta is equal to NIAB. This is the equation of moving coil galvanometer. Clearly, theta and I have the direct relation. More is the current, more will be torque, more jockey will deflect more, so theta will be more. So I is directly proportional to theta, so I guess this option B is the correct option. Next. In order to increase the sensitivity of a moving coil galvanometer, one should decrease. Guys. We say SI is equal to NAB divided by C. In order to increase the sensitivity, if you want to increase the sensitivity, one should decrease. You should decrease torsional constant. I have already discussed this. Okay, the torsional constant of its suspension. Number of turns, if you increase number of turns, SI will increase. If you increase area, SI will increase. If you increase magnetic field, SI will increase. So option B. Okay. Two galvanometers A and B require. See guys, I'll show you over here. This is the galvanometer A. This is the galvanometer B. Two galvanometers A and B require 3 milliampere and 5 milliampere. This galvanometer requires, I say 3 milliampere. This galvanometer requires, I say 5 milliampere. Two galvanometers require 3 milliampere and 5 milliampere. Okay, yes. Two galvanometers require 3 milliampere and 5 milliampere, respectively, to produce the same deflection. So theta is the deflection, theta is the deflection. Means, guys, it is saying you have a galvanometer, two galvanometers. You are sending the current of 2 milliampere. So it is showing some deflection theta, 20 degree. Another galvanometer, you are sending 5 milliampere. It is showing the same deflection, theta, 20 degree. Okay. We are supposed to say, to produce the same deflection of I naught divisions. So theta in this case is given as I naught. In this case is given as I naught. I naught is the theta value of theta. Then A is more sensitive than B. B is more sensitive than A. A and B are equally sensitive. Guys, see. We say as. When it comes to the sensitivity of a galvanometer, we say theta divided by I. Theta is same in both. So means theta is constant in both. So we say SI is inversely proportional to the current. So the one in which current is more, sensitivity is less. So we say sensitivity of B. So I can say sensitivity of B is less than sensitivity of A. Because in this current is more, so sensitivity will be less. So A is more sensitive than B. Okay. Next. Magnetic field lines. Guys, when it comes to the electric field, you show electric field with the help of the electric field lines. Like you are saying, I have got a positive charge over here. In case of the positive charge, you say electric field is away from the charge. Something like this. Electric field is away from the charge. Okay. In case of the negative charge, and you are showing these this electric field with the help of electric field lines. Similarly, when you have a magnet, let's suppose this is a bar magnet. This is South Pole, this is North Pole. Here also, it has got the magnetic field, and you have to show that magnetic field with the help of magnetic field lines. Okay. These are from north to south, outside of the magnet. Outside of the magnet, they are from north to south. And from south to north, inside of the magnet. The direction is from south to north, inside of the magnet. Like in case of, this is positive charge, this is negative charge. We say electric field is from positive charge to negative charge. In case of positive charge, electric field is away from the charge. In case of negative charge, electric field is towards the charge. So it is from positive to negative. Here, inside it is from south to north, outside from north to south. Next. Always form the closed loop. You see, they always form the closed loop. From south to north, closed, complete loop. Does not intersect. We say another field line will go something like this. So these two cannot cross. These two will not intersect. It comes and goes at any angle. Like it is saying that if this is the field line, this is south, this is north. If the field lines comes out of the north, it is not like, sir, they will always make 30 degree. They will always make 40 degree. No, no angle is, we say, particular over here, specific over here. It can come out at any angle. It can go in at any angle. Field line density represent magnetic field strength. If I say field lines are more over here, field lines are more over here, density is more. If density is more means field is strong. That's what is mentioned. Vibrational magnetometer. Now guys, see. Vibrational magnetometer is another device. Okay. Vibrational magnetometer is another device. See, we say it is a device which is used to calculate the magnetic moment of a bar magnet. It is used to calculate the magnetic moment of a bar magnet. Yes, it is used to calculate the magnetic moment of a bar magnet. One more thing I just want to mention over here. Let me erase. It is used to calculate the magnetic moment of a bar magnet. Okay. Second point I'll just write over here. It also compares the magnetic moment of two bar magnets. Like if I say you have two bar magnets over here, you want to find the magnetic moment of this, you want to find the magnetic moment of this, you can find it with the help of vibrational magnetometer. You can compare even these two bar magnets with the help of vibrational magnetometer. Yes. How does it actually work? Let me make you understand. How does it actually work? Let me make you understand. See guys, what it does actually is it has got a horizontal field inside it. What are you trying to say? I'll make you understand. Let's suppose I'll take a vibrational magnetometer device. Let's suppose I have this. This is a device. This is a device. Okay. This is the room heater that we use in Kashmir. Imagine this is a vibrational magnetometer. For what we use it? We use it to calculate the magnetic moment of the bar magnet. Okay. We place the bar magnet in it. Okay. And in this vibrational magnetometer, it has the magnetic field present. That is what we call the horizontal magnetic field present.
And in that horizontal magnetic field only we place the bar magnet. We place the bar magnet. Okay, like this is south, this is north. Okay. So we say in a vibrational magnetometer, it has, I'll just say, in a vibrational magnetometer, it has the magnetic field present in it. It has the magnetic field present in it. It has the magnetic field present in it. In which we place the bar magnet. In which we place the bar magnet. In which we place the bar magnet. Now guys, in which we place the bar magnet. Now guys, listen. Okay. Now, then bar magnet is displaced. Bar magnet is displaced. Okay. Now, if we displace this bar magnet over here, we know, due to this magnetic field, torque will be produced, it will come back. My dear friends, see, it is something like this. It is something like this. We say this is plus, this is minus. If you displace this, let's suppose if you displace, this is plus, this is minus. Force will act on this, force will act on this. Torque will be created, torque will be created. When it comes back, it will not stop here. It goes down. It is like pendulum. If you displace this pendulum, it will go here. Then when it comes back, it does not stop over here. It will go here. So it will start oscillating. Okay. Same is the case over here. This will start oscillating. Okay. This will start oscillating. So then bar magnet is displaced and it starts oscillating. It starts oscillating. And when it starts oscillating, it will have the time period. What is time period? In how much time it completes one cycle. And it will have time period. Okay. So this vibrational magnetometer calculates the time period of this bar magnet. This vibrational magnetometer finds the time period of the bar magnet. It will have the time period of oscillation. In how much time it completes? Sir, what is one cycle? Guys, see. If I say this bar, this is a pendulum. It goes from, see. If this is a pendulum, it goes from extreme position. See, it goes from extreme position. Then it comes back. Then it goes left. Then it comes back. This is one cycle. First, it goes from extreme. Then it comes back. Then it goes to left extreme. Then it comes back. That is one time period. Okay, that is one time period. Okay, cool. So we say, and my dear friends, I'll not derive that. Directly we say that time period will be 2 pi under root of I divided by MB. We say this is the time period. This is the time period of the bar magnet. This is the time period of the bar magnet in this external magnetic field. So if you have the magnet over here, if you want to find its magnetic moment, you place it in the external magnetic field or the vibrational magnetometer. So then displace, we say it will have time period, that is 2 pi under root of I by MB. What is this I? Where I is moment of inertia. Moment of inertia. Sir, what is moment of inertia? You have mass guys, see, in linear motion you have linear displacement. Here you have angular displacement. In linear motion you have linear displacement S, you have theta. Here you have linear velocity, you have angular velocity.
Angular velocity plays the same role in rotation or angular as this plays in linear. Here you have acceleration, you have angular acceleration. Here you have force, you have torque. Here you have mass, here you have moment of inertia. So moment of inertia plays the same role in rotational motion as mass plays in linear motion. Directly remember as a M is the magnetic moment, B is the magnetic field. M is the magnetic moment, B is the magnetic field. Okay, yes. M is the magnetic moment, B is the magnetic field. Now guys, here you have got two cases. Here you have got two cases. Okay, that is. Let's suppose you have got the two magnets. You want to compare. This is case one. This is case one. Guys, remember it. You want to compare the magnetic moments of these two magnets. Let's suppose this is M1 and this has got magnetic moment as M2. Case one is when like poles of two bar magnets are kept together. Like you take the two bar magnets, you have to compare their magnetic moment. South pole of this, north pole of this, north pole of this. Like poles of the two bar magnets are kept together. Okay? And here, I would want you guys to directly see, guys, what is the time period of this? T is equal to 2 pi. We say under root of, and this is the magnetic field B. We say I. Both will have the same moment of inertia, same size. If the size is same, moment of inertia is divided by, this will have M1 into B. Magnetic field for both is same. Call this as T1. Then we say time period of this will be T2 is equal to 2 pi under root of I divided by M2 into B. Now, if I say, guys, if I say divide first and second. So what will you say? T1 divided by T2. It will be, guys, see. 2 pi will cancel. I by MB will cancel. And here it remains 1 by a root M1. Here it remains 1 by a root M2. Because this and this is same, this and this is same, this and this is same. Now take this. So I can say T1 divided by T2 will be under root of M2 divided by M1. So this is the time comparison of the time period. Now from this comparison, if you take the square root over here, it becomes square. This is the value of magnetic moment of the two. This is the value of magnetic moment of the two. So M1 by M2 by M1 will be T1 by T2 whole square. So from now onwards, if you have the two bar magnets placed in the external magnetic field such that like poles are kept together, then this will be the ratio of time period. This will be the ratio of magnetic moments. And here, if this is case 2, I'll just mention the case 2 over here, something like this. Case 2 is case 2 when the unlike poles of two bar magnets are kept together. When the unlike poles of two bar magnets are kept together, like you have got in this particular case, this is the magnetic field. In this magnetic field, this bar magnet and this bar, south with north, north with south. Here, magnetic moment will be, you have to remember this. This is, I'll write over here, this is M1 divided by M2. There is a simple calculation, just directly remember. It will be equals to, we say T1 square plus T2 square divided by T1 square minus T2 square. What is T1? T1 and T2 are the time periods of the two bar magnets. Or you can also compare the time period, ratio of the time period also. T1 by T2 is equal to, we say, under root of M1 minus M2 upon, we say, M1 plus M2. Okay. Okay. Let's take a look at this question. The period of oscillation of a magnet in a vibrational magnetometer is 2 seconds. See, guys, this is the vibrational magnetometer. Okay. It says that you have got a magnet over here. Okay. It is North Pole, South Pole. Okay. Like poles are kept together. If it is not mentioned in the question, then keep the like poles together. It says time period of this bar magnet is 2 seconds. Means it completes its one oscillation in 2 seconds. The period of oscillation of a magnet and magnetic moment of this is given as, the period of oscillation of a magnet is 2 seconds. The period of oscillation of whose magnet? 4 times. Okay, it is given as M. You are supposed to find another magnet has got magnetic moment M2 as 4M, 4 times than this. You have to find the value of the time period of this magnet. Guys, what will you say? We say as T1 divided by T2 is simply under root of M2 by M1. We recently saw when the two magnets are placed in opposite sense. So I can say T1. What is the value of T1? That is 2 divided by T2 we have to find is equal under root of M2 is 4M divided by M. This and this will cancel. Root 4 is 2. So 2 by 2 is, so T2 is 1 second. So second will have 1 second. Let's talk about this one. Magnet A and B are geometrically similar. Okay, cool. Okay, cool. Okay. And magnetic moment of A is twice that of B. Okay, you have got the two magnets over here. You have got the two magnets over here. This is south, this is north. Okay, yes, this is south, this is okay. And here, this is north, this is south. Okay. And it says that magnetic moment of first is 2 times the magnetic moment of second. Magnetic moment of A is twice that of B. This is A, this is B. It is A has got twice magnetic moment than B. Time period of oscillation is T1 by T2. When they are like poles and unlike poles are kept together, unlike poles are kept together. Okay, guys, S with north, north with south. Okay, in this case, you have to find the value of T1 divided by T2. Guys, tell me, when unlike poles are kept together, in that case, how do we find T1 by T2? Under root of M1 minus M2 upon M1 plus M2. So I'll just write over here. It is under root of M1 minus M2 divided by M1 plus M2. So I can say T1 divided by T2 is equal to under root of, what is the value of M1? 2M minus M upon 2M plus M. So this is M. So this will be M plus 3M. M and M will cancel. So it will be 1 by root 3. So ratio is 1 by root 3. This is a very important question in this one. This is a previous year question. Now look at this question. It says a vibrational magnetometer placed in a magnetic field, you say. Sir, what is magnetic meridian? Magnetic field. Has a bar magnet. The magnet executes the oscillation with a time period of 2 seconds. Okay. It says that, guys, look at this. It will confuse you. Look at this. You have got a magnetic field B is equal to 24 microtesla. Okay. In this 24 microtesla, You are placing a bar magnet over here. You are placing a bar magnet over here. Okay, absolutely cool. Yes, you are placing a bar magnet over here. And my dear friends, it says that its time period of oscillation T1 is 2 seconds. Okay, it's completing its oscillation in 2 seconds. And then it says when a horizontal magnetic field of 18 microtesla is produced in the opposite direction, then it says finally, what it is doing is that it is finally applying, guys. If this is 24 microtesla, okay, this is 24, it is applying, if this is 24 microtesla, it is applying 18 microtesla in opposite direction. Could you please tell me what will be the net magnetic field finally? You say, sir, 24 minus 18 is, we say, sir, 6 microtesla, and direction is forward, direction of bigger one. So we say finally magnetic field is not 18, but magnetic field finally B2, call this as B1, this is B2 will be 20, sorry, B2 will be 6 microtesla. And in this, you have to tell me what is the time period of the magnet. Simple. It says initially you have got a magnetic field 24 microtesla. This is 24. Okay, 24 microtesla. Time period of the magnet is 2 seconds. Finally, if 18 microtesla is applied in the opposite direction, what is the value of this magnet? What is the value of time period over here? Guys, we say as when it comes to the time period, it is 2 pi under root of I divided by MB. Okay. See, it is talking about the same magnet. Magnet is exactly similar. You have just changed the magnetic field. So here, if I write the time period T1, so moment of inertia will be same for both. Magnetic field will be different. So I can write over here B1, but magnetic moment will be same because you are placing the same magnet in this magnetic field. Magnetic field will be different. And I can say T2 will be 2 pi under root of I divided by, we say M, and then we say B2. Now, if I say T1 divided by T2, what will it be? So we say 2 pi and 2 pi will cancel. I and I will cancel. M and M will cancel. So it will be 1 by root B1 divided by 1 by root B2. So it will come out to be under root of B2 by B1. Yes. So I can say in this particular case, T1 divided by T2 will be simply. T1 divided by T2 will be simply. What is T1? That is 2 seconds. And okay. So I can say T1, what is the value of T1 over here? 2 seconds. So I can say 2 divided by T2 is equal to under root of B2 by B1. What is the value of B2? B2 is 6, B1 is 24. That is 24 divided by 6. 6 ones are, 6 4s are. Root 4 is 2. Okay, T2 will come out to be 1 second. T2 will come out to be 1 second. Okay. Okay. I hope this is clear. Next. Now, guys, let's take a look at magnetic intensity. Let's take a look at magnetic intensity. Now, guys, see, let's take a look exactly at this one. Let's take a look exactly at this one. Magnetic intensity or magnetizing field. Let's suppose I have got over here a ring. I say I have a ring over here. And in this ring, current I is flowing. Okay. And radius of the ring, I am saying this is R. Can I say if I is the current flowing in the ring, magnetic field will be produced at the center? I say in this particular case, due to the current in the ring, or directly I'll say magnetic field at the center is, can I say this is B is equal to mu naught I divided by 2R. I would want you guys to focus completely over here. B is equal to mu naught by 2R. So magnetic field, because of this ring in which current is flowing, radius is R, is mu naught I by 2R. Okay? Yes. Now guys, we say this magnetic field depends upon mu naught. This magnetic field depends upon current. This magnetic field depends upon R. So we say here magnetic field depends upon we say medium means mu naught and the ring itself. Okay, that is current and R, radius. So what is mu naught? Mu naught is medium. For different mediums, mu is different. If you take another medium, we say mu will be different. If you take another medium, mu will be different. So for different mediums, we say mu will be different. And we say I and R. I is the current in the wire. R is the radius of this loop. So means magnetic field depends upon the loop itself. Loop means current and I. These are the parameters which are related to the loop. And mu naught is the medium. Can I say in this particular case, guys, we say here magnetic field without medium. Could you please tell me what is the magnetic field without medium over here? Sir, it will be eliminate this mu naught from this magnetic field. That will be simply, you say, sir, B divided by mu naught. If you have to remove divide, so you say it will be mu naught I divided by 2R divided by mu naught. Mu naught will cancel. So it will come out to be I divided by 2R. And we call this as, we say H. So what is this H? H is also the magnetic field because of this ring, because of this loop without medium. So I say H is also the magnetic field due to a ring. H is also the magnetic field due to a ring without medium. H is also the magnetic field due to a ring without medium. And it is called either you say magnetic intensity or magnetizing field. It is either called magnetic intensity or we say it is magnetizing field. Okay? Yes, sir. It is either called magnetic intensity or magnetizing field. Now, my dear friends, we say for this loop, for this circular loop, value of H is I by 2R. We say in case of a solenoid, let's find magnetizing field. Let's find H. Sir, what is magnetizing field? Magnetizing field is a magnetic field only, but without medium, without mu naught.
So for this solenoid, if I say this is solenoid, what is the magnetic field of a solenoid? Mu naught N into I. If you want to find the magnetizing field over here, we say H will be B divided by mu naught. So can I say what is the value of B? Mu naught Ni divided by this mu naught. This mu naught will cancel. So it will be N into I. It will be N into I. So for a solenoid, H is coming out to be equal to that is N into I. This is the magnetizing field for a solenoid. One more way we define it. We say it is also that field. It is also that field which is used to magnetize a material. It is also that field which is used to magnetize a material. Like I say you have got over here like you have a magnet over here, okay, bar magnet. You place a coin, you stick a coin to this is a bar magnet. So if you have a bar magnet, you take a coin and you place it onto the bar magnet for the complete one night. Tomorrow, next day, when you remove it from that, it will also start behaving like a magnet. Why? Because it has gained the magnetic properties. It has gained what? Magnetic properties. If that coin will now behave like a magnet, why? Because now the coin has attained magnetic properties. Coin is magnetized. So we say it is also that field in which we place a material so that it gets magnetized. Like I say this is the magnetizing field over here in which you place a material. So we say this is the material which gets magnetized. This is a material which gets magnetized. So what is H? H is the magnetizing field, or we say magnetizing field is also that field. Magnetizing field is also that field which is without medium. It's one and the same thing. Next. Okay. Like it is. In simple words, it is how much field you are applying to magnetize a material. It is how much field you are applying to magnetize a material, that is H. Okay. So H is the magnetizing field over here. This material gets magnetized because of this field. Like if you take a coin and stick it with the bar magnet will behave like a magnetizing field. Coin will be the material which gets magnetized. Then you have got intensity of magnetization. Guys, look at this. Intensity of magnetization. I'm saying you have a magnetic field over here, external magnetizing field. I want you to understand this. Okay. In this external magnetizing field H, this is H. Okay. You are placing a material which gets magnetized. What does magnetizing a material mean? If you have, guys, this material over here, you want to magnetize it. So we say kind of small bar magnets are being developed over here. Kind of magnetic dipoles are, because when you say it is a magnetic dipole over here, it's a bar magnet over here, then only you say around this there will be the magnetic field. Either you say magnetic field, either you say bar magnet, or you say magnetic moment. Everything is one and the same thing. So I am saying if a material gains magnetic properties, that means magnetic dipoles have been developed in that material. Magnetic dipoles have been developed in that material. If I say no magnetic dipole is present in this material, so means it is not magnetized. It is not showing magnetic properties. It will not attract any other thing. So we say if a material gets magnetized, magnetic dipoles are being developed inside it. Okay. Now we say when it comes to the intensity of magnetization, you place a material inside this
external magnetizing field. We say this material gets magnetized. Dipole moments are developed inside. Okay. How much it gets magnetized? Okay. How many dipoles are being created over here? That is called intensity of magnetization. Intensity of magnetization is magnetic moment per unit volume. If I say, guys, if I say you have got a magnetic field over here, you have placed the two materials A and B, let's suppose gold and iron. We say, sir, it gets strongly magnetized. A lot of dipoles have been developed over here. Why? Because this material has got a good magnetic properties. Sir, in this case, few magnetic moments are developed. We say its intensity of magnetization is large. In its unit volume, large number of dipoles have been developed. In its unit volume, less number of dipoles have been developed. Okay. So we say intensity of magnetization is magnetic moment per unit volume. How many magnetic moments are in the unit volume? Okay. Okay. If you are magnetizing a material, it tells you how much it has magnetized per unit volume. In unit volume, how many dipoles have been created? Okay. 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 That is intensity. And how do we represent the intensity of magnetization? That is, we say, sir, I. And what is H? And this developed, I is developed inside, H is the external magnetizing field. And we say susceptibility. A lot of students have seen these words before, but I hope now you got the exact feel of these topics. Susceptibility. What does susceptibility mean? See guys, if you have the external magnetizing field and you are placing two materials, let's suppose A and let's suppose this is the material B which is placed inside. Okay. Sir, this gets strongly magnetized. This gets strongly magnetized. This gets strongly magnetized. A lot of dipoles are created. And this does not get strongly magnetized. Only few dipoles are created. So we say its intensity of magnetization is large. Its intensity of magnetization is small. This is not a good magnetic material. This is iron. This is gold. Don't say this is gold. This is some material, something else. Okay. Now, my dear friends, in this particular case, can I say here, output is large. Output is large. Here, output is less. Why? Output means how much it gets magnetized. What are the results? Results are very good, sir. Results are not very good, sir. Magnetization is large, sir. Magnetization is now not large, sir. So we say this, what is this H? H means input. How much you are applying, how much magnetic field you are applying. So I am applying large magnetic field. Okay. I am applying in large input. Okay. So we say this output by input, how much it gets magnetized compared to how much you are applying. Sir, I am applying, sir, H. Output will be I. Okay. How much output you are getting in comparison to input. That is called susceptibility. So susceptibility is I divided by H. Either you say output by input or you say this susceptibility we represent with this chi. This chi. Okay. So I divided by H. If you are magnetizing a material, it tells you how much it gets magnetized compared to how much you are applying. Okay. 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 So it tells us how much a material is capable of getting magnetized. If I am saying, guys, if I am saying you have two materials, this is iron, this is platinum. So I say in this particular case, this iron, it has got more susceptibility. Okay. Let's suppose if this is iron, okay, and its susceptibility is large. And if I say this is platinum, its susceptibility is small. Why? Because we say it is capable of getting more magnetized. We say it is capable of getting less magnetized. If you are applying the input, you are getting large output. You are getting less output. So that's why we say this is susceptibility. So susceptibility tells you how much a material is capable of getting magnetized. From now onwards, my dear friends, if I say susceptibility of this material, like if I say you have got two materials, this and this, its susceptibility is large. What does that mean? It has good magnetic properties. It has less magnetic property. Okay, read this out. Okay, one more thing we have over here, that is relation between mu r, relative permeability, and this. I would want you guys to keep these equations in your mind. This relative permeability, this is the relation between relative permeability, okay, and this is, you have got over here this one, mu m by mu naught, 1 plus susceptibility. Okay, guys, what is relative permeability? Like if you remember epsilon r, relative permittivity, okay, it was permittivity of medium divided by permittivity of free space. Similarly here, relative permeability is, we say, permeability of medium divided by permeability of free space. So relation between relative permeability and susceptibility is this. Please keep this in your mind directly. Keep this in your mind directly. And keep this in your mind directly over here. Okay? Because instead of this, you can write mu m by mu naught also. You can write it something like this. Now, types of magnetic materials. Types of magnetic materials. Types of magnetic materials. See guys, when it comes to the magnetic materials, we say there are three types of magnetic materials. We say diamagnetic material, we say diamagnetic material, paramagnetic material, and ferromagnetic material. Sir, what is this? What is this? Guys. When it comes to the dia, para, and ferromagnetic material, understand this very carefully. It simply means if you have got, see, I'll make you understand here. Okay, there are two questions which I want you guys to solve on this. This one, please look at this from your end. Everything is mentioned. And this question also, this was on this one. Please take a look on both of these and take the screenshots and solve it later on from your end. Okay, like this. Sir, like I say, I have got three magnetic materials. This is the material 1, 2, and 3. This is gold, this is platinum or aluminium, and this is iron. Sir, I place this in diamagnetic, I put this in paramagnetic, I put this in ferromagnetic. Why, sir? Because they show different magnetic properties. This has got different susceptibility. They show different magnetic properties. This has got different susceptibility. This has got different susceptibility. So we say on the basis of their magnetic properties, we say, sir, this is capable of getting more magnetized. That's why we are putting this in the ferromagnetic. So the capability of a material to get magnetized, on the basis of that, we are dividing them into three categories: para, dia, ferro. Okay. First, let's talk about diamagnetic materials. Okay. Now, let's suppose if you are taking a crystal of diamagnetic material. Okay. Let's suppose this is a crystal. Okay. We know when it comes to a diamagnetic material, guys, see. We know this crystal is made up of millions of atoms out there. This crystal is made up of millions of atoms out there. Yes, sir. In case of a diamagnetic material, we say crystal is made up of millions of atoms out there. Yes. And now, if you go on in an atom, if you go into this in an atom, if you zoom it out, you see, inside this, we say electrons are revolving in an atom. In a diamagnetic material,
If you check the atom of a diamagnetic material, we say electron will be revolving around the nucleus. Electron will be revolving around the nucleus. Okay. Around the nucleus. Electron will be revolving around the nucleus. Okay. Now, my dear friends, when it comes to the diamagnetic material, we say, just a, yeah. See, in a diamagnetic material, we say paired electrons are present. Sir, what does paired electrons mean? You see, in an atom, if you check its atom, we say it will have 2 electrons. You, sir, I'm bringing this a diamag, this is a gold. Check its atom, it will have 2 electrons. Okay. And these 2 electrons will have opposite spin. What does opposite spin mean? See. Means if this is a diamagnetic material, this atom, this is spinning something like this, and this will have opposite spin. This is spinning in the opposite direction. So, if I say, this will have the magnetic moment, guys, this will have the magnetic moment in the downward direction. Another one, it will have magnetic moment in the upward direction. Because we know if an electron revolves in a nucleus, revolves in an orbit, it will have magnetic moment. This will have magnetic moment, they will have opposite magnetic moment. So we say net magnetic moment, orbital magnetic moment will be zero. What does it mean? So means, we say net magnetic moment for a diamagnetic material in an atom is 0. So means magnetic moment 0 means it does not have magnetic properties. It has no magnetic dipole moments. So it doesn't behave like a magnet. That is what it means. So no magnetic dipole moment over here. Okay. Now, when it is placed in an external magnetic field, example is copper, gold. When this copper, gold is placed in an external magnetic field, if we want to magnetize it in an external magnetizing field, right at H. If we want to, guys, if you have gold, you are saying, I want to magnetize it. I want to increase its magnetic properties. Okay. Place it with the bar magnet, place it in the external magnetizing field. And we saw when you place it in the external magnetic field, we saw it gets magnetized in opposite direction. Dipoles are definitely created over here. It gets magnetized, but in opposite direction. It gets magnetized in opposite direction. Forward, external magnetic field is forward. It gets magnetized in opposite direction. And it gets small magnetized, not highly magnetized. No. Okay. So my dear friends, in this particular case, if it gets magnetized in opposite direction, listen to me very carefully. Don't you think that here susceptibility will be negative? Why? Sorry, intensity of magnetization will be negative. This creation of dipoles is intensity of magnetization, due to which it is created, that is H. Why? Because it is in the backward direction. So negative, it means negative direction. This means positive. So I will be negative over here. H is positive over here. Now guys, if I is negative, don't you think that susceptibility is output by input? And also we call it, this is I divided by H. If I is negative, what about susceptibility? It will be also negative. So susceptibility for a diamagnetic material is negative. And it is small. Why is it small? Because it has less number of dipoles created. So we say I is less. So Hx, this chi is less. And one more thing I just want to mention over here, that is output is less than input, because small magnetization, output is less than input. Net magnetic field is less than external magnetic field. Why? Let me show you. External magnetic field is forward. Okay. It gets magnetized in opposite direction. Let's suppose this is 10 and its value is 2. What is the value of net magnetic field? Sir, that is 10 minus 2. That is 8. So net is less than external. Net is less than external. That is what is mentioned. Okay. Next, take a look over here. In this case, guys. We say also susceptibility does not depend upon the temperature. Now, guys, see. If you have iron over here, if you magnetize this iron, now it behaves like a magnet. It is attracting the things. If you want to decrease its magnetic properties, what will you do?
you will basically increase its temperature, you will heat it. When you increase the temperature, its magnetic properties, its susceptibility will be, it will decrease, it will lose the magnetic properties. But when it comes to diamagnetic material, if you magnetize a diamagnetic material, okay, it will be less magnetized. Now, if you increase the temperature, nothing will happen to its magnetic properties. Susceptibility will be constant. We know its susceptibility, guys, we know, we have studied, its susceptibility is negative and it is constant. Now, if you make the graph of susceptibility versus temperature, it is over here negative and constant. It does not change with temperature. But when it comes to the intensity of magnetization, okay, intensity of magnetization and external magnetizing field. Guys, see. I say this is the external magnetizing field. This is the external magnetizing field. Okay, and it gets magnetized in opposite direction. It gets magnetized in opposite direction. Now, more you apply, if you increase this H, we say it gets more magnetized. I will increase, but in opposite direction. That's what it is showing over here. If you increase the value of if you increase the value of H, here H is increased. I will increase, but in the negative direction. Why? Because I is negative. So that's why graph is from lower side. If I was positive, I would have made graph from the upper side. So here in this case, I varies with H linearly, but in the negative direction. Let's talk about paramagnetic material. Guys, see, when it comes to the paramagnetic material, I want you to understand this. We say it has unpaired electrons. If you take this is a paramagnetic material, platinum, aluminum. If you check its atom, it will have unpaired electrons. It will not have paired electrons. It can be 3, 5, something like that. Okay. Now, my dear friends, this is spinning something like this. This is spinning in opposite direction. This is same. Okay, here we do not say same spin, opposite spin. And if I say this and this will have magnetic moment something like this in the upward direction. This will have magnetic moment in the downward direction. Sir, 2m is upward, m is downward. So net magnetic moment for an atom is not equal to 0. But in diamagnetic, it was equal to 0. Next, it has some magnetic moments, okay? They are in the random direction. Now, guys, if you take a diamagnetic material, we say there are already magnetic moments present in this material. Not like, in paramagnetic. Not like diamagnetic, no magnetic moment was there. Because here, net magnetic moment is not equal to 0, means some magnetic, see guys, what is the net magnetic moment over here? 2m minus m, that will be m. 2m minus m is m. So we say in this particular case, my dear friends, we say they have some magnetic moment, but that is in the random directions. So this is the magnetic moment of one atom. Another atom will have this, another atom will have this, another atom will have this. So due to the random orientation, what is the net magnetic moment for this entire crystal? So we say net magnetic moment is 0. Guys, in paramagnetic material, net magnetic moment of an atom is not equal to 0. But for the entire crystal, in a crystal there are millions of atoms, we say net is 0. Next, if you place this in the external magnetizing field, we say it gets magnetized in the same direction. All these random dipoles are aligned in the proper direction. All the magnetic moments are aligned in a unique direction. Now it behaves like a magnet. If now it gets magnetized, it behaves like a magnet. Okay. Now tell me in this case, guys, tell me in this case, what is the value of susceptibility? That will be positive. What is the value of intensity of magnetization? Intensity of magnetization is positive. Why? Because it is in dipoles are in the same direction. If I is positive, could you please tell me what is the value of susceptibility? That is I divided by H. Susceptibility will be also positive. It gets magnetized in the same direction, but here, it gets magnetized by a small amount. Susceptibility is positive and small. No doubt it gets magnetized in the forward direction, but with a small amount, not highly magnetized, the small amount, okay, in the same direction. In this case, output is greater than input. B net is greater than B external. See, if I say external magnetic field is 10 and internal magnetic field is developed over here 2, but in the same direction. So 10 plus 2, net is 10 plus 2, that is 12. So net is greater than external. That is what I'm saying. Net is greater than external. Susceptibility is positive because same direction magnetized. Susceptibility is small. Why? Because it does not get magnetized by a large amount. Okay. And my dear friends, if you make the graph between susceptibility versus temperature. Now, if this is a magnetized paramagnetic material, if you increase its temperature, it will lose its magnetic properties. Susceptibility will decrease. That's why we say susceptibility is inversely proportional to temperature. Next, and intensity of magnetization versus H. Now, guys, I want you to understand this. If I say you are increasing the value of this H, we say the material which is placed inside, it gets more magnetized, okay? So I in this case will increase. So I is varying with linearly, okay, and I is positive in this case, and it is varying linearly. More you increase the magnetizing field, intensity of magnetization will increase. Then you have got the ferromagnetic material. Now guys, take a look. We say here unpaired electrons are present. Here magnetic field of different magnetic moments attract to form domains. Guys, see, when it comes to a material, I'll make you understand here. Let's suppose this is the ferromagnetic material. Here you have got the some magnetic moments, okay, something like this. So these are the magnetic moments of some electrons. We say they will attract together. They will attract each other. When they attract each other, they come in the same direction. Sir, what are these? These are the magnetic moments of some atoms. If an atom, it has magnetic moment because unpaired electrons are present. So they attract each other and then they form a domain. Okay. Now here, some magnetic moments will align in this direction. They form this domain. Some magnetic moments here will attract each other. They form in this. Here they come in this direction. They form this domain. So these are called the domains. And in the domains, all the magnetic moment are in the same direction. But in a crystal of many domains, the magnetic moments will be in a different direction. So these are the domains, creation of domains. Okay. And when it comes to the net magnetic moment of a domain, that is not equal to 0. Net magnetic moment of a domain is not equal to 0. But when it comes to the net magnetic moment for a crystal, that is 0. In a domain, all of these are in the same direction. But when it comes to a crystal, this magnetic field gets cancelled with this one because this domain has opposite. So that's why for a crystal, it becomes 0. And when you place it in the external magnetizing field, we say it gets strongly magnetized because of the domains. It gets highly magnetized and in the same direction. So can I say in this particular case, guys, susceptibility will be positive. Why? Because it is magnetized in the same direction. I is positive. If susceptibility is positive, and it will be large. Why? Because it is highly magnetized. Example is iron, cobalt, nickel. Now, in this case, guys, see. If you make the graph between I versus H, means if you are increasing the external magnetizing field, we say, sir, it gets more magnetized, not linearly. It will vary something like this. This is the graph in case of I versus H in case of ferromagnetic. Okay, susceptibility is very large, positive. Okay, and one more thing, if you say, if we heat the ferromagnetic material, let's suppose if you heat the ferromagnetic material, we say it will lose its magnetic properties. It will lose its magnetic properties. Look at the graph. If you increase the temperature of the ferromagnetic material, it will lose its magnetic properties, something like this. Okay, now let me show you this graph more clearly over here. Let me show you this graph more clearly over here. This is susceptibility and this is temperature. Now, my dear friends, in this case, we say it has got large susceptibility. So susceptibility is large. As you increase the temperature, susceptibility will decrease. Okay. It will not decrease that much till over here. So it will decrease. Okay. And then at a certain value of temperature, let's suppose this Tc, if you increase more temperature, then it will decrease something like this, like ferromagnetic material. In paramagnetic, we say from here to here it behaves like ferromagnetic. After this temperature it behaves like paramagnetic. Because after this temperature it will lose a lot of its magnetic properties. So this temperature is what we call the Curie temperature. If we heat the ferromagnetic material beyond Curie temperature, it becomes paramagnetic because its domains break. Okay, and we say in this case this will be the graph between susceptibility and temperature. I hope this is crystal and clear. Okay, there is no more detail about this. I have told you all the things. You can take a look of this also. Now, the last topic over here, that is hysteresis. It will take us 10 more minutes and we are good to go. Okay. Now, guys, take a look over here. We say hysteresis. What is hysteresis graph? See, it is the property for ferromagnetic substances. Okay. Para and diamagnetic does not have this property. Now, suppose if we have a material which needs to be magnetized, which we want to magnetize, but which material? Ferromagnetic material. Keep that thing in your mind. This is a ferromagnetic material. Ferromagnetic material. It's a ferromagnetic material. Okay. Now, my dear friends, this is the external magnetizing field you are applying, that is H, in which you are placing this ferromagnetic material which wants to get magnetized. Okay. And we know I will be developed inside this intensity of magnetization. Dipoles will be developed. Okay. Dipoles will be developed. And we have recently studied. Now, guys. I say, in this particular case, just a second. Okay. I say, as you increase, listen to me very carefully. I want you to understand this graph over here. I want you to understand this graph over here. I want you to understand this graph over here. See, guys, I want you to understand this graph over here. We said this is the graph between H versus I. In case of ferromagnetic material, I have told you over here, the intensity of magnetization increases with the magnetizing field, something like this. It does not vary linearly. As you increase the magnetizing field more, it gets strongly magnetized. We say it will increase and it will reach over here. Now, this is what we call the saturation point. After this point, It won't be getting, sir, if you have this material, if you want to magnetize it, we say, if you want to magnetize it, we say, sir, all the dipoles of this material are aligned. So we say this is completely or fully magnetized. This is completely or fully magnetized. After this, it is not possible to magnetize it. So we say this, let's suppose this is O and this is A. I can say A is what we call the saturation, or it is mentioned, it would be mentioned over here. Okay. So I'll write over here. A is saturation. So means it is fully magnetized. Now, if I say I have to demagnetize this material, like you are saying, sir, I have this material, I want to magnetize it. You'll keep it with the bar magnet for the complete night. Now I want you to demagnetize it. You'll take it away from the bar magnet, external magnetizing field. So means you'll decrease this, and it will reach over here. Guys, you are decreasing the external magnetizing field. You are making this external magnetizing field as 0 because you want to demagnetize this material. So I am saying the graph will be something like this and it will reach over here, OA, and let's call this as B. Now, we say I will still have the value. It does not come to 0. So I does not become 0 means when you demagnetize the material, you say, sir, in this case, all these dipoles will be now randomly aligned. No, it still has some magnetic properties retained. And this OB is what we call the retentivity. OB is what we call the retentivity. Guys, understand this. OB is called retentivity. This is how much it has retained its magnetic properties, characteristics, when H is 0. You wanted to demagnetize this material completely. You made the external magnetic field 0, but still it does not get demagnetized completely. It still has the value of I. So I can clearly say at this point B, H is 0, I is not equal to 0. Okay, let me make it over here. Yeah. Okay, so I can say in this particular case, at this point B, value of I is not equal to 0, but value of H is equal to 0. Now I want you to demagnetize it completely. Guys, what will you do? Sir, previously magnetizing field was in the forward direction. I say now apply the magnetizing field in the opposite direction. This is H. Now the dipoles which were aligned in the forward direction, guys, what will happen to these? Now this opposite magnetizing field will try to align them randomly. It will align them randomly because it will try to align them with its own direction. So first they will get aligned randomly. What will be the net intensity of magnetization over here? That is 0 because they are randomly aligned. So we say if you apply the magnetizing field in the opposite direction, we say at point C, can I say I will become 0, but value of H is negative. So means if you want to demagnetize this material completely, you have to apply the magnetic field in opposite direction. What is first? You have to magnetize it. So apply the magnetic field in the positive direction. So it gets magnetized completely. Now demagnetize it. From A to B, it gets demagnetized. It still have the magnetic properties at B. But if you want to demagnetize it completely, apply the magnetic field in negative direction. It gets demagnetized. Now, it is mentioned over here. At point C, I becomes 0. H is negative. And this OC is called cohesivity. What does cohesivity mean? Negative value of H required to make I 0. What does that mean? That means how much is the negative? This is OB, and this is OC. OC is the cohesivity. How much is the negative value of H required so that it gets completely demagnetized, so that I will become 0? This is cohesivity. Retentivity means at H is equal to 0, I will still have some value. It will still have some magnetic properties. Now I say magnetize it completely in the opposite direction, negative direction. You increase the value of this negative magnetic field. So we say now the dipoles which were aligned in the random direction will be aligned in the backward direction. Okay, completely. So it gets magnetized in this opposite direction, something like this. Okay, and here again OC and this is D. Again saturation will reach because all the dipoles are now aligned in the backward direction. It gets completely magnetized. It gets completely magnetized. Okay, now again I want you to demagnetize it. What will you do? Make this value is equal to 0. Make the external magnetizing field 0. So you'll basically do it something like this. So this is E. Again, guys, D is saturation. D is saturation. So what is this hysteresis? Hysteresis is basically magnetizing, demagnetizing, demagnetizing the material. Okay. So at E, what is the value of I? I in this particular case is, we say, sir, negative. Value of I is not equal to 0. Okay. And value of H is equal to 0. H is 0 because on this axis, this is plus H minus H, this is 0. Okay. Now I say again magnetize, guys. At E, if you have basically decrease this negative magnetic field, you are decreasing this negative magnetic field. Okay. So we say now if you want to completely, it is not completely demagnetized right now. You want to demagnetize it completely. So we say you increase the magnetic field in positive direction. You increase the magnetic field in positive direction. So now apply the magnetic field in the positive direction once again. So we said these dipoles inside this, they will be randomly aligned. They will be randomly aligned first. Then if you increase the value of H more, then they will be aligned here. At this point, what is the intensity of magnetization? 0. Then we say E, D, E, and this is F. Here, I is equal to 0, H is equal to positive. Guys, from O to A, it gets magnetized. From A to C, it gets demagnetized. From C to D, it gets magnetized in opposite direction. From D to F, it gets magnetized in forward direction. Sorry, it gets demagnetized. Now, again magnetize it. So we say, if you again magnetize it, it will again become magnetized in the forward direction. So increase the value of H, all of these will be aligned in the forward. So this is what we call the hysteresis loop because it is forming the loop over here. Now take a look at this. So you have a material, you want to magnetize it. You have a material, you want to magnetize it. So we say first we go from O to A. It gets at A, it is saturation. Okay. Then you want to demagnetize it. You decrease the magnetizing force, magnetizing field. And at point B, it does not get completely demagnetized. It has still magnetic properties in it. Now what will you do? You will apply the magnetic field in the opposite direction. You will apply the magnetic field in the opposite direction. So apply it in the opposite direction. So here at C, it gets completely demagnetized. Now magnetize in opposite direction. So increase the value of minus H. So at D, it gets saturation. Now, then again, decrease it from D to F magnet. It will be demagnetized. Again, it will be magnetized. This is what we call the hysteresis. This is what we call the hysteresis. All of the detail is mentioned over here. You can take a look. You can take a look from where to where everything is mentioned. I would request you guys to see it properly, write it properly, all the details. Take the screenshots. Okay. Now take a look at this. We say in this particular case, first you magnetize the material. So from where to where? I say from O to A. From O to A. Then you demagnetize the material. Then you demagnetize the material. Okay. Then you demagnetize the material. Okay. First you magnetize the material. Then you demagnetize the material from where to where? From A to C. See? First you magnetize from O to A to C, demagnetize, C to demagnetize, C to demagnetize. Okay, where is it? Okay, from A to C. Okay, from O to A to B, B to C, A to C. And then from where to where we do demagnetize it? C to D. We again magnetize it from C to D. Magnetize in opposite direction. Then again demagnetize it. So demagnetize it from D to F. D to F. Okay. And then it gets again magnetized from O to A. So this is what we call the loop, and this is what we call the hysteresis loop. This is what we call the hysteresis loop. Okay, one more thing. Area of the hysteresis loop is proportional to energy wasted per unit volume of the material in each cycle. Like if you are magnetizing a material, my dear friends, okay? It is something like this. If you are magnetizing a material, you are using energy in magnetizing or demagnetizing the material, okay? So how much energy is wasted? How much energy is wasted in each cycle? Like magnetization, demagnetization, magnetization, demagnetization. How much energy is wasted in each cycle? That will be proportional to area of the loop. Means if area of the loop is more, energy wasted in magnetizing, demagnetizing will be more in each cycle. Like. You have this. You have this. This is the graph for soft iron. This is the graph for hardened steel. We say in this case, area of this is more. So energy wasted here is more, energy wasted here is less. So that is the complete detail about this one. Okay, guys. Thank you so much. Make sure you hit the like button and comment down below. I have discussed all the topics over here. So that is for it. Thank you so much. Take care and bye-bye. Love you all. Thank you so much. Okay.